So when we looked at algorithms on weighted graphs for shortest paths and for minimum cost spanning trees, we had to use some data structures in order to make the updates efficient. So at the time we assumed that these data structures were available and we went ahead and did an analysis of these algorithms. Now let's go back and look at these data structures. So we begin with the union find data structure, which is used in Kruskal's algorithm for the minimum cost spanning tree. So recall how Kruskal's algorithm works. We arrange the edges in ascending order of cost and we process the edges in this order. So each edge we pick up, if it doesn't create a cycle, we add it to the tree. And we observe that not creating a cycle is the same as keeping track of the components that we have so far and checking that the endpoints lie in different components. So the edge u, v can be added if u and v currently are not connected, they are not in the same component. Now, as a result of adding this edge, the two components do get connected, so we have to merge the two components. So the bottleneck in implementing Kruskal's algorithm efficiently is to keep track of this collection of components in order to check which component a vertex belongs to and to merge two components whenever we add an edge connecting them. So formally, the problem that we are trying to solve is to maintain a partition of a set and update this partition. So by a partition, we mean that we have a set S and it's broken up into some disjoint subsets. So these subsets don't overlap, right? And every element belongs to one of these things. So there may be some which have more than one element, but each element is assigned to exactly one partition, right? And we call these partitions also components. So in Kruskal's algorithm and other applications, very often we start with a partition in which every element is on its own. So we never have maybe two elements in a partition. So we will call this setting up this data structure. So we will call it union find because the two operations we actually support on this data structure are called find. So this is a query operation. It says given an element S, right, let me know which component it belongs to currently. So this is an update which it doesn't update the data structure, it just queries the data structure and tells us in which of these partitions does S currently lie. And then we have an update which allows us to take two partitions, right? So maybe we take these two partitions and say now combine them into a single partition. So we call this union, right? So there is a union operation which merges partitions together, and there is a find operation which has to keep track of which partition a set belongs to, because an element belongs to, because over time the partition it belonged to originally would have got merged with other partitions. And because of these two operations, union and find, we call this a union find data structure. A data structure which supports these two operations efficiently. And the initialization of this union find is an operation which takes a set and breaks it up into, if it has n elements, breaks it up into n components, each containing one element. So the first issue that we have to deal with is about the names of the components. What do we call these components? A simple solution we will find is to just use the elements of the set itself as the names. Right? So it doesn't really matter what names we give. We just need to be able to check periodically whether S and T or U and V belong to the same component. So we just need to know whether find of U is equal to find of V. Right? So the exact choice of how we label find of U and find of V doesn't matter so long as we can check whether two labels are the same or they're different. But rather than manufacture a set of labels out of thin air, we will actually choose the labels to be the set elements themselves. So initially we said every element lies in a single partition. So supposing I have a set consisting of STU, then I would initially have three partitions, one containing S, one containing T, one containing U. Now the question is what do we call these partitions? Well, we'll just call them the same thing. We'll call this the partition S, we'll call this the partition T, and we'll call this the partition U. Okay, so sometimes the names of the elements will refer to names of partitions, sometimes they will refer to the names of the elements themselves. Now what happens when we merge, for example, supposing we merge these two partitions, right? Then the label has to be the same. So the element doesn't change, but maybe we might take the set, the label U and make it T. So now both element U and element T belong to the partition labeled T, right? So we just use as a set of labels the names of the elements themselves. So in particular, if we are dealing with graphs, the elements are the vertices typically. And we've already had a convention that we have n vertices in our set, we call them 1 to n. So our set of elements is 1 to n, and so is our set of components. So what we will do now is the easiest way to keep track of this is to set up an array, right? So we have an array which we will call component. And what will this array say? Well, this will say that for each of the vertices or nodes 1 to n, which component it belongs to, right? So initially we said each component will contain exactly one vertex, so we can just have a vertex n or vertex I in component I for every n. Okay. In general, after some time these might change, so this might have gone to component 3, this might have gone to component 7, and so on, right? So over time the component that a node belongs to changes because of the union operations. So then when we have find, we will just return the current value of component of I. And for union, all we have to do is we have to check and make all the components, both the components k and k prime have the same label. So rather than invent a new label, we will choose either k or k prime. In this case, we choose k prime. So what we will do is we will go through, and wherever we see a k, we will replace it by k prime. Right? So we will systematically replace every entry of the form k in this array to k prime. So after this, all component values which used to be k are now k prime. All which were k prime remain k prime. So effectively, the two components have been merged. So this is a very simple implementation of union find. So let's try and understand why this is not a very good implementation from a complexity point of view. So clearly, in order to make the initial things, we have to scan the array once, and then we just have to initialize component of I to be the value I. So this takes order n time. So this is fine. Similarly, finding an element is efficient. We just have to look up the ith element in the array, and remember that in an array, accessing any element takes constant time. So this is an efficient operation. It takes constant time. On the other hand, union is a problem, because the way we have described union, we have to go through every node, check if its component is k, and if it is component k, if component of I is k, we have to update it to k prime. Right? So regardless of what the components k and k prime currently look like, we will have to scan all the elements and update those which are k to k prime. So this will take order n time for just one union operation, which is independent of the size of k and k prime as current partition sets. Right? So if we do a sequence of m such operations, then this will be order m times n, right? And if it is n such operations, it will be n squared. Right? So a sequence of m operations, each of them will take order n time, and we would like to improve on this. So basically, we want to see if we can improve on the speed of the union operation. So let's make a slightly more elaborate representation. So we keep this array component as before, which tells us for each vertex I which component it belongs to. And the components as before are initially labeled 1 to n, and the names are drawn from the same set. So basically 1 to n are the vertices, 1 to n are also names of components, and initially the component of I is, the vertex I is in component I. Now we have a separate array of lists, right? So for each component that we currently have, we keep a list. So initially the list says that the component 1 consists of the vertex 1, the component 2 consists of the vertex 2, and so on. Okay? But over a period of time, we could have a situation where the component 4 consists of vertexes 1, 2, 4, and 7. Right? So for each component, we have the list of vertices that it belongs to. And we will also separately keep track of the size. So we'll say that the size of this component is also 4, where the size of this component is 1. Okay? So we have two auxiliary things. We keep for each component k the list of its members explicitly, and we also keep the size of this list. So we know exactly how big each component is at any given time. Initially, of course, the size is 1. Right? So when we do a make union find, we set component I equal to I as before. Then we initialize that the members of the list I are component I are just the list containing I itself, and the size of each component is 1. Now find is exactly the same as before. We just have to look at component and return the value that component I points to. Union is also similar to before. Okay? So what we need to do is we need to set everything that is pointing to k to point to k prime instead. So every entry in component which says k should become k prime, but now we can do this by just looking at members. So we don't have to scan all the elements 1 to n. We can look up every element that appears in members of k and update its value to k prime. Right? So this is one saving. We no longer have to go through 1 to n. We only have to look at exactly the members which belong to the set K. Then of course we need to update these new things. So members of K now become members of K prime. So we will merge these two lists. Now remember that these two lists are in sorted order. We can assume that they're always kept in ascending order of the names of the elements. So merging two sorted lists as we did in merge sort takes time proportional to the length of the final list. So this will be a linear time thing in proportional to the size of the components K and K prime. Finally, we now have one new component which subsumes the earlier two, so its size is exactly the sum of the previous two. Because these are partitions, no element was repeated, so every element that joins the partition is a new one. So size of K prime is exactly size of K plus the old size of K prime. So why do we get some benefit from this? So the first thing, as we said, is updating a component is now proportional to its size, right? So updating a component takes order size of K steps. It doesn't take order n steps. We don't have to go through every vertex from 1 to n. We can explicitly look up those elements mentioned in members of K and only update those values. But size of K actually plays a much more important role. What we can do now is we can determine whether to relabel K as K prime or K prime as K. Remember, we have a choice. When we merge K and K prime, all the elements are going to become part of the same component. So the new component will be either called K or it will be called K prime. So which one should we choose? So the strategy that we are going to do is to keep the name of the larger one. Right? So if the size of K is smaller than the size of K prime, that means K prime currently has more members than K. Then we will keep K prime as the name of the final set. So we will replace all the K's as K prime. And symmetrically, if size of K is bigger than size of K prime, we will replace all the K primes as K. Right? So the smaller set changes its name, the bigger set keeps its name. So this doesn't give us any benefit in the worst case of an individual union operation. Supposing we have size of K and size of K prime roughly the size of half. So if we have built up two components which are roughly half the size of the overall set, then whether we merge K or K prime into the other set, we have to update about half the values. So this is an order n operation, right? So earlier we had said that without doing anything fancy, we will scan all the vertices and the worst case for, and in fact every case of update will take us order n time. Now it says that there is a worst case where we cannot avoid taking order n time. So n by 2 is order n. So therefore, what have we gained? Okay. So what we have gained cannot be really accounted for in terms of individual merge operations. We have to look at the cumulative effect of a bunch of merges. So we need to do what is more careful accounting. We have to account for the operations. So remember, we did some careful accounting when we did things like when we used adjacency lists in breadth first search. We said, okay, across all the loops we will see each edge exactly twice. Therefore, across all the loops we take order m time. So we need to do a similar kind of careful accounting across not one merge but all the merges that take place. So the effect of merging the smaller set into the bigger set is that if I look at an individual element, the component, if it changes its label, right, if the component is currently K and it becomes K prime, then the new set is at least twice as big as the old set. Right? So supposing I had a set K and an element S in it, and I had another set K prime, okay, and then I decide to merge these into a single set. Now, by assumption, if the new set continues to be called K prime, that means that K was less than K prime, okay, or you could even say less than equal to, it doesn't really matter. So since K is smaller than K prime, what this means is that if I look at K plus K, which will be double the size of the old set, this will be less than or equal to K plus K prime just by substituting, and therefore this is going to be, so this is the size of the new set, right? K plus K prime is the size of the new set I construct, and it's going to be at least twice the size of the old set. Therefore, whenever the name of the set labeling the component of an element changes, the new set it belongs to is at least double the size. So now let's look at some sequence of M union operations starting from the initial condition when I have all elements in separate partitions. So what can happen in each operation? Perhaps I combine two elements. Right? Now if the next time if I combine these two, then totally in 2 operations I have only affected 3 elements. So in the worst case, if I start doing this separately each time, in one operation I affect 2, in another operation I affect 2 more, and so on. So after a sequence of m operations, at most 2m elements have had their status changed from the initial condition when they were pointing to a component consisting of only themselves. Okay, so that means only 2m elements have ever been affected by my union operations. That means a component cannot have got larger than 2m, right? Because in order to get into a component, something must change, and only 2m elements are allowed to have any change applied to them at all, right? So the size of any component after m union operations at most 2m. But how does the size grow? It goes 1, 2, 4, because it keeps doubling up to m, right? So after log m steps, okay, if I double 1 log m times, I will get m. So therefore, a component S can be relabeled, a fixed element S can be relabeled at most log m times, right? So because we have this doubling, the number of times that a set can be, an element can move into a new set is restricted, because each time it moves, the size of its component doubles, and there's a limit on the largest component it can belong to. So therefore, if we look at the sum total of m union operations, we know that 2m, so order m elements have had their component updated, and each has been updated at most log m times, right? And remember now that when we are updating elements, we don't touch any element which is not updated. It's not the old setup where we have to scan all the nodes 1 to n in order to decide which ones to update. Because we have this list members, okay, when we want to update the component k, we exactly update only those components. So we only touch the components which change. So m elements change log m times. So totally we have m log m steps of change. Right? So if we do m union operations, we take m log. It is not that each one takes m log m time directly, but the cumulative total of m union operations is only m log m. Right? So this we can average out in a way to say that therefore, since there were m operations and the total is m log m, even though some were small, some were big, on an average they take log m operations. So this is a different kind of analysis. It's not quite the analysis we did for example, for the adjacency list in BFS, where we just added up everything across the whole thing. Here also we are adding, but we are also kind of pointing backwards and saying, okay, now there are totally so many operations, and the total time taken across all these operations is so much. So we divide and we give each a share of the total cost. So though it is not the case that every single operation takes log m time, we can kind of believe that this gives us a log m implementation of the union operation. Right? So this kind of analysis is called amortized complexity. So this is a term which actually comes from accounting and from financial things, where you have certain costs which, for example, you might have in order to run a business, you might have to set up something, right? You might have to set up an office and all that. So now if you cannot say that my cost on day one was a lot because I have to do a lot of work to set up the office and therefore day one was expensive. What you have to do is look at the total lifetime of your operation and say, okay, this cost is divided across the entire thing, so is it worth it? Right? That is called amortization, where you kind of take some fixed cost of a fixed piece of equipment or asset or work and divide it across the entire lifespan when it's going to be used. So in the same way here, we are kind of doing an amortized analysis. We are counting across all the m union operations how much time it takes, and then working out that each one takes roughly log n time. So how do we use this union find data structure in Kruskal's algorithm? So remember, in Kruskal's algorithm, we initially sort the edges. So we have E1 to EM, an ascending order of cost. Now we begin with a trivial partition. So we do a make union find of our set of vertices. So each vertex j is labeled j. So we have exactly n partitions, one containing each vertex. Now we need to add the current edge we are looking at, provided it doesn't create a cycle. This is the same as saying that its endpoints must be in different components. This is the same as saying that if I do find of u and find of v for an edge uv, right, find of u is not equal to find of v. And if find of u is not equal to find of v, then I need to do a merge. So I need to do the union of these two components. I can get their component names by using find u and find v. So this will be some k in general, the component containing u. This will be k prime, the component containing v. And I do a union of those, and I've got a new component which contains both u and v. So since the tree has only n minus 1 edges, we will only add n minus 1 edges out of the total set to form the spanning tree. So therefore we have order n union operations to perform overall, and we know therefore for any m operations we said it will take m log m. So for n operations we have an overall amortized cost of n log n, right? So the maintaining the partitions and adding them and all that takes n log n. Now initially we had to sort the edges, so that takes m log m, but as we discussed when we actually looked at Kruskal in detail, since m is at most n squared, we know that log m is 2 log n at most. Okay, so at the level of orders of magnitude, log m and log n are the same, so we can look at m log n, m as the same as m log n. Right? So the total cost now comes out to m log n plus n log n, so we get m plus n log n. And if you remember the complexity that we claimed for Prim's algorithm and also actually for Dijkstra's algorithm, which is similar to Prim's in structure using heaps, we claimed that those were both of the type m plus n log n if we used a heap to do the minimum distance calculation. So therefore Kruskal's algorithm with a union find data structure essentially has the same complexity as Prim's algorithm using heaps. So to summarize, what we have seen is that we can implement union find using an array to keep track of components, an array of lists to name the vertices in each component, and another array to keep track of the size of each component. With this, the initialization step of making the union find data structure of disjoint individual element partitions is order n. Find takes constant time. And the amortized complexity for a sequence of m operations is m log n. So we can think of each union operation as taking log m time for over a sequence of any such m operations starting from the initial thing. In the last lecture, we saw an array-based implementation of the union find data structure in which the find operation took constant time, and we used an amortized analysis to claim that the union operation over a sequence of m unions would take m log m time. So effectively each union was a logarithmic time operation amortized over the entire sequence. Now we will see a more sophisticated implementation which has even better complexity. So recall that the union find data structure keeps track of a partition of a set S and supports 3 operations. One is the make union find, which creates a trivial partition where each element belongs to its own, each element is in a singleton partition named by itself. So we use the same names for the partitions and the elements. So each S is in a partition called S, each small s. Find tells us which partition a given element belongs to, and union combines 2 components or 2 partitions into a single one. So the array-based implementation uses an array called component to tell us which component each element belongs to. It keeps an array of lists to tell us which elements belong to each component. So it's a kind of reverse mapping. For each component K, it tells us which members of the set belong to that. And finally, it keeps track of the size of each component because we merged components by taking smaller ones and relabeling them with the names of the bigger ones. So make union find was an order n operation, find was an order 1 operation, and the amortized complexity of the union operation was log m for a sequence of m operations. So we will now have a different representation. We will use nodes with pointers. Right? So each element of the set will now be represented as a node. The node will have 2 parts. It will have the name, which is the element that you're keeping track of, and a label part which keeps track of its component. Right? So it's a pointer to the component. Okay? Now remember that the names of the components are the names of the elements. Right? So if we have a name here, for example, we have a name J, it says that this node represents the element J, and its label points back to itself. So it says this is J belongs to the component J. Here on the other hand, we have the element I, and through this field we go to the first node which points to itself, and this said that I belongs to component J. So I belongs to component J. So we are we are making heavy use of the fact that the names of the elements and the names of the components are the same. So we are kind of, in some context, we are interpreting the name field as the name of the element, and when we are following pointers, we are interpreting the name field as the name of the component. So make union find is the initialization. So what it does is it will set up each component as a singleton containing an element of the same name. Right? So I belongs to the component I. So there is a node I which points to itself. Right? Then there is a node K which points to itself, indicating this is a component called K containing K. This is a component called J containing J. So we have n such components, 1 to n. So we have n such nodes, each of which contains the name in the first component and a pointer to itself in the second component, saying it's a singleton component. So after a period of time, we will see that when we merge nodes, these pointers will point, instead of themselves, it will point to other things. So here, for example, could be a component containing I, J, K and L. And the structure says that the name of the component is actually J. Right? So this is the component J and it contains I, J, K, L. So you can see that the element I has a pointer not to itself but to another node. So if we follow this, we find that it's pointing to an element J which points to itself. So its name of the component of I is J. Similarly for L, if we start from L, L points to I points to J, and so on. Right? So we will see that this is how we will use to, this is the strategy we use to implement find. We have to start with a node and go up the path, and this will be a tree. So every path will end at the root, and the root will be the name of the component. So just to help us navigate this tree a little easier, let's assume that we have the following additional arrays of pointers and numbers. So we will keep track, first of all, of where each node is. Right? So we have an array called node here, and each element of the array is a pointer to the node containing that element. So the entry I says node I is here. Okay? Entry J says that node J is here, and so on. So there will correspondingly be an entry which says that node K is here and node L is here, and so on. So every element in our actual set will have a pointer from this node array to the actual node in the tree, where it, or the set of trees, the set of components, the actual node where that value lies. Then we need to know which are the components which are currently active. So here in this particular segment, IJKL, we said the component is J. There used to be a component I when I was initialized. There used to be a component K. There used to be a component L. But these names are no longer in use because these components have got merged directly or indirectly with J. So right now among IJKL, only J remains. Right? So we say that the root of J is the component J is the node containing J. And for all the other labels I, J, K, L, we say that I, K and L, we say that there is no component called I, there is no component called K. So we just have a blank thing saying there is no root for these things. If you want to find the root of this component, go to the node I and then work your way up to it. Finally, we will use a similar strategy as before in terms of merging by size. So we'll just explicitly keep track of the size of each component. So here it says that the size of this component IJKL is 4 because there are currently 4 elements in it. Right? So we have this node pointer which points to each element in the set where it currently lies, which node contains that element. We have a root pointer which tells us for each component which is currently active in our partition, which is the root of that partition. And then we have the size which tells us the size of each component. So when we do union, we basically do this merging of the smaller one to the larger one, right? So here we have two components. We have component J, which is J, K and M, and we have component I, which is I and L, right? So now we want to do the union of I and J. So now we first will, somewhere we will have recorded that the size of I is 2 and the size of J is 3, right? So having recorded this, we have to now therefore merge I into J. So what this means is that this edge which says that I is the root of this string has to be destroyed, and instead we have to put a link like this and merge these two trees into one larger tree. Right? So if we do that, this is the resulting tree. Now we have a single component called J. Of course, we would have updated the size of J to be the size of I plus the old size of J. So now it will say 5 instead of 3. And notice that this whole operation is an order 1 operation because we take a fixed number of steps to find out the sizes of the two components, to find the roots of the two components, and to decide which root to massage into which other root, right? So whether to make I point to j or j point to I, right? So this is an order 1 operation, okay? And that's because we have the size information to tell us the size. We don't have to go through the component to find its size, and we have this root information that directly tells us where the roots of the two partitions are. So we just have to go directly to that place and make one point to the other, or vice versa. Now find, on the other hand, as we saw, requires us to start from the value that we want to check and work our way up to the root. So supposing we say find of u, then remember that we'll have this node array, okay? And so node of u will say that the node containing u is here. So we will start there and then we'll follow this path. So we'll say, oh, this point's here, and then this point's here, and this point's here. And finally, when we reach a node which points to itself, that is the name. So then we will say, therefore, that find of u is equal to j. Okay? So this takes time proportional to the path that we traverse from the node to the root. Now remember, initially we had a path for u which looked like this, right? So initially every node has a path of length 1 to itself, saying that it is its own root. Now why does this path change? It changes because of the union operation. Every time we do a union, one node which used to point to itself now points to another node, and everything below it has its path increased by 1, right? So therefore the path increases by 1 every time the label of j changes. If we are going to go from find of j from j to the root, how much time this takes changes by 1 each time j changes its label. But as before, we are doubling the component size each time we merge, right? So each time we do a union, the label containing j contains twice as many elements as it did before. Now finally, the best you can do is to combine all the nodes in your graph into a single component, right? So the maximum component size is n. So therefore we start with a component of size 1, then we double it to 2, and we double it to 4, and eventually we cannot go past n. So this whole thing can be at most log n steps. So therefore log n times the label of j can change. Each time the label changes, because we take the root of another component and attach it here, the path length increases by 1. So the path length increases 1 plus 1 plus 1 log n times. So the path is at most log n. Okay? So with this analysis, we can see that because we are merging smaller components into larger components, find will take log n time. So we are now at a place where we are dual to the earlier data structure. In the earlier data structure with arrays, okay, so we had find was a constant time operation, and we had this amortized analysis that said that union was log n. Now we have this pointer based thing which says that union is order 1 but find is order log n, right? So it seems that we have got essentially a similar kind of structure, except that we have reversed the complexity of the two operations. Now it turns out that we can do something much more clever and actually make it even more efficient to find. So we can keep the order 1, of course, for union, but order log n can actually be reduced. So the key is that once we have traversed this path from u to j, right, we know in some sense that not only do we know that the path containing the component containing u is j, we know the component containing l is j, we also know the component containing I is j. So why don't we make use of this information and not recompute it each time we come back, right? So what we will do is we will do the usual find j, right? So we will traverse the path, and then we will go back from j to the root and say, okay, now I know this is j, so let me bypass this whole thing and maybe point directly to j. So I remove, okay, so I remove the earlier things. So I will remove this edge and directly go. Similarly, before I remove, of course, I'll go there. So I'll say I can remove this edge and directly go. So for each step, I can remove until I finally reach the one which is just below the root. So basically, now I will end up having a flat tree along this path. This path which used to look like this is now been flattened out like this. So everything now has a direct access to the path, right? So we are flattening the tree, right? So if you want to look at it pictorially, so I start with this, okay, and then if I look at the current situation, then I will replace this edge from U to L as an edge from U to J directly. Then I will replace the edge from L to I as an edge from L to J directly, and so now I end up with this flat tree. So now subsequent lookups are going to take only one step from U and L, right? So the first find takes log n time, then it takes constant time. So now you can actually show, I mean, this is not an easy calculation, so we are not going to try and attempt it now. But after this you can show that just like we can do an amortized analysis for in the earlier array-based implementation to get an overall log n, m log n cost, m log m cost for m union operations, here you can actually show that a total of n finds will actually take something almost linear in n. Now, almost linear in n is actually n times a function called alpha of n. Okay, and this alpha of n is something which is the inverse of the Ackermann function. So the Ackermann function is something which grows very fast. Okay, so it is a function which grows faster than any exponential. Now this is like the log of the inverse Ackermann, I mean the log of the Ackermann. So you know that for the exponential function, the inverse is the log. So that's why log n is nice for us. It's slow, right? Log of 1000 is 10. Log of 1 billion is 20, 1 million is 20, log of 1 billion is 30. It grows very slowly because in the other direction it's growing fast. 2 to the power 10, 2 to the power 20, 2 to the power 30 grows very fast. So similarly, Ackermann grows very fast. So if you take what is the corresponding log function, for what value is this the Ackermann input, it grows very slowly. In fact, it is claimed that alpha of n is at most 4 for any value of n that you are likely to encounter in a practical computing problem that you can solve. Right? So you can think of this as being something like order n, because we know that alpha of n is less than or equal to 4. So this is like 4n. Right? So path compression gives us a drastic reduction from n log n, which we would get without path compression, to something which is linear. So therefore now by moving to this pointer based thing, we have actually achieved a considerable saving compared to the more direct array based implementation that we gave in the last lecture. So to summarize, if we implement union find using nodes with pointers, then we can do, of course, the initial setup, the make union find in linear time. Union now becomes an order 1 operation because we just directly access the two roots and merge the smaller root with the bigger root. And find, now if we use this path compression trick, although in principle it is n log n for n operations, it is n alpha n for n operations if we use path compression. So we have seen how the use of a clever data structure, the union find data structure, can make Kruskal's algorithm more efficient. The other two algorithms which we need to make efficient are Dijkstra's algorithm for the single source shortest path and Prim's algorithm for the minimum cost spanning tree. Both of them, it turns out, require a data structure that is usually called a priority queue. So to understand priority queues, let's look at the following scenario. So supposing we have a job scheduler running on an operating system. So when we run multiple tasks on an operating system, each of them runs for a little bit of time and then is swapped out. So a job scheduler maintains a list of all jobs which are pending along with their priorities. Whenever the processor is free, the scheduler picks out a job with the maximum priority in the list and schedules it. Now what happens, of course, is this is dynamic. Right? So while some jobs are running, other new jobs may arrive. So at each time when new jobs arrive, they will come with different priorities, and it's the job of the scheduler to make sure that the new jobs with higher priority come ahead of older jobs with lower priority. So from a data structure point of view, our question is, what is the best way for the scheduler to maintain the list of pending jobs with their priorities so that this list can be updated dynamically as this list gets updated, as new jobs arrive. So this is what we call a priority queue, right? So we have two basic operations in a priority queue. The first is to extract the next job, which in this case means take the job with the highest priority and remove it from the queue. Now of course we have a situation where you have multiple jobs with the same priority, so we don't assume that the priorities are unique. But if they are not unique, then we can assume either that there is some tie-breaking rule or we don't care which one of the highest priority jobs you get. Right? So the main operation is delete max. Delete the maximum priority item from the queue. And then there is an insert. So a job will come, it will be inserted, it will come with a priority. So we need to insert it into the list so that subsequent delete max take this one into account. So the first solution that one could think of to keep such data is to maintain a list, some kind of a linear structure, an array or a list. Since it's growing dynamically, a list is the obvious choice. Now, if we keep an unsorted list, then it's easy to add a job, right? We just have to append it to the list. So insertion is a constant time operation. It takes time O1. But as we have seen many times, if we have an unsorted list, then we have to scan the entire list to find the minimum or the maximum. So in this case, if we want to do a delete max from an unsorted list, this operation is going to take us linear time proportional to the size of the list or the number of jobs that are pending at the moment. So the only useful thing one can do with the list otherwise is to sort it. So if we sort it, we can try and maintain the jobs in decreasing order of priority. If we do it in decreasing order of priority, then the maximum priority job is always at the beginning of the list. So we can instantly find it in constant time. So delete max now becomes a constant time operation. But then what happens to insert? Right? We need to insert a value into the list. And as we saw with insertion sort, when we insert a value into a sorted list, we have to walk down the list to find the correct place to put it in. So that will now take order and time. Right? So between an unsorted list and a sorted list, we have a trade-off. In an unsorted list, delete max takes linear time. In a sorted list, insert takes linear time. So one or the other is a bottleneck. Right? So whether we use an unsorted list or a sorted list, over a sequence of n jobs, supposing n jobs arrive in the system and we process them, then we will be inserting them n times and deleting max n times. So whichever solution we use among these two, we will end up spending order n squared time. So this suggests to us that a linear structure, a one-dimensional structure, has a severe limitation with respect to solving the representation of a priority queue in an efficient way. So we have to go from a one-dimensional structure to a two-dimensional structure. So let us start with a very naive two-dimensional structure just to show how we can get drastic improvements just by moving from one dimension to two dimensions. So here we assume that we know in advance somehow a bound on the number of total jobs we can have. So we have assumed in this case, say that n is 25. So now what we do is, instead of maintaining a one-dimensional list of length 25, maximum length 25, we reorganize this list as a square array of 5 by 5. So square root n by square root n. So now you can see here an example of such a thing. So we have 25 minus 6, 19 jobs currently with different priorities in there. Okay. Sometimes two jobs may have the same priority, that doesn't matter. But the important thing is that we are not necessarily maintaining it in a kind of sequential way through this two-dimensional array. All we are guaranteeing is that every row, as we look at the row from left to right, is an ascending order. Right? So we have the first row is in ascending order, second row is, but the rows themselves have nothing in common with each other. So you could have bigger values in the second row than the smaller row and vice versa. So for example, 19 is bigger than 12, but then 17 is bigger than 8 and so on. Right? So these are kind of 5 independent lists of jobs which together make up the total set of jobs, and each list is sorted. So now suppose we want to insert a new job into this list. So the strategy is very simple. We want to insert it in the correct place in the first row that has free space. Now to find out if one of the rows has free space, we need to walk down this thing to find out how many elements are there. So we will save that work by keeping this extra information here, which is the size of each of the rows, right? So let's assume that we have the size available of each of the rows. Now we know in this particular case that each row is of size 5 at most. So if the size is 5, right, then we know that if we try to insert 11 into this first row, right, that 11 will not be able to fit there because there is no space basically. So then we move to the next row. Once again we see that the size is 5, so then we go to the third row. And now we see that there is a space because there are only 3 elements in this row and it can take 5. So now we walk down this list and find the correct place to insert it and insert it as we do in insertion sort. Right? So now the question is, how much time does this take? Well, we know that we have square root of n rows. Right? So it takes square root of n steps to find the correct row to insert going from top to bottom. And then we have in each row square root of n entries. So if we do our usual insertion, it takes time proportional to the length of the row we are inserting into. So we have a square root of n scan to find the correct row. a square root of n scan to find the correct position within that row. So overall, it is time order of square root of n. Right? So what about deleting? Right? So we want to delete the maximum element in this array. Now because each row is independent of the other row, we don't know in advance where this maximum element is. However, we do know that in every row the maximum element is at the end because each row is sorted. Right? So the first thing we do know is that every possible maximum element is actually at the end of its row. Okay? So we have these 5 rows, we have 5 maximum elements, and now the overall maximum must be among these 5 elements, it must be the largest one. Right? So we can just use the size information. So we know it's the 5th element in the first row, the 5th element in the second row, the 4th element in the third and 4th row, and the second element in the last row. So using the size information, we can scan through all of these, right, and identify which is the biggest one. In this case, it is 43. Right? So we identify that 43 needs to be deleted. Okay? And then having deleted 43, then we remove it, and then of course we have to also reduce the size back from 4 to 3. Okay, so we can keep track of the size as and when we manipulate. In the previous example also, when we had increased 11, we made this 3 into 4. Okay, so again it's an order root n operation. So we have now achieved a data structure which keeps track of elements in a priority queue, where insert takes order root n time, delete max takes order root n time, and therefore now processing a sequence of n jobs takes n root n time. Okay, remember that previously it was order n square. So we have reduced from order n square to order n 3 by 2 if you want to write it this way. Okay? So this is just a sampler to explain that a two-dimensional structure can give you significant savings over a linear structure. So of course we are not going to be happy with this, otherwise we would have just stopped with this. So we can actually do much better than n to the 3 by 2, and this is what we are going to discuss in a later lecture. To give you a preview, what we are going to do is to maintain it not in a simple array or a square matrix like this, but in a special kind of binary tree called a heap. Okay? So this will be a binary tree, so it will have a structure like this, and it will be balanced. So basically all the paths will roughly have the same length, and what this will mean is that the height of the tree, okay, will be logarithmic in the size of the tree. And this will make both insert and delete max take log n operations, and this will give an overall bound for n operations of n log n. The other thing is that we actually maintain it as a dynamic tree like this. We don't have to make an assumption as we did in our simple solution that we just proposed, where we upper bound n. Right? We can have a solution where the tree can grow as large as we want, so long as we make sure that we grow it in a systematic way to keep it balanced. Okay, so this is what we will look at next. We will look at this data structure called a heap, which implements a priority queue by maintaining a type of binary tree. Let's now look at heaps. So recall that our goal is to implement a priority queue. In a priority queue, we have a sequence of jobs that keeps entering the system. Each job has a priority. Whenever we are ready to schedule a job to execute, we must pick up not the latest job or the earliest job that we got, but the job which currently has the highest priority among the waiting jobs. Therefore, we need an operation called delete max, which will search for the highest priority job among those that are pending and schedule it next. And we obviously have an insert operation which adds these jobs dynamically as they arrive. So we saw last time that a linear structure will not allow us to simultaneously optimize these two. Okay, we end up with an order n operation for delete max or an order n operation for insert. Then we saw a trivial two-dimensional array which gives us an n root n solution. That is a root n operation for each of these. So over n operations, it's order n root n. But we said that we will find a much better data structure using a tree of a special type called a heap. So the heap is going to be a balanced tree whose height is logarithmic in the size. That is, if I have n nodes in the tree, the height, that is the number of edges from the root to any leaf, will be log n. And with this, it will turn out that both insert and delete max are proportional to log n. And therefore, processing n jobs will take time n log n as opposed to n root n for the array or n squared for the linear representation. We also said that this heap in principle is flexible and can grow as large as we want, so we don't have to fix in advance the size of the heap that we need to keep. So let's start looking first at what a heap is. So a binary tree is a tree where we have a root and every node has 0, 1 or 2 children. So binary trees in general can have arbitrary shapes. Okay, so we could have binary trees which look like this, where the root has one child, this has 2 children, or it could look even more skewed in one direction. Okay, so binary trees can have very strange shapes, but a heap is a binary tree which has a very specific shape, where we fill up the tree nodes, or we add the tree nodes in a specific order. So first we start at the root, then we must add the left child of the root, then the right child, and this way keep going level by level, left to right. So we add this node, then we add this node, then we add this node. So once I know how many nodes are there in the tree, I know precisely what the shape is, right? So the shape is fixed. Right? So that is the first feature of a heap, that if I have a heap with n nodes, then the shape of the tree is deterministically fixed by this rule that the n nodes must be inserted top to bottom, left to right. Okay. Then we have a value property. Okay. So the value property says that, okay, so what is happening in the tree is that we have nodes and each node is a value. So whenever I see a node with value v1 which has children v2 and v3, okay, then what we want is this is bigger than or equal to v2 and bigger than or equal to v3, right? So among these 3 nodes, the largest one must be v1. So this is what is called the max heap property. So this is a local property. It just tells us at every node, look at that node, look at the 2 children, the node must be bigger than its 2 children. So here is an example of a heap with 4 nodes. So first, because it is 4 nodes, every 4 node heap will have this shape, because the first node will be the root, the second node will be the root's left child, third node will be the right child, and the fourth node will start a new level. Then moreover, we can check the heap property, right? So we see that 24 is bigger than 11, 24 is bigger than 7, so this is a valid node for a heap property. 11 is bigger than 10, there is no right child, so this is a valid heap. There is no child of 7 at all, so by trivially this is a valid heap node, and 10 is a valid heap node for the same reason. Okay, so every leaf node which has no children always satisfies the heap property. Okay. So once we have a leaf node, there is nothing to check. So here is another heap. This one has 7 nodes, so again the shape is fixed, and again you can check that this is bigger than 11 and 7, 11 is bigger than 10 and 5, and 7 is bigger than 6 and 5, and the rest are all leaf nodes, so there is no problem. Right? So these are 2 examples of heaps. So what is an example of something that is not a heap? So here we have something which is not a heap because the structure is wrong. Right? So we said that you can't leave holes. You must go top to bottom, left to right. So there should be some node here before you add the node on the right. Right? So there, where is this node? This node is missing. So this structure is not right. For the same reason, this structure is also not correct, because we have here something which is missing a node at this level and we started a new level. Right? So both of these are not heaps for structural reasons. Here on the other hand, we have something which is a valid structure. In fact, we saw a heap before which has this structure. The problem is with this node. Okay? So we want 7 to be bigger than 8 and 5, but this is of course not the case. 7 is not bigger than 8, 7 is smaller than 8. Right? So this node 8 actually violates the heap property. So something can fail to be a heap either because the tree structure is wrong, or because at some node the heap property is violated. In this case, the node that violates the heap property is 7, because one of its children is actually bigger than the node itself. So now we have to implement these 2 operations on heaps, insert and delete max. Right? So let's see how it works. So first let's insert 12. So insert 12 means I have to add a value to the heap. So the first thing when I add a value to the heap is I must expand the tree. So where do I put this node? Right? So this is now fixed because we know that heaps can only grow and shrink in a particular way. So I must add the new node, okay, left to right, top to bottom. So in this case, if I go left to right, top to bottom, right, I come to this point. Now I can't add anything more, so it must come at the next level. Right? So the first thing is that this is where the new node must come to contain 12. Now, if I put 12 into this position, the problem is that I might not have the heap property satisfied. In this case, you can see that the heap property actually fails right here because 12 is bigger than its parent. Right? So 10 violates the heap property. But notice that this can only happen above. Okay? So what I mean is that when you insert something, it's a leaf. Right? So since 12 is a leaf, it cannot fail the heap property below 12 because there is no child below 12. If at all the property fails, it is because the parent of the new node has a value which is too small. So there is a simple way to fix this locally at least, and that is to exchange these two. Right? So I exchange this 12 and 10, and now I fix the problem here. But now I've changed the value at this point, so I have to look at this configuration to see whether what I moved the 12 into violates the heap property or not. And here again you can see that there is a problem because 12 is still bigger than its parent. So then I exchange that, so now I've exchanged this. Now in the process what has happened is that 12 has gone from here to here, okay? And now the first thing we have to convince ourselves is that the local heap property that we just fixed doesn't need any further fixing. In other words, we have to guarantee that there is no problem at the other side between 12 and 5. Okay? And this cannot happen because we originally had 11, 5 and something here. We knew that 11 was bigger than 5 and it was bigger than this something. Then we did an exchange and we brought a 12 here. Right? So if at all the problem is only between 11 and 12, and since if there is a violation, 12 is bigger than 11, that's why there is a violation, but 11 is known to be bigger than the other side. So if I move 12 to the top of this 3-node structure, it cannot be smaller than the other side because the root currently is already bigger than the other side, and the only reason I move 12 up is because it is still bigger than that side. Okay? So then in a nutshell, when I do an upward swap like this, I can be sure that I don't have to look on the other side. Right? I just keep looking up. So now I brought 12 up to this point, so now I need to check whether there is any further violation, and it turns out that 12 is smaller than 24, so I can stop. Right? So this was the result of inserting 12 into this heap. Now I can insert a new node 33 just to convince ourselves we know what to do. So as before, if I insert 33, so this was the result of the heap after 12, and now I've inserted a 33 here. Okay, so it has to be to the right because that's the next node in the structure, and I put the value, but it violates the heap property between 11 and 33, so I swap it up. And then again I have a violation here, so I swap it up again. Again I have a violation here, so I swap it up again. And now I have reached the root, so actually it's become the biggest node, and now I can stop. Okay. So how long does this take? So every time we do an insert, we start at a leaf node, a new leaf node that we create, and we walk up to the root. Right? So the worst case of such a thing will depend on the worst case height of the tree. We have to bound the height of the tree. The height of the tree, by definition, if I have a tree like this, okay, so the height of the tree is the longest such path. The length of the longest path from the root to the node. Okay? So you can either count in terms of number of edges or in number of vertices. If it's vertices, this one will be 4. If it is edges, it will be 3. It doesn't really matter. But the point is that the longer such path will determine the complexity, because the longer the path, the more times I may need to swap on the way up. So what can we say about the height of a heap? Okay? So the first thing to notice is that in a heap, because of the way that we have done it, okay, so at the root node we have at level 0, if we call this level 0, okay, we have exactly one node. At level 1, at most we have 2 nodes. Okay, so we can write this as 2 to the power 0, and this is 2 to the power 1. Now of course now each of these will have 1, so it will double, right? So at every level the number of nodes doubles because each of the previous level has 2 children at most. So we have 2 square. So in this way we have number of nodes at level 0 is 2 to the power 0, at level 1 is 2 to the power 1, at any level I is 2 to the power I. Okay. So if we have k levels, then the levels are 0, 1 up to k minus 1. From what we have just said, that is 2 to the 0 plus 2 to the 1 plus 2 to the k. 2 to the k minus 1 it should be, sorry. Okay. So it will be 2 to the 0 plus 2 to the 1 plus 2 to the k minus 1. Okay. Now this, and one way to think about this is a binary number with k ones. Right? So binary number with k ones is just 2 to the power k minus 1. In other words, if I fill up a binary tree for k levels, I will have at most 2 to the k minus 1 nodes. Right? So therefore the number of nodes is exponential in the number of levels. So therefore if I have the number of nodes, then the number of levels must be logarithmic in that. Okay? And the number of levels is what determines the length of the longest path. And therefore insert in any heap will take time log of n, because there is every path is going to be guaranteed to be of height log n. Okay, so the other operation that we need to implement for a priority queue is to delete the maximum. Right? So the first question is, where is the maximum in a heap? So the claim is that the maximum is always at the root. Why is that? Because if I start anywhere, I know that among any 3 nodes, the maximum is at the top. Right? So if I look at 33, for example, 33 is bigger than 24 and 7. Right? But inductively, I know that 24 must be the biggest node in this subtree, and 7 must be the biggest node in this subtree. So therefore, 33 is bigger than both, so it must be the biggest node overall in this entire tree. Okay? So the model is the maximum value is always at the root. Right? So now the question is, if the maximum value is at the root, right, how do we remove it from the tree efficiently? So let's say we remove the maximum value. So then this leaves us with a hole, right? We don't have any value at the root now. At the same time, because we have removed the value, we have reduced the number of values in the tree by 1. But we said that the structure of the tree is fixed. If we reduce by 1, we cannot remove the root. We must remove the last node going on this left to right, top to bottom order. So we must in fact remove the node here. This node has to go. Right? So now we have a value which is homeless. It doesn't have a node to belong to. And we have a home which is empty. Right? So what we will do is we will move this 11 to the root. Right? Now unfortunately, because we have disturbed the heap order by doing this, taking some arbitrary node from a leaf and moving it to the root, we don't know whether we have the heap property satisfied or not. Now the only place where a heap property can be violated is at the root, because everywhere else the local neighborhood was not touched by this operation. Right? The only other place where a neighborhood was touched was here, but all we did was remove a node. If you remove a leaf, then it cannot violate a heap property, because for the upper node it was already bigger than both these children. Right? So this is okay. So the only place we could have a violation is here, and indeed we do, right? Because 11 and 24 are in the wrong order. So we will start now restoring the heap property downwards. When we insert it, we do it upwards. So we'll start here and look at this, and then we will look at both directions, and we'll take the bigger one of the two and move it up. Okay, so we swap with the largest check. Suppose, for instance, that this had been not 7 but 17. Okay, then what would have happened if we had moved 17 up is we would have got 17, 11 and 24. Right? And this would not have fixed the heap property, because this would still be wrong. Right? So we must take the bigger of the two and move it up, because among these three, the biggest value must be at the top. That's the definition of the max heap property. Right? So we exchange the 11 and the 24. So 24 goes up to the root, and then 11 has come in this direction. So we must again check whether this part, which has now been disturbed, satisfies the heap property. And of course in this case it doesn't, because 11 and 12 are not in the correct thing. So again, among these three, I have to take the maximum value up. So I take the 12 up and move the 11 down. Okay? And now I have to check this section whether this heap property satisfies. Here it is satisfied, and now again stop. Okay? So in delete max, I start from the root and I walk downwards. Okay? So supposing we do this again, okay? Then I remove 24, right? And then I move the 10 from the last leaf to the top. Then I again have to fix this problem, right? So I exchange the 10 and the 12. Then I have to look at this and fix this problem. So the biggest of these three is 11. I fix the 10 and the 11 and I get it. Right? So now by making sure that I take the biggest one up, again I don't walk down the other direction. So I am always walking down a single path. Right? So once again, just like insert, the cost is proportional to the height. And since we know that in a heap the height is logarithmic, delete max is also an order log n operation. Right? So what we have done is we have shown that a heap actually does both delete max and insert in log n time. Okay? Now another very nice property about heaps is that we don't actually need to maintain a very complex tree-like structure. We can actually do heaps in arrays. To do this, we observe that we can canonically number all the nodes in a heap. Right? We start numbering the root by 0. The first node we fill below the root by 1, the other child by 2, and so on. So I have a numbering 0, 1, 2. So I can actually represent this heap as an array which has indices 0, 1, 2, and so on. Okay? Now in this, the claim is that if I am at a position I, okay, so if I have some position I, then the children of this are 2i plus 1 and 2i plus 2. You can check this everywhere. So therefore, if I want to actually go to a heap and ask something about the heap property, then I will just look at position I, and then I will jump ahead to position 2i plus 1 and 2i plus 2. Right? So completely using the array alone, within the array, I can look up the children of a node, and by inverting this operation, if I look at j minus 1 by 2 and take the floor of that, okay, then I will come backwards, right? So if the child is 2i plus 1, 2i plus 2, then the parent is j minus 1 by 2, and then it might be fractional, so take the integer part. So floor means take the integer part of j minus 1 by 2, right? So this is not j minus half, okay? So read it as j minus 1 the whole by 2, right? So for example, for 12, j minus 1 is 11, okay? 11 by 2 is 5 and a half, floor of that is 5, so the parent of 12 is 5. Okay? So you can check that this is formed. So therefore, I can now do all my heap manipulation within an array, which is very convenient. I just have to write an array, and then whenever I do these operations which involve walking up or down the heap, I just use this 2i plus 1, 2i plus 2 formula, or I use this floor of j minus 1 by 2 formula. So how do we start this whole process off? How do we build a heap from a given set of values? Right? So a very naive strategy would work as follows. I am given a set of values, n values by x1 to xn. So I start with an empty heap, right? And then I insert x1. So I have a heap of size 1. Then I insert x2. So now I have a heap of size 2 and so on. So I do n inserts, right? And each insert takes log n time at most. Actually, it will take less time. It will take log I time if I have inserted I items so far. But let's take log n as an upper bound, right? So overall, if I insert these n elements, I will build the heap also in n log n time. Now, in fact, it turns out that there is a better way to do this. Okay? So if I look at any array, I can think of this as a heap, right? I can just imagine that it is ordered, because every array has a heap interpretation. I can imagine that this is how the array looks if I think of it as a heap. Of course, it doesn't satisfy the heap property, but this is how it would look if I arrange it as a heap. Now in this, anything which is at the leaf level doesn't need to be checked because it has no children. All leaves trivially satisfy the heap property. Right? So I need to start fixing things only at the previous level, so I walk backwards. So I come here, right, and at x3 I fix the heap property with respect to its children. Then at x2 I fix the property with respect to its children. In the process, something will move up and down, but only one level. Then I will come to x1 and I will fix its problem. Now this might involve two levels. Right? So for each level k minus 1, k minus 2, so leaves are at level k. At level k minus 1, k minus 2 on up to the root, we fix the heap property. So as we go up, fixing the heap property means walking down like we did for delete max, walking down to the leaf. Okay? So each level we go up, the length of this path increases by 1. But because the levels double as we go down, they halve as we go up. So the number of nodes for which we have to check this extra length path goes down by a factor of 2. Okay? So now if you do the analysis, which we are not going to do exactly, okay, it turns out that in this process, the number of updates you need to make a heap is actually only order n. Right? So if we use this bottom-up heapification, then it will be an order n procedure. So just to get a better picture of what's going on, so let's assume that we had 15 elements in our list, right, and we actually drew it out like this. And the claim is that these n by 2 nodes, okay, which is roughly half, it's actually 8 out of 15, already satisfy the heap property, so there's nothing to be done. So then I go one level up and I fix these, right? And when I fix these, I have to do it for 4 nodes, and each of them, the repair will involve one swap at most, or no swaps. Right? Worst case, it will all be one swap. Okay? Then I will go up one level, and now for each of these nodes, I will have to possibly go down 2 paths of length 2. Right? So each of them will involve a height 2 repair, that is 2 steps of thing, but then now from 4 nodes, I have gone to 2 nodes. Right? So there are only half as many nodes which require only 1 step more. And then finally, when I go to the root, I might have to do a kind of fix which involves swapping down to the last leaf, so 3 swaps. But there's only one node which does this. Okay? So therefore, since there's this trade-off that the number of nodes to be fixed is halving, and the length is only increasing by 1, it turns out that this whole operation takes only order n time. Okay. So to summarize, what we have seen is that heaps implement priority queues using special balanced trees. In these trees, both insert and delete max are logarithmic. We can use this bottom-up heapify to actually build a heap in order n time. And what is most useful is that this heap can actually be manipulated very simply as an array. Now, one thing which we can do is to invert the heap condition. So we can say that whenever we see V1, V2 and V3, we want V1 to be smaller than both V2 and V3. Right? So this is what is called a min heap. What we have been doing so far is a max heap. So sometimes we want to keep track of the smallest priority and remove the smallest priority item. Okay, just think of how, for example, you rank people in an exam, right? So if somebody in a competitive exam, the smaller the rank, the higher the priority. So if you have rank 1, then you have highest priority. So in some situations, it is natural to think of smaller numbers as higher priority. So you don't have to do anything very much. You just have to change the heap rule to be minimum. Okay, so that each node is smaller than its 2 children, and then everything will work exactly as we have done so far. Okay, so you have 2 types of heaps. You have max heaps and you have min heaps. And all that differs in max heaps and min heaps is the heap condition on the nodes, and the correspondingly whether the operation you implement is delete min or delete max. To complete our discussion of heaps, we will see how to use heaps in Dijkstra's algorithm, and also how to use heaps for a different type of sorting. Okay, so remember that heaps are a tree implementation of priority queues in which insert and delete are both of complexity log n. You can build a heap bottom up in order n time, and you can represent it as a tree, and so you can manipulate it in an you can represent the tree in an array, so you can manipulate it very easily. So let's go back to Dijkstra's algorithm. So in Dijkstra's algorithm, we start with the initial vertex and we keep burning these vertices, right? So we keep visiting vertices according to their distance. So initially we set the distance to be infinity for everything, right? And we use the starting point as setting the distance to the start vertex as 0. And then we find the smallest unvisited vertex, set it to be visited, and recompute the distance of each of its neighbors, right? So the bottlenecks were really at this part of the loop. So the bottlenecks are first to find the j with a minimum distance, right? So the naive implementation would take us order n time because we would have to scan all the unvisited vertices which are not in any particular order of distance, and among them find the minimum, right? So what seems obvious from what we have discussed so far is that we should maintain distance as a heap, okay? And use delete max, or actually delete min in this case, because we would want a min heap, okay? So we would use delete min, but then we also have to recompute the distance. So recomputing the distance means examining every neighbor k of j. So to make sure that we can look up the neighbors efficiently, we can use adjacency lists so that we don't waste time scanning an entire row of an adjacency matrix. But the bottleneck here is that we need to update the distance. That is, we need to get into the heap and change values. Okay, so we need to update heap values. Now we haven't really seen how to update heap values. We have only seen insert and delete min or delete max. Okay. So how does update work? Right. So supposing we want to change this value from 12 to 44. Right. Now if we increase this value, then with respect to its children, it cannot get any smaller. Right? So if 12 is bigger than 10 and 11, any larger value will also be bigger than 10 and 11. So if we make it 44, we don't have to look down. But because we made it bigger, it can become bigger than its parent, and in fact it does happen. So if we replace 12 by 44, then we find that there is a heap violation above. So now we treat this exactly like we did insert. We look at the parent and swap. Okay, so we fix this violation upwards. Okay, so now we look and we have got 44 here, and now we have to check whether it violates anything with its parent, okay, and it does, so we exchange that, and finally when it stops, when either there are no more violations or when we reach the root, in which case we can't go up any further, right? So increasing a value, you fix violations upwards, because in increasing a value you cannot become smaller than your children, but you can become bigger than your parent. The other type of change is to decrease a value. So supposing I take this 33 and I make it 9. Now again, by the same logic, because 33 was smaller than 44, 9 will also be smaller than 44. Any value smaller than 33 cannot create a violation up, so I must look down. right? So if I bring it down to 9, then of course there's a problem between 33 and 24, right? So if this is my new value, I have to check with its two children and take the biggest one up. In this case it's 24, right? So now having come here, I need to now check its two children and take the biggest one up, in which case it's 11, and so this is how it works, right? So when I update values and decrease a value, I have to fix violations downwards, because reducing a value cannot make it work bigger than its parent, but it can make it smaller than one of its two children. So if you look at Dijkstra's algorithm, the way it works is we take a vertex j and say update its distance, right? So we have to update the distance of some vertex j which is somewhere in the heap, right? So what our previous example showed us is if we put our finger on the node in the heap and change its value, we know how to adjust the heap. But how do we find where j is in the heap, right? So where is j located? So we need this extra information to be kept separately, right? So we will keep two new arrays, okay, pointing from the nodes which are 1 to n to the heap which is 0 to n minus 1, and vice versa from the heap which is 0 to n to the nodes, okay. So here in this picture, right, these two things are drawn in different colors. So the red labels against a node indicate the vertex. So 44 represents the distance of vertex 8, okay. And to indicate that, we have an array saying that in node to heap saying that the node 8 in the graph is vertex 0 in the heap. Similarly, if I look at this, it says that this vertex is 3. So the vertex 3 in my graph is node 6, okay, in my heap. Conversely, if I am in the heap and if I am at node 4, which is represented in blue, then which vertex does this correspond to? Okay, so it says that the node 4 in the heap corresponds to vertex 5. So from the heap, given the index of a node in the heap, which node in the graph does it correspond to? Okay, so we have these two extra things which we set up, and we have to update this when we do our swaps or inserts, right? So now, for instance, supposing we have this previous thing and we want to make this 33 into 9. Okay, so our goal is to reduce 33 to 9, which we did in the previous step. Now let's do this. So now when I do this, I need to go down to its two children in the heap and recognize that this 24 must change. Now since 24 must change, I must know also how to update it. So 24 is node 3 in the heap. So node 3 is vertex 2. Okay, so I have to go to vertex 2 here. So I need to update these entries. So I need to update 6 and 1, okay, and 3 and 2. Okay. So therefore, when I exchange the 9 and the 24, I must also exchange the 6 and the 2. I must say that now vertex 2 in my graph is now at node 1 in the tree, and vertex 6 in my graph is now at node 3 in the tree. Conversely, node 1 in the tree points to vertex 6, node 3 in the tree points to vertex 2, node 3 points to vertex 6, right? So after this update, basically these two values have got exchanged from what they were previously. Okay? So in addition to swapping at this level, I also have to recognize that this swap happened. Okay? Now I do one more swap because 9 and 11 have to swap. So now I will swap the entries for 3, 6 and 8, 9, and similarly here 6, 3 and 9, 8, right? So the entries correspond to vertex 6 and vertex 9 and node 3 and node 8, right? So vertex 6, vertex 9, node 3 and node 8, these have to be swapped. Right? So by keeping these two extra arrays, right, I can do these updates very easily because I have a way of going backwards and forwards between the heap index and the node index. And unless I do this, I cannot really use this for Dijkstra's algorithm, because Dijkstra's algorithm will ask us to update a value in the heap, but I need to know which value in the heap I need to update. The update can be done using this upward or downward manipulation, exactly like insert or delete max. But the real problem is identifying where the update starts. So as we saw before, now we can use this heap with this update operation and find the minimum time vertex in log n time. Okay? And because we have adjacency lists, right, over all the loops, updating the burn times takes log n time per edge, and they are totally order m edges. So overall we get n log n for updating, for finding the minimum n times, and m log n for updating the minimum m times, so n plus m log n. Okay? You can use a similar strategy for Prim's algorithm. Okay? In Prim's algorithm, the only distance, the notion of distance is not the same, we don't accumulate the distance, we look at the cost of the actual edge. Okay, but still we need to track the minimum cost edge connecting a node to a tree, to the current tree, and then we need to update these things after we add this edge to the tree. Right? So exactly the same idea of using a min heap with updates we'll use for getting Prim's algorithm also down to the same complexity as Dijkstra's algorithm. So before we leave heaps, let us see how to use heaps to sort. Okay? So we want to sort a list of values. So what we can do is we can first build a heap. Right? So we now start with some arbitrary sequence of values x1 to xn, and then we build a heap, and will possibly get reordered in some way as xi1, xi2 to xin. But this is not in sort order, this is in heap order. That is, we know that the maximum is at the left and so on. Now I do a delete max and I pull this guy out. Right? So I know that this is the maximum. Then after this something will come to the front. Okay? At the next point that will come out, and then I'll get the second max, and so on. Right? So if I do delete max n times, clearly at each point I get the next maximum. So I'm extracting elements from this heap in descending order, and so I get a sorted output. I can reverse it, I can keep it in ascending order, it doesn't matter, but I'm just extracting the elements in a particular order, and so this gives me a trivial sorting algorithm. Now each extraction takes log n time because it's a delete max, right? Or a delete min, depending on what type of heap you're using. So you do n such extractions, so in n log n time you can get the elements out in sorted order, and to put them in you took only order n time, so overall it's order n log n time. There is a small subtle thing that you can ask about this. The question is, where do these values go? Right? So initially in the first iteration, if I have my heap looking like this, okay, this is my maximum. So it looks like I have to put it in a new list. Okay? But what happens after this step is that this value gets inserted here, and then it percolates down via the heapify fix operation. Right? So when I delete the value at the root, I take the last leaf, put its value in the root, and then I push it down so that all the heap properties are there. And after this, now my heap only looks like this because this value is gone. Okay, so my heap ends with n minus 1. So I have a place in my array which is not being used anymore for the next delete max, because the next delete max involves only n minus 1 operations. So therefore I can in fact at this point go and put this value back into the heap at this position and be sure it's not touched. Right? So now what will happen is I'll have the max coming here, then I'll have the next second max coming here, and so on. So if I keep doing delete max, I will be propagating from the right the value in descending order, and therefore finally my heap will actually end up being resorted in ascending order. Right? So this gives me an in place order n log n sort. Right? By just making sure that when I delete a value, instead of throwing it away or putting it into a new list, I just put it into the place that was vacated right now by shrinking the heap by one value. And then I automatically get an output in sorted order. Right? So heaps can be used to do a very different kind of order n log n sort in place. Let's go back and look at divide and conquer again. So recall the divide and conquer paradigm consists of breaking up a problem into disjoint subproblems. Then we solve each of these subproblems separately, and then we combine them efficiently to form a solution to the original problem. So we have seen two examples of divide and conquer. Merge sort is a classic example of divide and conquer, where we divide the list to be sorted or the array to be sorted into two equal parts. We sort these two parts separately, and then we efficiently merge them into a sorted list. Quicksort has a different strategy. What it tries to do is avoid the merging step. So you rearrange the original list so that you have a lower and upper partition with respect to a pivot. Having rearranged them, you can sort the lower half and the upper half independently. And now because they are already rearranged, you don't have to merge them. So basically there is a cost involved with setting up the subproblems and a cost involved with combining the subproblems. And if this setup cost and combination cost is efficient, then the overall solution gives you something much better than a direct approach could. So let's look at the following situation. Very often when you go to an online store, you find a recommendation. For example, it would say that customers like you were interested in books like these, or customers who bought this phone also look for this pair of headphones. Right? So these services are recommended to you based on your profile. The online service maintains some profile information about what you like and what you don't like. It compares what you like and don't like with others and identifies a similar category of people. And then it looks for products or services that that category has opted for, which you have not, and then recommends these to you. Right? So a fundamental step in such a recommendation system is that of comparing profiles. Right? How does one person's likes, how do one person's likes and dislikes compare to those of others? So one instance of this is when you have preferences over things like movies or books. So suppose over a sequence of time you have gone to some website and entered your preferences about movies that you have watched. So say there are 5 movies, let us just call them A, B, C, D and E, which both you and somebody else have ranked on this website. So you, in general, 2 individuals will come up with different rankings. So perhaps you ranked D first and E last, and your friend ranked B first and E last. So you both agreed that E was the worst, but you disagree on whether B or D was better. In fact, your friend thinks D was so bad that it was actually only next to E from the bottom, right? So D, which was your first, has become your friend's fourth. So now what we can do is we can take 2 such sets of rankings and ask how similar or dissimilar they are. So one way of measuring this is to compare how you rank pairs of movies. Right? So for each pair of movies, you can compare whether you rank one better than the other and your friend also does or you don't. So here, for instance, if you look at B and C, okay, then this is ranked in a similar way by you and your friend. Okay? On the other hand, if you look at D and B, right, then in one case you rank D above B and your friend ranks B above D. Right? So we don't particularly care how far apart they are, how many other things there are. We're just saying, given choice of 2 things, which do you prefer, which does your friend prefer, and combine these choices across all the choices available in the given list. Right? So what we are trying to do is measure the dissimilarity in terms of what we can call inversions. Right? How many pairs of movies are ranked in an opposite way between you and your friend? So if you and your friend rank every pair of movies in the same order, then your total order of preferences must be the same. Right? So if there are 0 inversions, then you are exactly similar in your taste to your friend and the rankings are identical. On the other hand, if you have n movies, right, then you can do n choose 2 pairs, right? So the number of different pairs of movies are n choose 2, which is n into n minus 1 by 2. Right? So if every possible movie you disagree with your friend, then the number of inversions will be n into n minus 1 by 2, which is of order n square. Right? So you can use now this as a measure, how many pairs are out of order, as a measure of how similar or dissimilar 2 sets of rankings are, and this could be used, for instance, in this recommendation system to decide which customers to compare when making a recommendation. So you only want to pick customers who are close to the one whose recommendation is being made. There's no point in recommending something that a person is not going to like because you're comparing it with somebody who has very different tastes. So we can formulate this in another way. So now we take our ranking and we assume that that is the given order. Right? So we picked a certain order for the movies and we call that the basic ranking 1, 2, 3, 4 up to n. Now our friend's ranking would rank what we called 1 as maybe 5, what we called 2 as maybe 3 and so on. Right? So everything that we rank with a rank I will be ranked by a different rank j by our friend. And of course, every rank will appear there somewhere or the other. So the friend's ranking will be a permutation of 1 to n. And what you're asking is, if I rank I before j, that is if I is a smaller number than j, does the friend rank j before I? Any such thing would be an inversion, right? So an inversion would be a pair I comma j in my list where I is smaller than j. So in my list, I is ahead of j. But in my friend's list, j appears before I in that permutation. Okay, so let's look at this a little more concretely. So supposing this was our original example, so there were 5 movies A, B, C, D, E, and I ranked them or you ranked them as D, B, C, A, E, then I would say that D is 1, B is 2, C is 3, A is 4 and E is 5. Okay, so this is my original list 1 to 5. Now, because I have this correspondence between the movies and the things and the rankings, then I know that B, for instance, is 2, right? So B is 2, A is 4, C is 3, D is 1, and E is 5, right? So from this list of preferences, I can rewrite it as a reordering of my ranking. And now we are asking whether there are pairs like this, 2 and 1, right? So 2 appears before 1 in my friends list. It appears after 1 obviously in the original list. So this is an inversion. So 2, 1 is an inversion. Likewise, 4, 1 is an inversion. So is 3, 1. Okay, so we have these 3 inversions, whether we can write them as 1, 2 or 2, 1, 1, 3 or 3, 1, because these are pairs. Okay, so the order is not important. These pairs of movies are ranked oppositely by you and your friend. And the final inversion in this particular example is 3 and 4. Right? So 3 and 4 appear in opposite order. You can check that for every other pair, for example 4, 5 or 2, 3 or 2, 4, right? The order is preserved. So there are 4 inversions in this particular list between your ranking and your friend's ranking. And our goal is to count this number of inversions given 2 permutations. So another way of thinking about this, though it will not materially affect how we compute it, is to draw this kind of a graph. So you take the rankings to start with as the correct order on top. So you have one set of vertices 1 to 5, and then you have a permutation of the vertices 1 to 5 listed in the order of your friend's ranking. And then you combine 1 to 1, 2 to 2 and so on, so that you build up this graph which has, if you have 5 on top and 5 in the bottom, you have 5 edges. If you have n and n, you have n edges. Now in this graph, every time a line crosses, this indicates a mismatch, right? So 2 has gone ahead of 1, likewise 4 has gone ahead of 3 and so on, right? So there are 4 crossings between these lines, and that really corresponds to 4 inversions in this example. So now there is a very simple brute force way to check, because we know that every inversion is a pair ij such that j appears before I in my friends list. So we can just check that, right? So we can just check for every I and every j which is different from I, whether I and j is an inversion, and this will give us a brute force order n squared algorithm. Okay. So this actually enumerates all the inversions. It checks every possible pair, and if it is an inversion, it says yes. If it's not an inversion, it says no, and then you count how many inversions you saw. And we saw that we could actually, in the worst case, have a complete set n into n minus 1 by 2 inversions. So this will exhaustively enumerate every inversion and check it for yes or no. So our goal is to give a more efficient algorithm. So we will move to this divide and conquer paradigm. So suppose your friend's permutation, see, our permutation is always 1 to n, so we can just assume it is given. So what is really interesting is our friend's permutation, right? So the friend's permutation is some order of 1 to n jumbled up. Let us call it I1 to In. So now we will do something similar to merge sort. So we will take this list I1 to In and divide it into 2 parts, right? So we have I1 to In by 2, which is the left, and In by 2 plus 1 to n, which is the right. So divide and conquer is a very simple-minded strategy. You can only do one thing. You can solve this, and then you can combine. Right? So this is the basic paradigm. So you have to divide, solve the divided parts, and combine. Right? So we will recursively assume that we can count the inversions in left and right. Now what is left to count are those inversions which cross the boundary. So is there a J I pair that looks like this? Right? This would not be counted when I count only the left, because I is not in the left. It will not be counted only in the right because J is not in the right. So there will be an inversion where I is less than J as numbers, but J appears in the left, I appears in the right. So this has to be done after we have solved the recursive thing. So this is basically the combination step. How many elements in the right are bigger than elements in the left? Right? Anything on the left, if it is smaller than something on the right, then it's not an inversion, because it's already in the correct order in the overall list. But if something on the right is bigger than something on the left, then that's an inversion. We have to count all such pairs. So in order to solve this, we will make our recursive procedure a little stronger than just counting. Right? So we will assume that not only do we count in the 2 halves, we sort them while we are counting. Right? So what happens is, now we divide our problem into 2 parts, okay, and then we come back. So this is my L and this is my R. I have now sorted L, sorted R, and I have a count also. I have a count L and a count R. Right? Now the fact that these are sorted means that I can do some kind of merging. So I can use a version of merge. So we will describe a version of merging which allows us to count. So this gives us another count. And then we'll have three counts, the left count, the right count, and the count returned by merge. So what we want to do while merging is to actually check how many elements on the right are bigger than how many elements on the left. So how do we do this? So what is the principle of merge and count? So remember that an inversion across L and R consists of an element in R. Okay, so we have an element in R and an element in L. Okay, such that this number is smaller than this number. Right, so we have some I here and some j here, such that I is smaller than j. Right, so what will happen in our merge procedure is at some point. Right, so we are merging, so we pick the smaller of these two and pull it out. Okay, so anytime now if I pull out an element from here, okay, that means that at this current point I have merged up to this and up to this. Okay, so there are two pointers in my list, left and right, the sorted list, up to which the merge has proceeded so far. Now at this point I choose the right hand side element because it is smaller. So how much, if it is smaller, okay, then it is smaller than everything which I have not yet looked at. That's why, because it is smaller than the first element I am looking at in L, is therefore smaller than everything else in L, because everything else in L is sorted with respect to this. Right? So therefore this entire segment which is left in L corresponds to elements which are smaller than the current element I am pulling out from R. In other words, this element in R contributes as many inversions as there are elements in L at the point when it is extracted in the merge process. Right? So whenever I add an element from R to the output, it is inverted with respect to all the elements currently in L. So I should add the current size of L to the number of inversions. Right? So this gives us our merge and count. While we are merging, every time we pull from the left, there is no inversion. Every time we pull from the right, we see how many elements are still remaining in the left, and that many items need to be added to our inversion count. So here is the merge procedure for merge and count, which is very similar to the merge procedure in the basic merge sort. So we have two lists A and B to be merged, both are sorted. Okay, and A has m elements and B has n elements, and we want to produce an output list C which has m plus n elements. So we begin with assigning a pointer to tell us how far we have gone in each list, which is set to 0. Right? And now we have to keep track of the number of inversions, so we keep a variable called count which is initialized to 0, the total number of inversions which have been seen so far. So long as something is there to move into C, we move something. So the two cases, the first case is to move from A. So either B is empty, j is equal to n, or the element at the head of A, ai is smaller than or equal to bj, in which case we do the usual thing, we copy the ith element of A into ck and then we increment both I and k. The other case is when either A is empty, I is equal to m, or bj has a smaller value. In this case, we have possibly an inversion. Right? So how many inversions do we have? We have exactly m minus I inversions. We have as many inversions as, so this is I, we have as many inversions as our elements currently in A, which is m minus I. Now notice that in the specific case where we are copying from B because A is empty, we have I equal to m. So this would actually be 0. Right? So there should not be an inversion if we are just duplicating B and C because A is exhausted. But that's also taken care of by m minus I being 0. So although we are updating the count, we are actually not adding anything to it. So only when we are doing a non-trivial merge, that is when we are moving something from B when A is still not empty, do we increment the count. If we are moving because we have run out of elements in A, count will remain the same. So at the end of this merge procedure, we return the number of inversions we saw plus the merged list. So now we incorporate our merge procedure into the merge sort with counting as follows. So as usual, we will sort in general an array from some left index to some right index because we will sort different segments at different times. So if the current segment to be sorted has length 1, then there is nothing to be done. We just set up a new, the sorted segment is just the value that we see, and there is no inversion because there is only one value. On the other hand, if it is bigger than 1, then we compute the midpoint and we do these two recursive calls. Each of them will return the count on the left and the right respectively. Then we call our merge procedure and get a count from the merge section. So then our total number of inversions is the count from the left, the count from the right, and the count from the merge together. And the new array is the one returned by merge. Right? So this is a very simple extension of merge sort, which allows us to count inversions, which is useful for our recommendation system. So the analysis, of course, given that the structure is so similar to merge sort, the analysis is similar. We have this recurrence for the time taken on n steps. So t of 1 is 1 and t of n is 2 times tn by 2 plus n, exactly as for merge sort, because it only takes us linear time to merge sort with count. Right? So when we merge with count, it takes the same amount of time as merging without counting. So we solve this and we get n log n. Now one important thing to note is when we did our brute force calculation, right, we looked at every possible pair and decided whether or not it was an inversion. So we actually explicitly counted the inversions to get the answer. Now here we are doing it in n log n, which is potentially much smaller than the number of inversions altogether. So we are actually counting the number of inversions or estimating or actually calculating how many inversions are there without actually counting them manually one by one, because there could be n squared inversions, but even if there are n squared inversions, we could find that out in n log n time. Right? So we are not manually counting every step, rather we are getting this through our recursive calculation. We now look at another divide and conquer algorithm. This is a geometric problem. Given a set of points, we would like to compute the closest pair of points among them. So recall that at the beginning of this set of lectures, to motivate the need for more efficient algorithms, we considered the example of a video game where there are several objects on the screen and you might want to find at any given point the closest pair of objects among them. So for this, again, a naive algorithm would be to explicitly compute the distance between every pair of these n objects, which would be an order n squared algorithm. So what we are going to see is that we can actually use divide and conquer and produce an order n log n algorithm for this problem. So formally we are looking at points in 2 dimensions. So each point is given by an xy coordinate xp, yp. And we are using the usual Euclidean notion of distance, that is the distance given by Pythagoras' formula, which is that the distance between p1 and p2 is the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. So we'll just assume that there is this distance formula which we can use whenever we want to compute the distance between a pair of points. So our target is given a set of n points, p1 to pn, to find the closest pair among them. And it will be convenient for the analysis of the algorithm that we are going to suggest that no 2 points in this set have the same x or y coordinate, right? So every x coordinate among these n x coordinates is different. Every y coordinate among these n coordinates is different. Now it can be extended, the algorithm we are going to show can be extended to deal with the case where this assumption is not true, but it will then unnecessarily complicate the understanding of the algorithm. So let's just assume that we are solving this special case of the problem where every point is at a different x coordinate and a different y coordinate from every other point. So as we have seen, a brute force solution would be to try every pair, compute d of pi pj, and then report the minimum among these distances. So this would be an order n squared algorithm. So let us see first the same problem if we had only one-dimensional points, right? If we have one-dimensional points, then all these points lie along a line which we can assume is the x-axis. So we have a bunch of points, right? And we want to find the closest one. So what we can do is we can first sort them, okay, so that we have the points in increasing order of x coordinate, right? And then it's easy to see that the distances that we need are the distances between 2 adjacent points, because if I look at a point, the nearest point is either the one on its left or the one on its right. So I just need to scan this x2 minus x1 distance, then x3 minus x2. So I just need to scan these n minus 1 distances and then keep track of the smallest gap between these 2 points, and that would give me the smallest distance among the overall pair of overall n points, right? So here the algorithm is n log n because it takes n log n times to sort the points in x order. After that, finding the minimum is actually very easy. So in one dimension, this problem is very easy to solve. The challenge is to solve it in 2 dimensions. Right? So in 2 dimensions, if we are going to use divide and conquer, we need a way of separating the points into 2 groups of roughly equal size or hopefully exactly equal size. So a natural way, since this is a geometric problem, is to separate them based on their position. So if this is my overall set of points, then it's natural to try and draw some kind of a line and say that half the points are here and half the points are there, right? So we will do it using a vertical line, right? So we will split this set not by some arbitrary line like this, but rather we will try and split it by a vertical line, right? So somewhere which may not be halfway across because the points may be scattered in an uneven way, we will split it so that there are exactly the same number of points to the left of the line and to the right of the line. Right? So now because of the divide and conquer thing, what we will do is we will compute the smallest distance among the points to the left. Separately, we will compute the smallest distance, the points on the right. But this does not tell us anything about distances between points on the left and points on the right. And there could very well be points very close to each other across the boundary, right? So I could have had 4 points here, 4 points there, and I could have had a pair of points which spans this black line, which are actually closer together than any 2 points on the left or 2 points on the right. So we need to compute the closest pairs across the separating line, and this is the challenge. Right? So let's look a little closer at how we do this. So we will make a further step before we do this thing recursively. Given our points P, we will compute points, the set of points, we will compute 2 sorted orders of it. Okay? So we will first scan these points by x coordinate from left to right, and we will list it in this order and call it Px. Then we will scan the list P from, so we will sort it on the y coordinate and call this Py. So from P we will produce 2 lists, okay? One sorted by x and one sorted by y. Right? So we will assume that we have done this. Of course we can do this, we know, in order log n log n time right at the beginning. Right? Now the next step is to do this recursive call. And so when we do the recursive call, because we have Px sorted by x coordinate, we know that the line that we need to draw is the one that separates Px into 2 equal parts. So we need to go to the midpoint of Px and draw a line at the x coordinate separating the midpoint from the next point. So the position of this line is fixed once we know Px. Fixed meaning we know between which 2 points. Remember we assumed that no 2 points are the same x coordinate, no 2 points are the same y coordinate. So I just have to look for the median value or the value of the middle of x, right, and draw a line there. Now I have separated out into 2 equal parts by assumption because I have done this at the midpoint of Px. So I have 2 sets Q and R, but in order to continue this recursion I need to assume that Q is sorted in both x and y and so is R, right? So I need to assume that I have some efficient way of extracting for each of these sub-problems a similar ordering of the points sorted by x, sorted by y. So I need to efficiently compute Qx and Qy, Rx and Ry. Qx and Qy is easy because this whole thing earlier was Px, right? And then we split this thing midpoint. So everything to the left of the midpoint is Qx and everything to the right of the midpoint is Rx. Right? So in one scan of Px, I go up to halfway and I put everything in Qx, and then from the halfway point I put everything in Rx and I'm done. Right? Now what about y? Now y, the problem is as I'm going up, right, these 2 points are in Qy, then this point goes into Ry because in the overall scheme of things in Py, these are all listed globally by y coordinate. Right? So I would have to move this to R, then I would have to put this back into, so the next one again possibly is R depending on how you do this, then the next one is in Q and so on, right? So as I'm going up, some points go in P and some points go in Qy and some go in Ry. Now how do I determine that without going over this too many times? Okay? So the key is that having done this split of x, we know this dividing line, right? So we know which x coordinate separates Q from P, from an R. So as we go through Py, right, we look at each point, okay, and if the x coordinate is less than this midpoint, so let us call this xq. If it is less than xq, then we push it into Qy. If it is x is greater than xq, then we push it into Ry. And because it was originally sorted, we are building up Qy and Ry also in sorted order. So in one scan of Py, we get Qy and Ry, right? So in linear time, we can take the given sorted lists Px and Qy, Px and Py, and separate it out into sorted list Qx, Qy for the left half and Rx, Ry for the right half. Okay. So now when we call our algorithm with closest pair Px, Py, it will split recursively into closest pair Qx, Qy and Rx, Ry for the left and right half. Okay. So we can assume as usual that we will solve these recursively, we will get the closest distance there. Now we have to worry about how to combine them, how to take care of these points whose distance spans the interval, the line separating the two halves. So if we solve this problem on the left, right, among all the points in Q, I will identify some pair of points as being the nearest pair with a distance dq. Okay. And now similarly, if I do solve the problem on the right, I will identify some pair of points as being the minimum on the right with distance dr. So now we are interested in the smaller of these two, because the smaller of these two is a candidate for the overall minimum distance. So now we are looking at points which could be within at dq or smaller than dq across this boundary. Okay. So let d be the minimum of dq and dr. So it is the smaller of these two. So in this particular example, d is dq. Okay. Now the claim is that if we look at this zone here, okay, which is plus minus d distance away from the separating line, then if I have some point outside this, and if I want to look at any point across on the other side, this distance from here to there is d plus some distance on either side. Therefore, it is more than d. So it's more than the smaller of dq and dr. So it cannot be a candidate for our overall smallest distance. Right? So these kind of things are useless. There is no point in looking for any line which is any pair whose one endpoint is outside the zone. Because if it's outside the zone, then it can only be at least d plus something away from something on the other side of the line. So it is enough to look at points inside the zone on both sides. Right? So we only need to consider points across the separator which lie within this plus minus t zone. Right? Any pair outside this cannot be the closest pair overall. So let's take a closer look. So this is my plus minus d zone. Right? So this is minus d, this is plus d. Right? Now what we are going to do is we are going to further break it up into these squares of size d by 2. Right? So I have d by 2 plus d by 2. So this whole thing is width d, and I am going to construct all these squares. Okay? So now the claim is that inside such a box, right, I can have at most one point. I cannot have 2 points. Why? Because the furthest separation within a box is across a diagonal. Right? The furthest that 2 points can be in the box is at 2 endpoints of the diagonal. But the diagonal of the square of size d by 2 is square root of d by 2. Okay, so this is some 0.047 d. So this is less than d, strictly less than d. But notice that this square is completely on one side of the red line. It's either on the left or the right. And both on the left and the right, we know that the minimum separation is d. There is no point on one side of the line, there are no 2 points closer than d, because the d is the minimum of dq and dr. Right? So therefore, in each of these boxes, we can have at most 1 point. Okay? And now we start looking at any point. So look at a point here in this box. Now the claim is that if I have to be within distance d, right, then how far away can I be? Well, if you think about it, the furthest you can be, or the furthest box you can hope to go to is that box. Right? So you can be a little more careful about this, but it certainly cannot be any further than that box. So if you have to go from this box, if we have to go more than this distance away, then it will be more than d away. Right? So the claim is that any point within this distance d must lie within the next 4 by 4 segment. So we have to compare each point only against 15. Now of course we will compare it in one scan from bottom to top. So this would have, the points below this, they would have been compared when we considered those before. Right? So we will do this scan in this order, as we will see in a minute. Right? So therefore we only need to consider this point against points in this 16 squares around it. So that's a fixed number, independent of how many points they actually are. So formally what we will do is we have this, on this side we have Qy which is sorted, on this side we have Ry which is sorted, but remember they are both sorted. So we will do a kind of merge, right? So we will go through Qy and Ry, we will pick the next one in sorted Y order between Qy and Ry, If the x coordinate is, remember this is some xq, our original separating point, plus d or minus d. If the x coordinate of the point that we find is between xq plus d and xq minus d, then we will add it to a list sy. Right? So sy will now be a sorted list of points within this band from bottom to top, extracted from qy and ry in linear time. Now within this list, these next 15 boxes, these boxes will now be all ordered, right? So if I just scan them, then I will find that all these, so there will be possibly 4 points which come from these 4 boxes, 4 from these 4 boxes, and so on. So I can definitely find the next 15 points in this list and I compare only with those. So this is a linear scan, right? So in other words, we have this following algorithm. So we start with by assuming that we have set up our problem so that P has been split into two copies, Px and Py, sorted by x, sorted by y. Now if we have less than 3 points or less, then we just do it by brute force, compute the closest pair and return the answer. So the answer consists of the distance and a pair, the points which are at that distance. If it is more than 3, then we do this recursive thing. So we, from Px, Py, as we said, we construct Qx, Qy and Rx, Ry, and this we saw we can do in linear time. Okay. Then we will recursively solve the solution, solve the problem for Q and R, and we will get these two distances, dx and dr. From this, we will take our d to be the minimum of dq and dr. Right? So using this, we will set up this sy, the list of all points inside that zone, and then we will scan that list to find within that zone which are the points which are at the closest distance, ds. Now if ds is more than dq, the minimum of dq and dr, then s doesn't contribute anything, but if it is less, it gives us the correct answer. So we will return either the dq, the answer produced from the left, or the answer produced from the right, or the answer produced from our in-between zone, depending on which of these distances is the smallest. Right? So this is the basic algorithm. You have to do a little bit more work to actually code it correctly, but this gives the overall structure of the algorithm. So we have a non-recursive part, which is to first compute the initial sorted list px and py. This takes order on n log n time, of course, because sorting takes n log n time. Then having set up this recursive thing, the overall recursive problem divides n points into two sets of n by 2. So we have our familiar thing which says t of n is 2 times t of n by 2. And then because all the setting up time, okay, and all this combining time is linear, we have exactly the recurrence for merge sort. So therefore the recursive part also gives us order n log n, right? So we have a initial sorting phase which is n log n. We have a recursive part which is n log n, and therefore overall this algorithm is n log n. So we now look at another data structure called a search tree. So to motivate search trees, let's consider the following example. So supposing you are an air traffic controller and you're controlling access to a single runway where flights have to land and take off. So the air traffic control tower receives requests from the aircraft about their expected arrival and departure times. And these requests come at random times. So it's not that they come in order of the time of the actual event. So we might first get a request for a landing in Chennai at 16:23, and later on we might get a request for a takeoff at 16:12, which is actually earlier. And then we might get another arrival information at 16:55, and then another earlier arrival information at 16:18. And the strategy that the control tower is supposed to follow is to give priority to the flights with the earliest usage time. Right? So this is a priority queue. Each request goes into the queue, but it has a priority depending on the expected time that it's going to take place. So we could give a min heap representation, and if we take these 6 requests in the order that they come and we insert them into the min heap, then we will get the min heap that we see on the right hand side. Right? And so in this, because 1612 happens to be the earliest event among these 6, it will automatically float up to the root, and so it will be available to us as the next event to process, and then maybe 2 minutes before that event happens, we can send a signal to the flight giving it clearance to take off. So suppose we have an extra requirement on this. Not only do we want to give priority to the earliest event to happen, but we also want to impose some minimum separation of planes to avoid any possibility of collisions on the runway. So we say that two planes accessing the runway must be a minimum of 3 minutes apart. Now in this example, we can see that the rule is violated by the two events at 1653 and 1655. So what happens is that we should, when we insert or we accept the request for 1655, assuming it came after 1653, at this point we should check that it is whether it is at least 3 minutes apart from all the current pending requests. If not, we should send a message to the pilot saying 1655 is not possible. You must move your takeoff or landing to 1656 or later. Now unfortunately, in the heap data structure there is no easy way to do this. So when 1655 is added to the heap, we have to scan it against all the elements in the heap in order to find out whether it is within 3 minutes of any of them. So this would be a linear scan. So all other operations, insert and delete on a heap, were logarithmic, but this, if we want to impose this constraint that no two elements in the heap are within 3 minutes of each other, then we would add an extra linear time cost to every insert, and this would then make a heap unviable for this kind of data. So one way to compute this kind of requirement is to be able to check the predecessor and the successor. In other words, given the list of values that we have, for any value, can we quickly compute what is the previous in terms of the nearest smaller value and the next successor, what's the nearest bigger value, right? So if we look at 1618 for example, then the next smaller value is here, so this is the predecessor, 1612, and the next bigger value is here, so this is the successor. Now this happens to be, it looks like there is some nice relationship within the heap in terms of the tree structure between predecessor and successor, but if we look at a different value, for example 1653, then we will find that the predecessor lies in a different branch of the tree and the successor lies in the same branch. Okay, so there is no direct relationship between the tree structure of the heap and the predecessor and the successor relation that we need. However, the important thing to note is if we could compute predecessor and successor, then we can solve this problem, because once we look at the successor or the predecessor and we find something which is within 3 minutes, then we can flag a warning and signal to that aircraft that that request is not tenable. So if we want to maintain this information, let's try and look at the different data structures we have seen so far. Okay, so we have unsorted arrays, sorted arrays, and min heaps. Okay, now in this particular structure, we are not going to look at directly a delete min or a delete max, but two separate operations, one which checks the minimum and maximum, okay, and one which deletes an element arbitrarily. So for min and max, as far as min and max go, okay, then it is clear that the best data structure is sorted array, because these values are at the extreme ends of the array. The worst is an unsorted array because they could be anywhere and both require linear time. And then depending on whether we have a min heap or the max heap, one of them is good and the other one is bad. So in a min heap, we can find the minimum with the root, the maximum could be anywhere. And likewise in a max heap, the maximum would be at the root, the minimum could be anywhere. So if we look at the next set of operations, this is insert and delete. Okay. Now here it turns out that an unsorted array is good for insert because we can just stick it in at the end. For delete, we have to go through the array and look for the value and remove it, so it will take linear time. In a sorted array, both will be slow because we have to either insert in the correct position like an insertion sort, or when we delete, we have to compress the array, which will take linear time. Now we know that in a min heap, insert is logarithmic. Okay. Delete is also logarithmic, even though this is not delete min. Okay. So this can be broken up as two steps. So update to the current minimum overall minus 1 and then delete min. Right? So you can take the current value that you want to delete, reset its value so that it becomes the minimum, in which case, as we saw, when you update to a smaller value, it will propagate up to the root. And then if you do a delete min, that value will disappear, and so you would have effectively in two steps of log n each, we would have deleted it, so overall it is log n. And now, as we just said, predecessor and successor, in a sorted list they are adjacent, so these are both constant operations. On the other hand, in an unsorted list, we have to look through the whole array. And we also said in a heap, we have to scan because there is no particular order in which the adjacent elements are stored in the heap. So what we are going to look at today are binary search trees. And in a binary search tree, we are going to argue that all of these operations are actually logarithmic, provided we maintain the binary search tree with a good structure. And also we will look at an operation called find, which searches for a value, and this will also be logarithmic. Right? So we will simultaneously be able to optimize all these 7 operations in a binary search tree. So a binary tree is just a tree with a root in which every node has either 1, 2 or 3 children. A heap was a very special kind of binary tree which we filled up top to bottom, left to right. But in general, a binary tree has no constraint, right? So we have values at each node, and we will assume that not only do we have a way to go from the parent to the child, but we also have a way to go from the child to the parent, right? So every node we are going to assume will have a link to its parent, left child and right child. Okay, of course these links may be missing, but if they are there, then they will be all 3. So we can point up the tree and to the 2 nodes below it on down the tree. Okay. So just in terms of terminology, the root is the topmost node, has no parent. The leaf is any node which has no children, and at any given point, if we look at a node, then it is the parent of its left child and its right child. So now we take a binary tree and we further impose a constraint on the values. So remember, like in a heap, we first had a structural condition that the tree is filled top to bottom, left to right, and then we said there is a heap property which says max heap or min heap, either a node is bigger than its 2 children or it is smaller than its 2 children. So there was a property on the structure and there was a property on the values and how they are arranged with respect to each other. So in a binary search tree, the binary tree could have an arbitrary structure, but the values are arranged in a specific way. So for each node with a value v, all the nodes below v, smaller than v, are in the left subtree, and all the values of bigger than v are the right subtree. Okay, and we will assume that there are no duplicate values. So for example, here if we look at a root node 5, then the left subtree of 5 contains values 1, 2, 4, which are all the nodes in this tree smaller than 5, and the right subtree contains 8 and 9. And now this is a property that is recursively satisfied throughout the tree. So if you look at the node 2, for example, its left subtree is just the single node 1, which is a value smaller than 1 in the tree rooted at 2. And its right subtree is the value 4, which is the right, it's a bigger than 2, the only value bigger than 2 in the subtree. Likewise, if we look at 8, then there's only one value other than 8 in the subtree starting at 8. That's the value 9, and since it's bigger, it's in the right subtree, and we have the left subtree empty. Right? So we can have these kind of gaps, unlike in heaps. We can have a gap, but we have this uniform property that at any node in the subtree, all the values smaller than the node are on the left, and all the values bigger are on the right. So typically, we would implement this as a linked structure where we have each node with 3 fields other than the value. So we have a pointer to the parent, a pointer to the left child, and a pointer to the right child. So the first thing that we can do with a binary search tree is to list out its values in sorted order. This is called an in-order traversal. So an in-order traversal is a recursive traversal. It is a way of walking through the tree so that we first walk through the left subtree, then the current node, and then the right subtree. For example, if we perform an in-order traversal here, we start at the root, and then we have to first walk down the left subtree, so we walk to the left child, and then once again we must walk down to the left subtree, so we walk to the left child, and now there is no left child, so now we will print out 1 and move back up because there is no right child. Now we print out 2 and go down to the right subtree, and now again because 4 has no left or right subtrees, we'll print it out and go back up. And since we have already finished 2, we will end up at the root. Now we will print out 5, move to the right subtree. Then because there is no left subtree, we'll print 8 and go to the right subtree. And finally we'll print 9. Okay. So it's easy to see that because of this property, we know that everything to the left is smaller than the value and everything to the right is bigger than the value. So this is like a recursive, this is very similar to the partitioning of quicksort in a sense. So we've already partitioned the values, so the smaller values are to the left, so there are bigger values to the right. And if we recursively follow this partitioning to list out, we will obviously get the values in sorted order. So now searching for a tree, a value in a binary search tree is very much like binary search. Remember, in binary search you have an array, and then you start at the midpoint, and then if you find it you say yes. Otherwise, if it is smaller, you go into the left. Otherwise, or if it's bigger, you look in the right. Okay, so we have a very similar thing. So we want to find a value v in a tree. If the tree is empty, of course, we say that it's not there, so we return false. If the current node has the value, then we have found it and we return true. On the other hand, if we have not found it, then since we have a tree, we look to see whether the value is smaller than the current value. If it is smaller, then we recursively search in the left and return whatever we find there. If it's found there, we say true. If it's not found there, we say it's not in the tree. Otherwise, we search recursively in the right. Okay, so this is very similar to binary search. Now, like binary search, you can do an iterative version of this. So you start at the root, and then so long as it's not nil, you trace down the path, right? So if the current value is v, you return true. Otherwise, you walk down to the left, or you walk. So you start at the root, and you kind of trace a path depending on the values that you find. And then when you reach a node, you say yes. Okay. On the other hand, if you reach a point where you cannot go any further, then if you run out of nodes, if you come all the way down and then you say there is no extension where I can find it, then you will say false. Okay. So this is the simple recursive and iterative versions of find. So the next two operations that we wanted to do were finding the minimum and the maximum. So the minimum node in the tree is the leftmost node. In other words, it's a node that you reach if you go as far as you can following only left edges. So in this case, from 5 if I go left, I go to 3. From 3 if I go left, I go to 1. And then I cannot go left. There is something below 1, it's on the right. But nevertheless, since I can't go left, 1 must be the minimum element of the tree. Because everything that is smaller than something will be to its left. So if I cannot go left, there is nothing smaller than 1. Okay, so this is the reason why the leftmost value in the tree will be the minimum. Right? So we can easily find it recursively. Now we will typically use this assuming the tree is not empty. It simplifies a little bit of coding. So assuming the tree is not empty, we don't have to check any special condition and give any error when it's not empty, when it is empty. So we assume it is not empty. So if we can go left, we do. So if the t dot left is nil, then this is the minimum value and we return it. Otherwise, we recursively search for the minimum value on our left. Okay. And again, there is a very simple iterative version. We start at the current thing and we keep going left as long as we can, so long as we don't hit nil. And when we reach this point where t dot left is nil, we come out of this loop and we return the value at this point. Right? So here, for instance, we would start with 5, t dot left is 3, t dot left is 1, t dot left is nil, so at this point we stop, so t is pointing to 1. So therefore, t dot value is 1 and this is the value we return. Right? So we can find the minimum. So symmetrically, the maximum is the rightmost value in the tree. Okay. As you go right, you go bigger. If you can't go right anymore, there is nothing which is bigger than that node. So here from 5 you can go to 7 to 9, and 9 is the biggest value because the next node, which although it is below 9 in the tree, it is to the left and therefore smaller than 9. So we have a symmetric recursive solution, maxval, which checks the right. If the right is nil, then we are at the maximum and we return the value. If the right is not nil, then we recursively search the right for the maximum. And again, an iterative version of the same. We just follow chase pointers to the right. Right? So long as t dot right is not nil, we move from t to t dot right. And when we can't move anymore, we are at the maximum value, so we return that value. So at this point, we have done find, minimum, and maximum in a search tree. Okay, so these three operations we have done. Now, if you remember, we have to do predecessor and successor. So let's first look at successor. So recall that the successor of x in the list is supposed to be the next value, the next smallest value after x in the list. So if we printed it out in sorted order, it will be the value that would appear to the right of x. Right? And in order of the in-order traversal of a tree prints out the values in sorted order. So it was effectively what in order would print immediately after x. So we know that the way that inorder works, right? It prints the left subtree, then it prints x, then it prints the right subtree. Right? So if we want the one that comes immediately after x, it will be the first value here, so the smallest value in the right subtree. In other words, the minimum of the right subtree, and we already know how to compute the minimum of a tree. But there could be a possibility that we want the successor of a value which doesn't have a right subtree. Then what do we do? Right? So the first observation is that if a value has no right subtree, then it must be the maximum of the subtree to which it belongs. So in this case, if we look at the value x, it has no right subtree, so it is the maximum of some subtree. So we have to first identify the subtree. So how do we identify the subtree? Well, we walk up and find out how the subtree is connected. Right? So we get to x by following a sequence of right pointers. So we follow those right pointers backwards, and when we follow a left pointer, we know that we have come out of the subtree. So therefore that node must be the root of the subtree below which this is the left subtree. Therefore that is the next value. So this entire red block subtree will be printed out in sorted order ending with x. After this, the root will be printed, which is this node which we have labeled SUCC for successor. So therefore that is the node that we want to designate as the successor for x. Right? So here is a simple pseudocode for this. So we want to find the successor of a node t. Now if this node has a right pointer, then we just return the minimum value of the right subtree. On the other hand, if it doesn't have a right, then we need to go up and find the first place where the path turns right. Okay, so we start with t and then we compute its parent, which we call y. Now so long as this direction is right, we keep moving up. So we go to one more parent and we move t up. So that's what's happening in this loop here. Okay? So we move t and y up, and then at some point we will move t and y will go this way. So it will be y dot left, and therefore this now this y is the successor of this original node t. Okay, and then there's one special case where we reach the top and we don't ever turn right, and that's the case where we actually was started from the maximum value overall in the tree, in which case we reach nil and it has no successor, so we'll just return nil. Okay, so let's look at this particular thing. So for 3, for instance, the right subtree exists 4 and the smallest value there is 4, therefore that's the successor. For 1, the smallest value is 2, so that's the successor. For 7, the minimum value in this subtree is 8, so 8 is the successor of 7. So these all come out of the basic case where you have a right subtree. On the other hand, if you don't have a right subtree, then for instance you start at 2, then you walk up, and then where you turn right, you find that 3 is the successor. Or from 4 you walk up, and where you turn right, you find that 5 is the successor. Similarly for 8 you immediately turn right, so 9 is the successor. And finally for 9 you will come and you will reach this nil case. So 9 will say that there is no successor because it is the largest possible value. So the situation for the predecessor is symmetric. So if we have a left subtree, then the predecessor is the maximum value in this. So we go down left and then we go all the way right. Okay? And if we don't have a left subtree, right, then it means that this is already the minimum value in its subtree. So we walk back up following these sequence of left pointers until we turn the other way, and then this node where we turn is the predecessor of this. Right? So for example, if we look at these values which have left subtree, so for 5 we go down the left subtree and we find the rightmost value, which is 4. So 4 is the predecessor of 5. Likewise 2 is the predecessor of 3, and 8 is the predecessor of 9. Okay. Now we have these other values for which we can't go left. For example, we can't go left at 2, we can't go left at 4, we can't go left at 7, right? We can't go left at 8. So what do we do? In these cases, we start at 2, for example, and then we try to go up, and where we turn right, there we find. Okay. So we come here and we find that 1 is the predecessor. Similarly from 4 we go, and so our goal is to go right, and then where we turn left we find the predecessor, right? So we immediately turn left at these 3 nodes, okay, and then 8 we go right, and where we turn left we find the predecessor. Okay, so this is how the predecessor works. It's exactly symmetric to the successor function. Okay, so now let's see how to insert a value. Inserting a value in a search tree is fairly straightforward. There is only one place because of, remember that the tree is listed in order will give us a sorted list, right? So now after adding this value, it must again give us a sorted list. So it is like saying that there is only one place to insert a value in a sorted list, right? So it's like insertion in a sorted list, except we have to find the correct place in the tree to hang it so that when we do this in order traversal, it would be in the correct order when we list it out. And it turns out that basically we have to find out where it should be by searching for it. And if it is not present, we add it where the search fails. Okay. So for instance, if we want to insert 21, then we will walk down the tree and we will look for the place where we should find 21. So if it's smaller than 52, we go left, smaller than 37, we go left, bigger than 16, we go right. And then we find that at 28, there is no value of 21 because there's no left. So then since it should be to the left of 28, we add it there. Okay. Now for instance, if we want to insert 65, then we will go right from 52, and now at 74 we will look left, that there's nothing to the left, so we will insert it. So it can happen at any position in the tree, it doesn't have to be at a leaf node. Like at 28 was already a leaf and we inserted 21 below it, but 74 had a right child, but we inserted something to its left because the left child was missing. Now it could be that we try to insert a value that's already there. For instance, we might want to insert 91, right? So we look for 91 and we find it. So we will interpret the insertion of 91 as something which does not disturb the tree, okay? Because we really said we don't want to have duplicate values, right? So when we insert, we try to find. If the find fails, we insert. If the find succeeds, we do nothing. So there's a very simple recursive way to do this. So first of all, we have a special case which says if the tree is empty, right, then we just create a new node and point to that node. So this is an isolated node which has only a value v, parent left and right will all be nil. On the other hand, if we find it, then we do nothing. Now we have not found it. So now if the value is smaller than the value of the current node, and if we have no left child, right, then we actually insert, right? If we have to go left and we can't go left, then we create a new node to our left and we make that node point here by its parent. So we create a new node here and we say that its parent is ourselves. So t.left.parent is t. Otherwise, we just recursively insert to our left, right? So if we do have a left, we recursively insert. If we don't have a left, then we create a node with v. This is the actual insert operation, and we make it point to us through the parent. Likewise, if we do want to go right and there is no right, we insert it to the right, okay, and we make it point to ourselves through its parent. Otherwise, we recursively insert to the right. So insert is a very straightforward function. So how do we delete a node? Okay, so delete says that we are given a value v. If we find v in the tree, we must delete the node containing v. So the basic case that is very simple to handle is when the node is a leaf node, because then we can just delete it and then it just falls off the tree at the bottom. So for instance, if we want to delete 65, then we will search for 65, find it by the usual mechanism of following the left and right paths, and then since it is a leaf node, we can just remove this node from the tree and nothing happens. It remains a valid search tree. Now sometimes the deleted node might have only one child. For instance, supposing we delete 74. So we come down to 74, now we want to delete this node, but it has a right child. But now what we can do is we can promote this child, right? So we can just kind of pretend that this link goes directly through this to 91, right? So we just eliminate the node in between and we directly connect 52 to the successor of the node that is going to be deleted. Okay, so if there's only one child, then there's no problem. Now what if the deleted node has two children, right? So supposing we want to delete 37, that is this one, right? So we identify 37. Now 37 must go, but we can't arbitrarily restructure the tree because we'll have two children and we don't know what to do with it, right? So now one strategy that works is to make a hole there to remove the 37 and replace it by either its predecessor or its successor. Okay, so supposing we identify its predecessor, but predecessor, remember, will be the biggest node, the maximum in its left subtree. So here it will be 28. So what we will do is we'll copy the 28 to this node which is to be deleted. So 37, the node has not been deleted, its value has been replaced by 28. Now why is this a valid value? Because we want to preserve the sorted thing, right? So if we have some list of sorted values and I delete something here, then what happens is that everything is to the right of the predecessor. So I basically move the predecessor to this point and I preserve the order between these elements in the sorted order. So moving the predecessor here, I guarantee that anything that is to the right remains bigger than this node, and everything to the left remains smaller than this node because it was the biggest value in this. Now, of course, I have two copies of 28, so I must remove the 28, right? So then I'll focus on the left subtree and I delete this predecessor value. But the good thing about the predecessor value is that it's the rightmost value. Rightmost value means either it is a leaf or it has only one left child. So we are back in the simpler case, one of these two cases, right? So we can just delete the predecessor of V using one of these two cases. Either it's going to be a leaf, it just falls off, or I'm going to promote this 21. So in this case, the 21 will get promoted, right? So deleting in general consists of moving the predecessor to the current value and then deleting the predecessor from the left subtree. So it's a long piece of code because we have these many cases. So first of all, if it's an empty tree, we do have nothing to, we can't delete. If on the other hand, that value at the current node is not V, so if it is strictly less than, then if there is something to the left, we delete from there. If it is strictly greater than, if there is something to the right, we delete from there. So these are the two recursive cases, right? So if it is not strictly less than and not strictly greater than, it must be equal and we have to do some real delete. So now we have these three cases, right? So the first case actually breaks up into two cases. If it's a leaf, it could be a leaf because it is the root, right? The root and it is only one node. So we will treat that slightly differently. So we will say that if it has no parent, that is it's the root, then deleting the value actually makes the tree empty. So we just reset T to be the empty tree nil and we return. If on the other hand, it is a leaf node, it has no children, right? Then what we do is we try to delete it by just setting the parent's value to be nil. So supposing I come here, right, and this is my leaf node and I want to delete this, then I look up and then I basically set the right pointer of this to be nil, which essentially kills off this link and says that there is no right pointer. So if the current node is the left child of its parent, I set the left child of the parent to nil, otherwise I set the right child of the parent to nil. So this of course creates some garbage because this node is now inaccessible from the tree, but we assume that this will be recovered and we don't have to worry about it. If you are doing this in a language like C, then you have to be careful to restore this back to the free space. But in other languages which have garbage collection, this will just automatically be restored when garbage collection takes over. But the point is that we are just simply removing it by resetting our parent's pointer to be nil, right? So this is the leaf case. So having considered the leaf case, now let's consider the case where you delete a node with only one child. Right? So the first case we will look at is when we are trying to delete a node which has only a left subtree. So left is not nil, right is nil. Okay. So what we do first of all is we look at this immediate left successor. So this has a parent somewhere above it. So we first make this left child point directly to the parent. So t.left.parent is d.parent. Right? Then we look up and we decide whether this is a left parent or a left child or a right child of which parent. So supposing the node we have, okay, is sitting to the left of its parent, if t.parent.left is t, okay, then what we do is we make this point directly here. Okay. Now on the other hand, if it was not like this but it was the other way, right? So if this happened to be a right child of its parent, then we say that t.parent, the right child should now point directly here. Right? The right child of the parent is now my left child. Right? So this is a way to splice out or remove this thing and promote the child, the only child up. We do a symmetrical thing if it's only the right child. Right? So we first take the right child and then we reset its parent to be your own parent, and then after that, depending on the case, we either make this point like this or this point like this. Okay? So either t.parent.left is t.right, t.parent.right is t.right. So if we have only one child, we just remove the node effectively from the tree. And finally, if we have a node with two children, what we do is we first compute the predecessor of v, okay, and then we set the current node's value to be the predecessor value. And now we know that this value is duplicate, so we go to the left child and delete it. Now remember that when we delete it here, the left child, we are deleting what we know is the maximum value. So therefore it will have either no children, it will be a leaf, or it will have a single child. So it won't come back to this case, it will just stop at the earlier two cases and it will get successfully deleted. So there is no problem with just calling delete again. Right? So all these operations that we have described now walk down a single path. So therefore, the worst case complexity of any one of these operations is the height of the current given tree. And if we have maintained some kind of a balanced tree like a heap we saw, then the height is logarithmic in the size. So if we have n nodes, the height is order log n. So we will see in the next lecture how to maintain the balance, but assuming that we maintain the balance, we have succeeded in what we achieved, what we wanted to achieve, which is we wanted all these 7 operations, okay, to be simultaneously efficient, and they are all now log n time because each of them can be achieved in one traversal up or down a path in the tree. So in the previous lecture, we looked at operations on search trees and we claimed that these were efficient if we could maintain balance. So let's see how we can keep search trees balanced. So recall that we are looking at these 7 operations. Okay, we want to be able to search for a value. We want to be able to insert and delete values. We also want to be able to compute the minimum and the maximum value in a tree and also find the predecessor and successor of a given value. And all of these we claimed would be order log n provided the tree is balanced. Okay, so that's because all of the operations as we implemented them will walk up or down a single path, and so the worst case would be the height of the tree, and in a balanced tree the height will always be logarithmic in the size of the tree. So today's this lecture, the goal is to explain how to maintain the balance as the tree grows and shrinks. So trees, there are many different notions of balance in a tree. So essentially a balance, you should think of it as like a physical balance, right? So if you go to an old style vegetable seller, then they will have this kind of a balance. And then you want at any point, if you hold up a tree by its root, the two sides should be balanced. They should be equal, right? So the most direct notion of balance is that the two are exactly equal. That is, the number of nodes at the left is equal to the number of nodes in the right for every node. But then it's easy to see that you're going to get complete binary trees. For example, you could have a tree which has this structure. Or if you extended one more level, then for every node on the left, you must extend on the right. But then these must also be balanced. So you must definitely complete this. So you can have a tree up to 3 levels, which is completely filled, or up to 4 levels, and so on, right? So if you want this exact size balance, then it's very restricted. So you might have a little bit more flexibility. You might say that, okay, we don't want it to be exactly equal. Maybe we want it to be at most one off. Then you could have structures, for instance, like this, where you have only a left, or you have at this point a left and a right, but you have only a right. Okay, these type of structures now, which are not complete binary trees, become balanced in this notion. So this allows us more flexibility and we can get more trees this way, but it is difficult to maintain this property incrementally as we do inserts and deletes. So we will go for a different notion of balance. Notion of balance that we will use is not with respect to size, but with respect to height. Okay, so we will say that the height is the number of nodes from the root to a leaf. For example, if I have a tree which looks like this, then here the height is 1, 2, 3, 4, because on this path we have 4 nodes, right? So the height becomes 4. It's the length of the longest path measured in terms of nodes. The reason we measure in terms of nodes is then we can distinguish easily the empty tree from the tree with only a root. If we measure in terms of edges, the tree with only a root will have height 0 because there are no edges, and so would be the empty tree. Whereas if we measure in terms of nodes, okay, then the empty tree has height 0 and the tree with only the root has height 1. So we can distinguish these two. And now, in keeping with our earlier relaxation of the size condition, a height balanced tree will be one where the height of the left and the height of the right differ by at most 1. Now this is more relaxed than the previous thing. For example, now of course I could start with a height balance tree like this, okay, and then I could now connect this to form a height balance tree like this, right? And now this, which is a height 3 tree, I can connect with a height 2 tree, okay, and form a height balance tree which looks like this. So the height of the left subtree is 3, the height of the right subtree is 2. In this recursively, the height of the left subtree is 2, the height of the right subtree is 1, and so on. Right? So we could have things which look quite different. So size here, for instance, size is 4 and size is 2. Okay, but nevertheless, you can kind of compute that the size, even in this case, will be exponential in the height, or rather, the height will be logarithmic in the size. So these trees are called AVL trees. They're named after the two people who independently invented them. One person called Edelson-Welsky and independently Landis. Okay, so an AVL tree is a height balance tree which says that at every node the height of the left and the height of the right subtrees differ by at most 1. So let us refer to the difference between the heights as the slope. Okay, so we have intuitively in our picture. So if it's unbalanced, then the thing is tilted. So we could have a tilt this way or a tilt this way. So we call this the slope. So let us say the slope is the height of the left minus height. So the height of the left is less than the height of the right, then you have positive slope. If the height of the left is bigger than the height of the right, then you have left is smaller than right, you have negative slope. Left is bigger than right, you have positive slope. So in a balanced tree, since the height difference absolute value must be 1, you can only have 3 possible slopes throughout the tree. Either there is no slope, they are exactly the same, or it is minus 1 or plus 1. Now if you can argue very easily that if the current values of the slopes are minus 1 plus 1, when you delete a node, you can reduce one of the heights by 1, so the difference can go from 1 to 2. Or when you increase, you can make the height difference again go from 1 to 2. So the new slope after a single insert or a single delete can be at most minus 1 or minus 2 or plus 2. So what we will endeavor to do, what we will try to do is that whenever we do an insert or a delete, we'll immediately try to rebalance the tree. So we will have a single disturbance from to minus 2 or plus 2. It will never become very badly unbalanced, and we will immediately restore the balance to within minus 1 to plus 1. Okay, so we will do this rebalancing. We will also do this rebalancing bottom up. So what happens when we do an insert, if you remember, is that we go down and we find a place to insert. Right? So at this point we add a new node. So therefore now at this point there could be some imbalance. So we'll fix it. Then we'll go back to up this path and we'll go there and we will fix the path here. But at this point we will assume that the tree below has been balanced. Right? So whenever we rebalance a slope which is outside the range, we will assume that the subtrees below that are already balanced. Okay, because this balancing, as we will see, is going to be done bottom up. Right, so here is a typical situation that we would reach after a single operation which removes the balance. Okay, so we might have a node which has slope plus 2 or minus 2. So let's look at plus 2. Minus 2 will turn out to be symmetric. So we have a node which we call x, which has slope plus 2, and what it means is it has a left tree and a right tree such that the height of the left tree is 2 more than the height of the right tree. Remember, the slope is height of left minus height of right. So h plus 2 minus h will be 2. Now recursively we are going to assume that all the slopes here and here are at most plus 1 or minus 1. Okay, so we are assuming that everything below this has been fixed and the only imbalance in this subtree at x is at x itself. So now since the left has height h plus 2, okay, it has height at least 2. H can be at most, at smallest h can be 0. So it has height at least 2, so there is at least one node here. I mean 2 means that there are at least 2 nodes here, so there is at least one node in particular. So we will expand this. Okay, so we will expand this by exposing its root, and the root will have in general 2 subtrees. Right? So now this whole thing has height h plus 2. Okay. So we will now look at this new node that we have extracted. Right? So its slope is minus 1, 0 or plus 1. Okay, and we are going to do some bottom-up rebalancing. We are assuming everything below is okay. So we're going to do some case analysis based on what is the slope of y. So let's first look at the situation where the slope of y is either 0 or plus 1. So if it is 0 or plus 1, it means that, so remember this whole thing was h plus 2, of which one node is here. So its left child must be at least h plus 1. And because the slope is 0 or plus 1, the right child is either h plus 1 in case the slope is 0, or it is h in case the slope is plus 1. So now this is the current situation as we have it with an unbalanced node x. Everything below is balanced, but we have just come to a situation where we are trying to analyze what is the situation below, right? So x has got a unbalance of plus 2, and below it we have y, which we are assuming is either 0 or plus 1. So now we do this rotation. So we take this tree and we kind of hang it up by y and we reattach things. Okay, so in this rotation, when we hang it up by y, x comes down. Okay, and now we look at the subtrees. So we have these three subtrees, right? We had TLL, TLR, and TR. So TR is to the right of x and is also to the right of y. Okay, so it is the right of both. TLR is to the left of x, to the right of y. TLL is to the left of y, left of x. So if we go there, we find that TR is to the right of both, TLR is to the left of x, right of y, and TLL is to the left of both. Right? So we hang up these trees. So now all the values we can verify will be correctly organized as a search tree should. But now if you look at the slopes, we have just inherited the slopes from what we knew, that the slope of TLL was h plus 1, TLR was h plus 1 or h, and TR is h. Okay, so this means that if I look at this overall height at this point, it is either h plus 1 or at most h plus 2. So this is h plus 2 or h plus 1. Right? If it is h plus 2, then the height slope at y is minus 1. If it is h plus 1, then both sides are h plus 1, slope at y is 0. And if we look at x, okay, here we have h or h plus 1, and here we have h. So the difference is either 0 or plus 1. So x is now balanced, y is balanced, and by assumption, inductively, all the gray subtrees are balanced. So by one right rotation, okay, we have rebalanced the tree. So the third situation is that it is not 0 or plus 1, but the slope at y is minus 1. Okay. So we have already dealt with the case where 0 or plus 1 is the possibility. So if it is minus 1, this means that the right subtree must be strictly taller than the left subtree. So this whole thing, remember, again is h plus 2 by assumption, because the whole thing has plus 2. So this whole thing is h plus 2 and this thing is h. Now this h plus 2 has now been split as y and the rest. Therefore h plus 1 must be coming from the right and h from the left, because the slope by assumption we are assuming slope is minus 1. So now we are going to expand out this node. Now it's h plus 1. So there is at least one node here. Even if h is 0, it has at least a root node. So we will expose that root node as we exposed y earlier. Okay, so now we have kind of expanded this TLR as z with two subtrees, TLRL. So this is supposed to indicate that I start at the original tree, go left, go right, and go left. So TLRL, go left, go right. So this is TLRR. So that's the notation for these subtrees, right? So this whole thing was h plus 1. So therefore this h plus 1 came from either side. So either this is h or h minus 1, or this is h or h minus 1. Okay, at least one of them must be h. Because if both are h minus 1, then the whole thing cannot be h plus 1. Right? So at least one is h and it is balanced. So I don't know which way it is, but at least one of these trees has h, the other one could have h or h minus 1. And it turns out it will not matter which one has it. So now I have a two-step procedure. What I will do is now I will do a similar rotation but to the left, involving these two nodes. Right? So I will hang up these subtrees here by z. Right? So if I hang up these subtrees, then what happens is that these three trees below have to be reattached, right? And we reattach them in the correct way. TLL is to the left of both y and z. TLRR is to the right of both y and z, and TLRL is to the left of z and to the right of y. And now if you go back and check all the heights, then you find that at y, I either have height 0, okay, or I have height plus 1. Now if I look at z, then the left hand side is now h plus 1, okay, and the right hand side is h or h minus 1. So if it's h plus 1 and this is h, then I get plus 1. If it is h1, h plus 1 and this is h minus 1, I get plus 2. So in the process now, not only did I have x which was unbalanced, I have temporarily created a z which potentially is unbalanced. So I cannot say for sure it's unbalanced, but it could be unbalanced because I don't know which is h and which is h minus 1. But this is only an intermediate step. So now what I did, so earlier what we did was we did on left rotation here, right? So I'm going to follow this up by a right rotation at x. So if we rotate right at x, z goes up, x goes down. And now again we hang off the 4 trees, and there's only one way to hang off. You can verify if you go back and check how they were hanging. So TRR must be bigger than z and x, TLL must be smaller than y and z, and so on. And now we have a very happy situation, which is that if we look at the slope of y, then it is either 0 or it could be plus 1 because this could be minus h minus 1. If I look at x, it could be minus 1 because this could be h minus 1. This is definitely h, or it could be 0. But this whole thing is definitely h plus 1 because I do have at least one subtree of size h. This whole thing is again h plus 1 because I have at least one subtree of size h, and therefore the slope at z is 0. So all three nodes x, y and z have slopes in the correct range, and therefore again I have restored the balance. So to summarize this, what we have said is that if we have plus 2, then we look at the left child of x, call it y. Now, if the slope of y is 0 or 1, we rotate right at x. If the slope at y is minus 1, we first rotate this and then we rotate y. Either case we rotate at x, but first we rotate at y in case the slope is minus 1. Now it will turn out that if we have the other case, the other extreme where the slope at x is minus 2, then we'll have a symmetric picture. So we will be able to expose the right child, call it y. So then the basic operation is that if y has slope minus 1 or 0, it's symmetric, remember. Okay, then we will do a single left rotation at x. Otherwise, we will first do a right rotation at y in case the slope at y is plus 1, and then we will do a left rotation at x. Okay, so we will not look at the minus 2 case in detail, but it's easy to see that it is symmetric to the plus 2 case. Okay, so how do you do these rotations? Well, you can just draw these pictures and figure it out. So you just give names to everything. So we say that we want to rotate this x down and the y up. Now we have our original t pointing here, remember, right? So we cannot change the node that t is pointing to. So we remember the value at t, we remember the value here. So we give these names x and y to the contents. And then we have these pointers pointing to these 3 trees, TLL, TLR and TR. And then we reconnect them. So what we do is we first replace this value by y, right? Then what we do is we make this node come to the right and we reset its value to x. Okay, so we put an x here and we have moved it there. And then we hang off below the top node on the left, we put TLL. And below this new right node on the left we put TLR, and the right we put TR. So we just do this kind of reconnection. It's like unhooking and rehooking trees, and we just keep track of all the names so that everything gets unhooked and rehooked correctly. So it's a very simple. So notice that this is a kind of constant set of operations involving a few of these left and right pointers. So it will, regardless of the size of the tree, it's a very local operation. So we can treat this as one constant unit of operations. Okay, and a similar thing for the left. Okay, we give names and we just do this updating exactly as we had done before. So again, this is a constant set of operations which implements rotate left. So now that we have the 2 rotations, okay, then what does rebalancing say? Rebalancing says that if I have a node which has plus 2, then I will expose its left child, okay, and I will check its slope. If its slope is minus 1, then first I will do a right rotation there, sorry, a left rotation there. And then regardless, I will do a right rotation at the top. Okay, and the symmetric cases, if I have a slope which has minus 2 at the top, then it will have a right child. Okay, and then if this has plus 1, then I will first do a right rotation here, and then regardless, I will do a left rotation at the top. Okay, so rebalancing is these 2 steps, and rotation is a set of other steps. So basically, rebalancing at a given node is a constant number of operations at that node. So now what we do is every time we make a change in our tree which could affect the balance or the slope of a node, we do a rebalance, right? So when we, in our earlier code for insert, when we did a recursive insert in the left of a tree, we rebalance it. Similarly, when we insert on the right of a tree, we rebalance it. So we just introduced this rebalance code and notice that this is a constant operation for this node. Right? So we will do this all the way along the path. So this will be a log n times a constant number of operations. So this will not affect anything in terms of the asymptotic complexity of our operation. It will be a logarithmic number of constant time operations for each node. The same with the delete. Wherever we do a recursive delete, we rebalance. And then there was this case where we deleted the maximum value of the predecessor. So again, we do a rebalance. Right? So wherever we had our insert or delete affecting the structure of the tree, we just make sure that we rebalance the tree at that point. So there is one point we have to be a bit careful about in this thing. So we said that we have to do all these rebalancing. So if we go back to rebalancing, okay, so rebalancing requires us to compute the slope. Okay, and slope we said was defined to be the height of the left minus the height of the right. Now it is possible to compute the height on the fly. The height of a tree is recursively computed. If it is nil, it has height 0. Otherwise, you recursively compute the height of the left and the right, and then accounting for this node, you add 1 to that. So you take the maximum of the two subtrees and add 1. But this, unfortunately, involves examining every node in the tree. So this will be proportional to order of the size of the tree, right? So this will be an exponential operation in some sense, compared to the path. So we are trying to do a log n operation. This will be an order n operation. Okay, so this will be killing all our attempts to do something efficiently, because in order to compute the height, we actually have to see the entire tree, which is not what we want to do. But we can get around this by just keeping the current value of the height and updating it each time. Right? So we have an additional thing. So we have in our tree node, we currently had the value parent, left and right. So now we just add one more field called height. So now whenever we do any rebalancing, then the height of this tree may change, the current node. So we just look inductively, we assume that below us the height got set correctly. So we look at the two heights which are locally there, add 1 to the maximum of 2. Now this is just looking up one value in our two neighbors below, the two children. Right? So this now becomes a constant time operation. It doesn't require us to traverse the entire tree. So as we are rebalancing, we readjust the heights. And every time we want to check the slope, we just have to check the value of the two trees below us and check the difference of their heights, because that will be given locally by this height field in the node. Okay, so we have to be careful not to compute height recursively, but to store the height as part of the tree and also update that with every update. So to summarize, you can use rotations to maintain height balanced binary search trees. And in a height balanced binary search tree, we have claimed that the height is going to be logarithmic in the size. And since all our operations are proportional to the height, because they all go along one path, all these operations, namely find, insert, delete, minimum, maximum, predecessor and successor, can all be done in logarithmic time. So let's take another look at greedy algorithms. So we're looking at algorithms where we need to achieve a global optimum by making a sequence of choices. So in a greedy strategy, what we do is we make the next choice based on some local criteria. So there may be a number of choices we could make, but we just pick one of them based on something which looks good at the moment. And now we never go back and revise an earlier decision. So we deterministically search through the space of solutions by picking a good choice at each step. And this drastically reduces the space in which we have to search. So the tricky thing is that this strategy very often doesn't work. So if we have a greedy strategy in mind, we need to go back and prove that the way we have made our local choices actually achieves a global optimum. So we have seen three algorithms so far which follow this greedy paradigm. The first was Dijkstra's algorithm for the single source shortest path problem. So recall that in this algorithm, we kept burning vertices. And at each stage, we froze the distance to the nearest unburned vertex and claimed that this would in fact be the shortest distance to that vertex from the source. So globally, the optimum we achieve in this algorithm is that the distance assigned by this greedy strategy happens to be the shortest distance from the source. A closely related algorithm is Prim's algorithm for the minimum cost spanning tree. So here we incrementally build up a tree, and at each stage we add to the spanning tree the nearest vertex that is not yet in the tree. And here the global optimum that we achieve is that we construct a spanning tree that is minimum cost. Another algorithm for the minimum cost spanning tree is Kruskal's algorithm. Here we don't build up a tree directly, but rather we keep collecting edges and form a connected component overall, which becomes a tree. So here we keep adding to the current set of edges in our set the next smallest edge that doesn't form a cycle with those that we've already chosen. And now the global optimum is that the edges that we collect in this way form a minimum cost spanning tree. So now let's look at a completely different problem, a problem called interval scheduling. So suppose we have a special video classroom where we can deliver online lectures. Now different teachers want to book the classroom to deliver classes, and each instructor has a slot that he would like to deliver his lecture in. So instructor I has a slot that starts at a time Si and finishes at Fi. Right? So you have a slot which starts at Si and finishes at Fi. Now two instructors may have overlapping slots, so there may be somebody who wants a slot like this. Okay, so the blue slot starts before the red slot ends. So obviously both these slots cannot be given bookings because they will interfere with each other. So our task is to look at the set of bookings and choose a subset which is feasible, that is, no two bookings that we choose interfere with each other, so that we maximize the number of teachers who get to use the room. So broadly, if we follow a greedy approach, this is what we would do. Among all the bookings that are not yet allocated and which are still available to allocate, we will pick one based on some local strategy. Then we would remove all conflicting bookings, bookings that overlap with this booking with the slot that we just allocated. And somehow we have to argue that this sequence of bookings that we are choosing maximizes the number of teachers who get to use the room. So let's look at some typical greedy strategies that one might want. So one strategy might be to choose the booking whose start time is earliest. But it's not difficult to come up with a counterexample. So if you look at this picture, there is one long green booking, okay, which starts earliest and in fact ends after all the other bookings are made. So if we use this greedy strategy, we would allocate this very long booking and the entire period will be allocated to just one teacher. Whereas if we chose the booking that started a little later, then we could actually satisfy 6 teachers' bookings. And since our goal is to maximize the number of teachers who can use the room, that would be a better strategy. So this greedy strategy is clearly flawed. Another greedy strategy we might think of is to choose a booking whose interval is shortest. Once again, here is a counterexample. The interval in the middle is the shortest one. But if we choose this, it is in conflict with both the other bookings, so we have to rule both of them out. So if we choose the shortest interval, then we can only allocate one teacher to the room. Whereas if we ignore that strategy and if we choose the two longer intervals, then we can actually use the room for 2 teachers and get a better optimum for the problem that we have chosen. So the previous example suggests that there is something to do with conflicts. So maybe we might choose bookings in terms of how many other bookings they rule out. So one strategy now we might think of is to choose the booking that overlaps with the minimum number of other bookings. In other words, by choosing this booking, we rule out as few other bookings as possible. So let's look at this example. Here, the center booking overlaps with only 2, this one and this one. Every other booking overlaps with at least 3. So if we choose this booking, then we rule out the bookings on either side of it. And that means that we can do either this one or one of these, right? So if we take the center booking, we can do at most 3 bookings overall. We can't do the 2 on either side of it. So we can either do the 2 extreme ones, or we can do any one of these and any one of these, right? So we can do a total of 3. We can allocate a total of 3 bookings among these. However, if we don't do this, right, if we choose a better strategy would be to clearly take the 4 on the top. Okay? So we can allocate 4 teachers this room if we don't use the strategy that we must pick the one with the minimum number of conflicts. So this greedy strategy also fails. So here is a 4th strategy. Instead of choosing the one like we began with, whose start time is earliest, let's choose the one whose finish time is earliest. So can we come up with a counterexample? Or should we instead try to prove that this is correct? So in fact, this strategy does work, and let's see how we can prove it. Before we prove it, let's formally write down the algorithm a little more clearly. So we start with a set of bookings B, and we want to construct from this set a subset A of accepted bookings. So initially, we have no accepted bookings because we're just starting to build this set. And now we do the following. So long as we have pending bookings which are still feasible, we pick that booking which has the smallest finishing time among the set which is still with us, and we add that to B, that to A. And now having added that to A, we cannot schedule any more bookings which overlap with this B. So we remove from our set capital B all the bookings which overlap with the booking B that we just chose. Right? So each time we pick up the next booking which is still available with the smallest finishing time, and we remove everything which is in conflict with it. So here is an example of how our algorithm would work. So here we have 9 bookings. The blue lines indicate the bookings, and the numbers of the bookings are given above them. So in this, so initially our set B has all these 9 bookings. Okay, and our set A is initially empty. So now what we look at is the smallest finishing time among the 9 bookings, and that happens to be 1. Right? So we select 1, and then having selected 1, we find all the bookings which overlap with it. So 2 overlaps with 1, and so does 6. So we remove 2 from our set, and we remove 6 from our set. So now B has been pruned to 3, 5, 3, 4, 5, 7, 8, 9. Right? And A has the booking number 1. So now among this feasible set 3, 4, 5, 7, 8, 9, we pick the one that ends earliest, which is 3. Right? And then since 4 is in conflict with 3, we remove 4. So continuing in this way, we now pick 5 because 5 is the earliest one to finish. And then because 7 is in conflict with 5, we remove 7. And now we have 2 left, 8 and 9. But 8 finishes before 9. We could actually pick either one, but our algorithm will pick 8 because 8 has the shortest finishing time. So we pick 8, and then we will say that 9 is not feasible, so we remove it. And now we have that B is empty, and A is 1, 3, 5, 8. And since B is empty, we have no more jobs to schedule, no more bookings to honor, so the algorithm ends. Right? So we have found a feasible set of 4 bookings that can be accommodated within this list. So our goal is to show that the solution A produced by our algorithm is actually correct. So suppose there is an optimal set of bookings O. Now we cannot in general assume that our solution A is identical to O because there may be multiple ways of producing solutions of the same size. Remember that all we want is a solution which allocates as many teachers as possible to rooms. So there may be 2 different ways to allocate the same number of teachers. So we can't argue that A and O are identical, but it suffices to show that A and O are of the same size. In other words, no matter what optimal booking is produced by some other strategy, our strategy, our greedy strategy, produces one which is of the same size. So let A be the set of bookings that our strategy chooses, and this could be the order in which it chooses. So I1 is chosen first, then I2, and so on. So when I1 is chosen, I2 is still feasible, and since I1 was the earliest finishing time overall, we have that the finishing time of I1 is before the starting time of I2, the finishing time of I2 is before the starting time of I3, and so on. So these bookings in A are in sorted order. Now let's assume that we have an optimum solution with M bookings, J1 to Jm, again in sorted order. So J1 ends before J2 starts, J2 ends before J3 starts, and so on. So our goal is to show that K in fact is the same as M. In other words, the optimum solution is of the same size as the solution that the greedy strategy produces. So we will actually show that for each job in the sequence I and J, okay, the corresponding job in the A sequence finishes no later than the corresponding job in the O sequence. So for every R up to K, f of IR is earlier than or equal to f of JR. So in this sense, we are trying to argue that the greedy solution stays ahead of any optimum solution that you might produce by any other method. So the proof of this claim is by induction on R. So when we look at the first job, I1, we know that I1 is overall the earliest finish time among all the jobs, all the bookings in our list, right? Since I1 has the earliest finish time among all the bookings, it must definitely be less than or equal to f of J1, because J1 cannot be smaller than the overall minimum. Now let's assume that we have established by induction that up to R minus 1, the booking I minus I of R minus 1 has a finish time which is earlier than the booking J of R minus 1. Then we claim it must be the case that IR finishes before JR. Because if we didn't have this, then we would have the picture as below. So we have that IR minus 1 finishes before JR minus 1. Now suppose we claim that JR actually ends before IR. Then our algorithm would at this stage find that JR is still feasible because it doesn't overlap with IR minus 1. And among the jobs which remain, JR has an earlier finishing time than IR. So our greedy strategy would pick JR rather than IR. So therefore the fact that we have picked IR and not JR means that we cannot have a picture like this. It cannot be that IR ends strictly after JR. It must end before or at the same time as JR. So now, having shown that the greedy strategy always stays ahead, we will now claim that actually our solution must be optimal. So suppose that M is actually strictly greater than K. Then we know that when we reach IK, right, it is before JK. Now because we have a solution which is longer than K, there is another job after this called JK plus 1. Okay, assuming that M is strictly, because this goes up to job booking JM, right? So since this happens, there must be a sequence of jobs, sequence of bookings after JK. Okay, so let's look at the sequence. Now the claim is that this particular booking at this point is not ruled out by anything that has happened before, right? So if you look at I1 up to IK, none of these overlap with JK plus 1 because JK plus 1 is after JK, right? So IK finishes before JK and JK finishes before JK plus 1 starts. Therefore IK is compatible with JK plus 1. This means at this stage B is not empty, right? When we have finished in our greedy algorithm processing I1 to IK, B is not empty. But we claim that we stopped with IK, and the only reason our greedy algorithm stops is because B is empty, right? So if there is a job or a booking JK plus 1, then it cannot be that our algorithm stopped at this point, so there's a contradiction, right? So therefore we cannot have any bookings in the optimum solution which go beyond k, and therefore m must be equal to k. So having shown that it's correct, let's just quickly look at how we would implement this and estimate the upper bound of the complexity. So initially we sort the n bookings by finishing time. This takes time n log n for n bookings. And now let's assume that the bookings are renumbered 1, 2 up to n in this sorted order, right? So booking 1 has the earliest finishing time, booking 2 has the second earliest finishing time, and so on. Now we set up in one order n scan an array st such that st of I contains the starting time of booking I. Now we start with booking 1, right? And each time we choose a booking j, we start from j plus 1 and keep scanning the start times of bookings till we find the earliest k whose starting time is beyond f of j. In other words, we are looking, so we know that these bookings are in order of finishing time, right? So we know that after j, the booking that ends next is j plus 1, but if its starting time is not beyond the finishing time of j, it's overlapping, so it cannot be compatible. So we just scan this array st until we find the smallest k, which actually starts after fj ends, right? So in this way, in one order n scan, we can go through all our bookings and pick up a greedy optimum set. Right? So this is an order n scan. Sorting takes order n log n. So overall, this greedy strategy is correct and it takes time O n log n. So we now look at a different greedy algorithm with a slightly more complicated proof of correctness. So the problem we are looking at is called minimizing lateness. So like our interval scheduling problem in the last example, we have a single resource and there are n requests to use this resource. So now, unlike the earlier situation where we had a start time and a finish time and the resource had to be scheduled within this time, here we just know that each request I requires time I t of I to complete, and each request I comes with a deadline d of I. Here we are going to schedule every request. So each request j will start at a time start of j called sj, and it will take time tj, so it will end at f of j, the finish time of j, which will be the start time plus the time it takes to process request j. Now if this finish time is bigger than the deadline, then it is late, right? So the amount that it is late is given by the difference between the delay and the finish time. And the goal is to find a schedule which minimizes the maximum lateness. So we want to minimize the maximum value of this Lj over all the jobs j. So since we know we are looking for greedy strategies, let's try and suggest some greedy strategies for this problem. So suppose we want to finish jobs as quickly as possible. So we choose the shortest job first. So we choose jobs in increasing order of length. So this could be a greedy strategy, but unfortunately there is a fairly simple counterexample. So suppose we have two jobs. Job 1 takes 1 time unit and job 2 takes 10 time units, but the deadlines are 100 and 10 respectively. In other words, the first job has a very long gap within which it can be scheduled without any penalty, whereas the second job has to finish more or less assuming it starts initially. So now if we pick the shortest job, right, then we are going to incur a lateness of 1 because we're going to go from 1 and then we're going to go from 2 to 11, right? So the second job is going to finish 1 unit of time late. On the other hand, if we do 1 to 10 and then we do 11, then we get no lateness, we get lateness 0, right? So here picking the shortest job first doesn't give us the best answer. So the second strategy might be to pick those jobs. So earlier we saw that we had a job which had 10 time units and it also had a deadline of 10. So we need to pick those jobs perhaps whose time is closest to the deadline, right? So we look at the slack, how much time we can afford to delay starting a job, dj minus tj and pick those which have the smallest slack. So here we have a very similar example to the first one, except that the deadline of the first job is now 2. So here we have slack 0 for the second job and slack 1 the first job. Right? So the second one has a deadline equal to its time. The first one has a deadline which is 1 more than its time. So then by this strategy we would pick T2 first, right? And if we pick T2 followed by T1, then what happens is that this lateness is going to be 11 minus 2 because we first do T2, so we start T1 job 1 only at time 11, so it finishes at time 11, but it should have finished by 2, so the lateness is 9. On the other hand, if we do T1 followed by T2, then we have that the lateness is just 1 because the second job should have finished at 10, instead it finishes at 11, so 11 minus 7 is 1. Okay. So now here, although our intuition told us to pick the smaller slack time, actually that's not the good one. So it turns out that a greedy strategy that does work is to choose the job with the earliest deadline d of j first. The challenge is to prove that this strategy is in fact correct. So to prove that it's correct, we'll first assume that we have actually numbered all our jobs in order of deadline. Right? So we number our jobs 1, 2, 3 up to n so that the deadline of 1 is less than or equal to deadline of 2 and so on. Now having done this, our schedule is very straightforward. We just schedule job 1 first, then job 2, then job 3 and so on. Right? So we don't have to do anything. Once we have sorted the jobs by deadline, we just schedule them in that order. So the job 1 starts at time 0, which we'll call s of 1. It ends at f of 1, which is t of 1, 0 plus t of 1. Now S2, the starting time for job 2 is as soon as job 1 ends. Right? So at F1 we start job 2 and it will end at S2 plus T2. Okay, so likewise now S3 will be F2. We'll start job 3 at time F2 and we'll go on till S3 plus T3 and call this F3. Right? So we will just schedule each job as soon as the previous one ends in this deadline order. So since we are scheduling jobs one after the other without waiting, it is very clear that the schedule has no gaps. Right? It has no idle time. The resource that we are trying to allocate is continuously in use until all n requests are finished. Right? So now the claim is that there is an optimum schedule which has no idle time. Right? Because suppose you had an optimum schedule in which you had blocks like this where the resource was being used, okay, and there were these gaps in between which were idle. Then it's very clear that I can shift these things forward because there's no constraint on when I can schedule things. I only have a constraint on when things should finish. So by moving things earlier, I can only reduce the lateness. Right? So if the blue schedule with gaps was optimal, I can move it so that it doesn't have gaps, and certainly my new schedule will have no more lateness than the blue one. Therefore, we can always assume that the optimum schedule has no idle time. So now our goal is to actually argue that the schedule that we have produced by sorting in terms of deadlines and then using that order blindly is as good as any optimal schedule. So here in the previous interval scheduling problem, we said that we would not be able to guarantee that the schedule that we found was equal to a given optimal schedule, but we will just show that they're of the same size. Now here what we will do is slightly different. We will take an optimum schedule which is produced by some other strategy and we will step by step transform it into one that is the same as the one that we have produced. Okay? So this is what is called an exchange argument. Right? We start with some schedule and then we keep moving things around in that schedule, preserving optimality until eventually we transform the given schedule O into our schedule A, which we would get from our greedy strategy. So our strategy processes and schedules jobs in order of deadlines. Right? So we can say that the schedule O the optimum schedule has an inversion, okay, if it actually has two jobs which appear out of order with respect to deadlines. So there is a job I which appears before job J in O, but the deadline of J is strictly before the deadline of I. Okay. So notice that our solution, because the greedy solution processes things in deadline order, there cannot be any inversions in our schedule. But the optimum schedule, the arbitrary optimum schedule that we are presented with may well have inversions. So now the first point is that if we have no inversions, okay, and no idle time, then the lateness must be the same. So now first of all, if we have no inversions and no idle time, then the only flexibility we have is to reorder, because we are not allowed to put things with later deadlines ahead of things with earlier deadlines. The only flexibility we have is to reorder things with the same deadline, right? We might have multiple jobs with the same deadline, and we could pick different sequentializations or different reorderings of these same deadlines. They would not violate inversions because they're equal. Inversion happens only when we have something strictly smaller coming after something that is strictly bigger. Okay. So the claim is that in such a situation we cannot have a different answer because of, even if we allow ourselves to shuffle jobs with the same deadline. So here is a picture. So suppose these three jobs, the blue job, the yellow job, and the red job, all have the same deadline. So here is one sequence where we do blue first, then yellow, then red. Here's another sequence where we do red first, then blue, then yellow. Now they all have the same deadline. So say the deadline is at this point, right? So deadline is here. Now the last of these jobs, regardless of how we shuffle them, will end at the same point, right? Because we have their total, the sum of their times, and that will be the end. And the last job will have among these the maximum delay with respect to this deadline. So since we are counting the maximum lateness, right, the maximum lateness cannot change regardless of how I shuffle these jobs. Whichever job ends last will end at the same time, because all of these are of the same length. I mean, the sum of these are the same length regardless of how I shuffle them, and therefore the lateness doesn't change, right? So in summary, if we have two schedules which have no inversions and no idle time, then the answer in terms of the lateness we produce is the same. So now, if we can claim that there is an optimum schedule with no inversions and no idle time, now recall that our schedule A has this property. So A has no inversions by construction and no idle time. And now we are going to claim that there is an optimum schedule. We are going to start with O, and we are going to produce from this some O prime which has no inversions and no idle time. And by the previous remark, since O prime and A both have no inversions, no idle time, they must actually produce the same lateness. Okay. So how do we do this? Okay. So first of all, we know that we can assume that the optimum schedule has no idle time, because we already said that idle time is useless. We can always shift anything left, compress all the gaps so that there is no idle time. So the first observation is that now we have no idle time. So one part of this requirement is assumed, right? So the only thing that we have to worry about is inversions. So the first claim is that if O has an inversion, then in fact we have an inversion among two consecutive elements, right? There is a pair of jobs I and J such that J is immediately after I, but the deadline of J is smaller than the deadline of I, right? So we have something with a smaller deadline which comes later than something with a bigger deadline. And this is very clear because if there is an inversion, right, then the deadlines normally will keep increasing, and then somewhere there's an inversion, so it comes down, right? So at the point where it comes down, we must have two adjacent things where the bigger one comes before the smaller one. Okay? So whenever we have an inversion anywhere in the sequence, we can find some point where two consecutive items have an inversion. Now the next observation is that we can remove this inversion by swapping these two jobs, right? So if we have I and J which has an inversion, then if we exchange I and J, that is we put J before I, then now D of J is less than D of I and this inversion is gone, right? So it's obvious that we have removed the inversion. But what is not obvious is that this
operation of removing this inversion by swapping these consecutive jobs which are out of order will actually not affect the quality of the solution. So what we need to ask is whether after swapping I and j, we get a solution whose maximum lateness is no larger than that of O. Right? So we have an optimum solution, we have an inversion, an adjacent consecutive inversion. We want to undo this inversion by swapping those two consecutive elements, but we don't want to change the optimality. So this can again be seen by a diagram. So remember that this inversion said that I came before j, but d of j was strictly less than d of I, which is why it was an inversion. Right? So we had this kind of situation. So we had some history, this blue history, and then at this point, okay, we had I and then j. So this is my original, and now I'm going to go from O to O prime by exchanging j and I. Right? So now observe that d of j is to the left of d of I by assumption. Right? So d of j is strictly less than d of I. So now let's look at the lateness of j. So it is from the end. So I plus j take the same amount of time whether I do I before j or j before I. Right? So if I look from the deadline of j up to where j ends, then this length, this lateness must be more than the lateness below. Right? It cannot be less than, because d of I is strictly to the right of d of j. Right? And the endpoint is the same. So if I look at the endpoint and I subtract the deadline point, the deadline point for I is closer to the end than the deadline point for j, because dj is before di. So therefore, by exchanging I and j, not only have I removed one inversion, I have also guaranteed that because of this, so notice that no other job, every other job up to this point ends at the same time, and every job which is after this point also ends at the same point. So no other job has its lateness affected by the swap. The only two jobs whose lateness changes are I and j. But they change in such a way that the overall lateness can only reduce. It cannot increase. So therefore this is a safe swap in terms of preserving optimality. Right? So therefore now we come back to our claim that there is an optimum schedule with no inversions and no idle time. Right? We know that we have an optimum schedule with no idle time because that's a general principle. Now, from the previous argument, we can remove every consecutive inversion without increasing lateness. Therefore, the optimality is preserved. Now, if we have n jobs, okay, even if every pair of them is out of order, we have only n into n minus 2, 1 by 2 inversions to begin with. So we can systematically invert every one of them without affecting optimality until we get an optimum schedule with no inversions and no idle time. And we already saw that any two schedules with no inversions and no idle time must be equivalent in terms of lateness. Therefore, our schedule A, which has this property that it has no inversions and no idle time, has the same lateness as this transformed version of O. And since the transformed version of O has the same lateness as O itself, and O was optimal, our algorithm A also, our solution A is also optimal. So the trick in this problem was to actually prove that the greedy strategy was correct. The implementation and the complexity are very easy to calculate. We just have to sort the jobs by deadline and then read off the schedule in the same order. So sorting the jobs takes n log n as usual, and reading off the schedule just takes order n time because we just have to read off the jobs 1 to n after they are sorted. So overall we have an n log n algorithm. So for the last example of a greedy algorithm in this course, we will look at a problem from communication theory. We will look at the problem of Huffman codes. So when we communicate, we have to transmit information from one place to another place. So we might be working in some language like English, Hindi or whatever, but if we are using computers, for example, to transmit our data, we know that they must send this information in binary strings. So our typical goal is to take an alphabet and then encode it over strings of 0 and 1 so that at the other end we can decode it and recover the message. Right? So if we have, say, the 26 lowercase letters A to Z, then it's easy to see that we need to, if we want to encode each letter as a fixed sequence of zeros and ones of a fixed length, then we will need to use 5 bits per letter, because if we use only 4 bits, we can only get 16 different combinations. So with 5 bits, we can get 32 different combinations. So now a natural question is, can we do something clever about using different length encodings for different letters, so that more frequent letters get sent with shorter encodings, right? So can we optimize the amount of data we actually transfer in order to send a message from one place to another? So this brings us to the idea of having a variable length encoding, where we use different strings of different lengths for different letters in the alphabet. So one of the most famous examples of a variable length encoding is the classical Morse code, which was developed by Samuel Morse when the telegraph was invented. Right? So this was done using a mechanical device by clicking on a contact, and it would produce long and short clicks. So the short clicks were called dots and the long clicks were called dashes. We can as well think of them as representing the bits 0 and 1. So in the Morse code encoding, different letters do have different encodings. Now in English, E is the most frequent letter and T is another very frequent letter. So Morse assigned them codes of a dot, that is 0 for E, and a dash, that is 1 for T. Then Morse picked other frequent letters such as A and gave them 2-letter encoding. So A is encoded as dot dash or 0, 1. Now the problem with Morse's encoding is that it is ambiguous when you come to decoding. So for instance, if we look at the word, the sequence 0, 1, okay, then we don't know whether we should interpret each of these as a 1-letter code and get ET, ET. Or for instance, we should think of this as two-letter codes and get AA and so on. Right? So depending on whether we stop at a 0 or extend 0 to 0, 1, we can get many different interpretations. Now, in practice in Morse code, what used to happen is that the operator gives a slight pause indicating the end of the letter. So therefore, effectively, Morse code is not a binary code, but it's a 3-letter code, 0, 1 and pause. Now, when we are using, of course, digital computers, we don't want to go to 3 letters. So we want to efficiently do this using just 2 letters. So in order to make a variable length code and unambiguously decodable, we need what's called the prefix property. Okay, when we read through a sequence of zeros and ones, we should be unambiguously clear whether we have read a letter or there is more to read. We shouldn't be like the earlier case where we have read 0 and we don't know whether we stop at 0 and call it an E in the Morse code setting, or we want to call it an A, which is a 0, 1. Okay. So we are going to use this capital letter E to denote the encoding function. So E of X is the encoding of the letter X. So here is an example. So we have 5 letters A, B, C, D, E. And now you can check that none of these encodings can be extended to anything. I don't have, if I see 1, 1, it must be an A. There's no other code which starts with 1, 1. If I see 0, 0, it's not a code, but 0, 0, 1 is a code. So 0, 1 cannot be extended and so on. Right? So each of these cannot be extended to be the code of any other letter. So now when we get a long sequence like this, there is no doubt. Right? The first point where I have completed a letter is 0, 0, 1, and this is a C. The next point where I have completed a letter is 3 zeros and it's an E. Then I read another C, and then an A, and then a B. Right? So if we have this prefix code property, that is, no letter is encoded to a string which is the prefix of the encoding of some other letter, then we have unambiguous decoding possible, and this is very important. So our goal is to find optimal prefix codes. So we need to talk about what we mean by optimality. So remember, we said that our goal is to assign shorter codes to more frequent letters. So somehow we have to determine what are more frequent and less frequent letters. Right? So people have measured the frequency of the occurrence of each letter in different languages. So this is a very language specific thing. Right? So this optimality, something which is optimal for English may not work for French or for any other, Spanish or something. So you take a large body of text in a particular language, right? And then you count the number of A's, B's, C's, D's and E's, and then you just look up the fraction. Out of the total number of letters across all this text, how many are E's, how many are B's, how many are C's. So this is a kind of statistical estimate right, of the average frequency of this. So this frequency will be a fraction. What fraction of the letters over a large body of text will be E's? What fraction will be C's? And these fractions will add up to 1, right? Because every letter must be one of them, right? So the fraction of A's plus the fraction of B's plus the fraction of C's and so on is going to add up to 1. And because of this, we can also think of this statistical estimate as a kind of probability. Like if I give you a random letter, if I look at a piece of text and I pick up a random letter from that text, what is the probability that it's X? Well, it will just be the frequency of X across all the text, right? F of X. So these will add up to 1. So now we have a message which consists of some n symbols, right? So we have M1, M2 to Mn, right? So these are my n symbols. Now we know that if I pick a particular letter X, then Fx fraction of these are X, right? So in other words, if I take n and I multiply it by the fraction, so say if Fx is say 1/3, then 1/3 of n, so n by 3 of these symbols will actually be the letter X, right? And now each of these X's is going to be represented by its encoding, right? So supposing it is 0, 1, 0, then each X is going to be represented by 3 bits. So then n into Fx is the number of times I see X, and this into the length of this encoding is going to give me the total number of bits taken to encode all the X's in this message. Now if I do this for every letter, okay, so if I take the summation over every Y or every X in my alphabet of n times the frequency of the letter times the encoding length of that letter. Okay? So this tells me how many bits I need to encode that particular letter. I add up all the letters, I get the total length of the encoded message. Right? And if I don't include this n, okay, because notice that n is not part of the summation, it's an independent thing, it's a fraction of any n. Okay? If I just look at the total weighted average of the lengths of the encodings, then this is, if you studied probability theory, what is called the expected length of the encoding. So this is the average number of bits I use for a letter. Okay? So let's work out how this, so suppose we take our earlier example of 5 letters, now we insert some fictitious information about frequencies. So this, all these 5 values are fractions between 0 and 1 and they all add up to 1. Then if I do this summation over X of f of X times the length of E of X, okay, then I have 0.32 times 2 because the encoding of A is 2 letters. Okay, then I have 0.25 times 2 because the encoding of B is 2 letters and so on. Right? So I have these 5 terms A, B, C, D, E and then I add it up and I get 2.25. Right? So it says that I need on an average 2.25 bits per letter. Of course I can't use 0.25 bits per letter, but what this says is, for instance, that if I have 100 letters, I would expect to see 225 bits in the output encoding. Now a very specific kind of prefix code is the fixed length code, where just by the fact that every code is of a fixed length, I know exactly where each one, so supposing I use 3 bits in this case, if I want a fixed length code of this, then there are 5 letters, so I can't do it with 2 bits because I'll only get 4 different combinations, so I need 3 bits. So if I use some 3-bit code, okay, then every 3 bits will be 1 letter. Okay. So in the fixed length encoding of this, I would use 3 bits per letter, so therefore clearly the number of bits per letter is 3 because I'm using 3 for every one of them. And so by going to a variable length code encoding which takes into account the frequencies, I'm actually saving, instead of sending 300 bits for 100 characters, I'm sending it 225 bits. So you have a 25% saving. Right? So this is what we are trying to get at. So in this example, in the previous thing, we had 2 frequencies, right? 0.2 and 0.18. So 0.18 means D is less frequent than C, but somehow we had assigned C to be a longer code. So this violated our basic principle that shorter code should be assigned to more frequent letters. So if I see a pair of letters which are where one is more frequent than the other, I expected to get a shorter code and I had not done so. So if I invert that, right? So supposing I now assign a 3-letter code to D and a 2-letter code to C, then these 2 terms change. The other terms, though the encoding may have differed, the lengths don't change, right? So then I get, instead of 2.25, I get down to 2.23. Right? So what this says is, by looking at different encodings, I could get different ABL values, right? This average bits per letter. So now our goal is to find an assignment capital E which minimizes this quantity so that our coding is as efficient as possible. So to get to this, it's useful to think of these encodings as binary trees. Right? So in a binary tree, I can interpret the directions as 0 and 1. So typically left is 0 and right is 1. So now if I read off a path in a binary tree, it is also a binary sequence. So this path is 1, 1 on the right, for example. Okay? And this path, for example, is 0, 1. And this path is 0, 0, 0. Now if I read off a path, and then I find a letter at that label, then it's as good as saying is that that path labels that letter, or that letter is encoded by that path. So here, because E has the encoding 0, 0, 0, in the binary tree, I will follow the path 0, 0, 0 and label that corresponding letter, that vertex, by E. Now because it is a prefix code, if 0, 0, 0 labels E, there will not be any code which says 0, 0, 0 and something more. There will not be another label below it. Right? So these labels will not extend to other labels. I will not find an F below D because otherwise it is not a prefix code. I do 1 0 and I get a T, but I do 1 0 something else and I get an F. So the code for F extends the code for D. This is not allowed. Right? So in a prefix code, this cannot happen. So therefore, all the labels are actually at leaf nodes. Right? They are at nodes which have no successors. So here is an encoding for the other scheme that we had, where we exchanged the values of C and D. So now C has a 2-letter code and D has a 3-letter code. So this is indicated by the depth now. The depth is the path, right? The length of the path is the depth of the node. So C in our earlier thing was at depth 3, right? And now it is at depth 2. And likewise, D was at depth 2 and now it is at depth 3, right? So we want to basically put things which have higher frequencies higher up in the tree at lesser depth. So having encoded our or looked at our encoding as a binary tree, we will now make a couple of observations, 3 observations about them, which will be useful to prove and to develop an optimal algorithm and prove it is optimal. So the first thing is that in such a tree, right, if it is optimal, every node will either have no children, it will be a leaf, or it will have 2 children. This is what you call a full tree, right? So every optimal tree is full. Now it's easy to see this because supposing we claim we have an optimal tree in which somewhere in between we had a node which had only one child. Then this child can effectively be promoted. We can remove this node completely and we can shrink the tree along this direction and nothing will change. Except that the depth of the nodes below it will become less. So in fact, we will possibly get a shorter average bit length than we had before. Right? So therefore, by having a singleton, either only a left child or a right child, we cannot be optimal. So every node must have either 0 or 2 children. The next property is exactly what we saw in the earlier thing, which is that if I have 2 nodes x and y, such that x is higher than y, okay, so x is at some level and y is at a different level, then x has a shorter encoding than y. This must mean that f of x is at least as much as f of y. In other words, when I go down the tree, my frequency cannot increase. Because if f of y were bigger than f of x, that if I had more y's than x's in my text, then I would just exchange these two, right? I would find a better encoding by putting y here and x here. Because now if I do f of y times the length of y or the depth of y in this tree, okay, then it will reduce because the depth of y is reduced. And this is a higher multiplier. So therefore, if I had a higher thing below, then I could exchange letters and get a better tree. And that doesn't happen in an optimal tree. So then in an optimal tree, if I go down the tree, I'll only find lower frequency letters. The final property is to do with leaves at the lowest level. So supposing I have a leaf at the lowest level, right? So this is some leaf at the lowest level. So I know because it is an optimal tree that it cannot be an isolated child, it must have a sibling, right? If I go up and come down, it must have a sibling. Now there are 2 possibilities, right? The 2 possibilities are this is a leaf, okay? Or the other possibility is that this is not a leaf. Right? The claim is that if it is not a leaf, then it must have children. So then there are leaves here which are at a lower level than X, but X is assumed to be a maximum depth leaf. Okay? So a maximum depth leaf cannot have a sibling which is not a leaf, because its sibling would then have children which have a higher depth. Okay? So therefore, if I have a maximum depth leaf in my optimal tree, then it will occur as a pair with another maximum depth leaf. Right? So this is a conclusion that leaves at maximum depth occur in pairs. And then we know that because the frequencies keep dropping as we go down, increasing in depth, these pairs must have the lowest frequencies, among the lowest frequencies. So now in order to develop a solution, we will use recursion. So what we will do is we'll say, let us look in the overall table that we start with and pick two letters which have the lowest frequency. So we can assign them the longest codes. So they can be put at the lowest level. And then we know that the lowest level leaves occur in pairs. So let's assume that these will be paired up. Okay? So we will assign these lowest frequency letters X and Y to a pair of leaves at the maximum depth. Left and right does not matter, because it's only the depth that matters. So now the recursive solution will say that, okay, how do I figure out what the rest of the tree looks like? Well, if I have a situation where I have decided that X and Y go here, okay, then I will kind of treat this as a unit and make a new letter called XY and give it the cumulative frequency Fx plus Fy of the old two letters. Right? So I'll construct a new alphabet in which I drop X and Y and I add a new composite or hybrid letter XY, whose frequency is going to be Fx plus Fy. Now recursion kicks in. I have a k minus 1 letter alphabet. Okay, so I will recursively find an octaval encoding of that. Now, before coming to how to adapt the solution, the recursion ends when we have only two letters. For two letters, the optimal solution is to build a tree which has exactly two leaves labeled 0 and 1 as the path. Right? So this is the base case. So if I have more than two letters, I will recursively construct a tree for the smaller thing, and then I will come back, and now in the tree that I constructed, I will have somewhere a leaf labeled XY. Now XY is not a letter, so what I will do is I will replace this by two new leaves called X and Y. So I will go from the tree over A prime to a tree over A by doing this. Okay, so this is an algorithm developed by Huffman, and this type of coding is called Huffman coding. So let's look at this example that we had earlier. Right? So here the two lowest frequency letters are D and E. Right? So we merge them into a new letter DE, and this is a frequency 0.23 because it's 0.18 plus 0.05. Now these two are our two lowest letters, so we merge them and we get a new letter CDE of cumulative frequency 0.43, which is the sum of all the frequencies of the components. Now it turns out that these two are the smaller two, so I merge them into a letter AB. And now I have reached my base case where I have exactly two letters. So I can set up a trivial tree for these two letters labeled 0 and 1. Okay. And now I work backwards. So the last thing I did was to merge A and B. So now I will take this AB thing and split it up as A and B. Right? So I will split AB as A and B and I will get this tree. Then the previous step was to combine CDE into C and D. So I'm going to split this up as C and D. Okay. And finally I'm going to split this up as D and E. Right? So this is how Huffman's algorithm works. Right? By recursively combining the two lowest frequency nodes and then taking the composite node and splitting them back afterwards. So to show that this algorithm is optimal, we will go by induction on the size of the alphabet. Now clearly when I have only two letters, I can't do any better than assign one of them 0 and one of them 1. So the base case is optimal. So we will assume that this is optimal for k minus 1 letters and now show that it's also optimal for k letters. So recall that we went from k to k minus 1 by combining the two lowest frequency letters as one, constructing an optimal tree for this smaller alphabet, okay, and then expanding the xy to get a new tree. So the claim is that when I go from the tree over k minus 1 letters to the tree over k letters, the cost is going to increase, but this cost is going to be fixed
by whichever letters I chose to contract. So if I chose x and y to merge to go from t to t prime, then the amount by which the average bits per letter is going to change is exactly the frequency of this combined letter fxy. Right? So it's deterministically fixed by which one I chose. So even though I don't know the cost of the trees directly, I can tell you that the cost is going to be different by this amount. This is not very difficult to prove. Okay, so in that summation that we had, so in the tree notation, remember this depth of z is the same as the length of the encoding of z, because the depth exactly reflects the length of the string used to encode it. So this is our ABL calculation. Now for every node other than x, y and xy, they are exactly at the same position in t and t prime. So the summation, the terms don't change. So the only changes are between these three nodes. So what I will do when going from t prime to t is I will remove this contribution of the composite letter xy. Okay, and then at the next level, which is 1 plus the depth of the xy, I will add the node fx and I'll add node fy, so I'll get the combination of fx times that plus fy times that. Right, so I'm subtracting this amount on the left, and then I'm adding this amount on the right. So now, actually, f of xy is nothing but fx plus fy. So this left-hand side term is actually this right-hand side component, depth of xy times fx plus fy. So I'm subtracting this and adding it back, so they cancel each other out. Okay? So therefore, all I'm left with is 1 times fx plus fy, which is fx plus fy or fxy. Right? So therefore, in going from t prime to t, the crucial thing is it only depends on which letters I have contracted. That fixes the difference uniquely. Now, let's assume that we know how to solve all k-1 size alphabets efficiently, and we have done this recursive thing to construct a tree T for size k. Suppose there's another strategy which produces a better tree for size k. Okay? So there's another tree, candidate tree S, produced by some different strategy, whose average bits per letter is strictly better than the one that we construct recursively. Now in S, we know for sure that these two letters that we use in the recursive construction, x and y, okay, so they occur somewhere at the bottom of this tree. Okay, so this is my tree S. Okay, so these must be leaf nodes because they have the lowest probability, lowest frequencies over all the letters, so they must be at maximum depth. But they may not be next to each other. But it doesn't matter because since they are both at maximum depth, I can move them around. At this depth, I can move letters around. I can reassign them to other leaves at the same depth, such that I come with a configuration. I come to a new S. I call it S again, where I actually have X and Y together. Okay, so I can assume that the S that has this optimal property, which is better than the T I constructed, actually has X and Y as sibling leaves at the maximum depth. Now what I'm going to do is in this S, I'm going to concretely fuse this and get an S prime. So this S prime will be over k-1 letters, except instead of doing it by a recursive call, I'm actually taking a concrete tree over k letters and I'm actually compressing two nodes into one and calling it a tree over k-1 letters. But because this is over k-1 letters and this represents an encoding, okay, it cannot be any better than the encoding that I recursively computed for k-1 letters because I assumed by induction that my algorithm works efficiently for k-1 letters. So S prime is no better than T prime. But S prime plus f of xy is S. T prime plus f of xy is T. Right? So the difference between T prime and T and S prime and S is exactly the same. So if S prime is no better than T prime, then S cannot be any better than T. Right? So it was a contradiction to assume that S was strictly better than T. So this proves that our strategy of recursively computing T is optimal for all k. A word about the implementation. Okay, so what we have to do is k-1 times we have to merge these two minimum values and compute a recursive solution. Right? So the bottleneck is finding these minimum values. If we use an array, then as we know, we'll have to scan the array each time to find the minimum values.
remember that the minimum values keep changing. I can't sort it once and for all because each time I combine two letters, I introduce a new letter into my array with a new minimum value which was not there before, or not a new value which is not there before, which may or may not be the minimum. So at each stage I have to find the minimum. So it's an order k scan each time, right? It's a linear scan, and I do this about k times, so I get order k square. But it should be fairly clear to see that this bottleneck can be got around by using a heap, because that's precisely what heaps are good at, finding the minimum, right? So if I maintain the frequencies not as a simple list or array but as a heap, then in order log k time I can find the minimum values, and then I can insert back the new composite letter also into the heap in log k time. So each iteration takes only log k, and so I improve from k squared to k log k. So recall that we mentioned at the beginning that this is going to be our last greedy algorithm. So why is this greedy? Well, because every time we make a recursive call, we are deciding to combine two nodes into one. And the two letters we choose are always the ones with the lowest frequencies. Now, what is to say that we could not do better by choosing the lowest and the third lowest, for example? But we never tried. Okay, we only tried the lowest and the second lowest. So we make a locally optimal choice, and we keep going with this choice, never going back to revisit it, and finally we get a global solution. Now we have proved that this global solution is actually optimal, and we have to do that because there is no other reason to expect that by making this short-sighted choice at the current time, take the two worst frequencies and combine them, that you are always going to get the best solution. So this is very much a greedy strategy. So finally, a brief historical note. So Claude Shannon is the father of information theory, and when they were looking at these problems around 1950 or so, so they were faced with this problem of finding an efficient encoding. So Shannon and Fano proposed a divide and conquer thing. So what they said was, okay, let us look at the encoding of the alphabet. So some of them are going to start with 0 and some of them are going to start with 1. Right? So everything which is in the left subtree of this coding tree that we construct is going to have a code of the form 0 something something. Everything on the right is going to have something of the form 1 something something. So it seemed intuitive to them that a divide and conquer strategy is good. What if I put letters on this side such that they occupy roughly half the frequency weight of the total alphabet? That is, if I take the frequencies of all the letters whose encoding starts with 0, their frequencies add up to roughly half, and the other one also to half. So I split the alphabet into two of equal weight, assign some of them to start with zeros, the other to start with 1, and then I recursively solve this. Right? So I partition A as A1, A2. The sums of the frequencies in each of the sets are roughly equal. Solve them recursively. Unfortunately, this is not guaranteed to generate an optimal encoding. Right? So you can come up with examples where you can do this, and then you will end up with something which you can improve by doing some other thing. So it turned out that Huffman was a graduate student in a course of Fano. He heard about this problem and he thought about it, and after a few years he came up with this clever algorithm which we have done today. So in the next few lectures, we will look at a very powerful technique for designing algorithms called dynamic programming. So the starting point of dynamic programming is to consider what we would call inductive definitions. Now there are many very simple functions which we come across which are inductive. So we all know that mathematically n factorial is n times n minus 1 factorial. Right? So we can write an inductive definition of factorial as follows. The base case, okay, is when n is 0, and in this case the factorial is 1. So f of 0 is 1. And in general, if we have n greater than 0, then f of n is given by n times f of n minus 1. In other words, we express the factorial of n in terms of the same function applied to a smaller input. Now this kind of inductive definition is not restricted only to numeric problems. You can also do it for structural problems. So for example, in a list or an array, you can consider a sub-list or a sub-array as a smaller problem. So here is a very simple way of describing insertion sort. So if I want to sort n elements, right, then the way insertion sort does is that, of course, if there is nothing to sort in the base case, then we are done. Otherwise, we look at the rest of the list starting from the second element and we recursively sort it, right? And then we insert the first element into the sorted list. So the insertion sort applied to x1 to xn requires us to insert the value x1 in the recursively sorted x2 to xn. So again we are applying the same function that we are trying to define to a smaller input, and in the base case, the smallest input, namely the empty one, we have an answer which is readily available to us. So one of the attractions of having inductive definitions is that they yield in a very natural way recursive programs. So we don't have to think much. We can almost take the inductive definition and directly translate it as a program. So here is a translation for factorial which more or less reflects the structure that we had before. Remember the structure that we had before that was that f of 0 is equal to 1 and f of n is equal to n times f of n minus 1. Right? So we say if n, now just to make it a little more robust so that people give negative numbers, we give sensible answers. Instead of just checking n equal to 0, we can just check for any value 0 or less, we will just return 1. Right? If somebody asks us for factorial of minus 7, we are just going to return 1. But the expected thing is that they will start with 0. And then if they give us a positive number which is bigger than 0, then we will go to the recursive case. So we will compute factorial for n minus 1, multiply by n, and then return this answer. Right? So there's a very direct one-to-one correspondence between this inductive definition and the recursive program, and that's what makes inductive definitions very attractive from the point of view of describing a function, because the inductive definition can be mathematically justified, and then the program is obviously correct, obvious in quotes, because it follows directly from the recursive or the inductive definition. So what such inductive definitions exploit is what is sometimes called the optimal substructure property. So what this complicated phrase means basically is what you expect from an inductive definition, that is, you solve the original problem by combining solutions to subproblems. Right? So the solutions to the original problem are derived in terms of solutions to the subproblem, and in particular if the subproblem is the same type, then it's computing the same type of answer. Now in a numerical question like factorial, it doesn't make sense to say something is optimal. But for example, when you're doing insertion sort, then certainly when you sort the sublist, the result of that is what you want for that sublist. Okay? So this gives rise to the notion of a subproblem. Right? So factorial of n minus 1 is a factorial subproblem of factorial of n, obviously. But it just so happens that factorial of n only required factorial of n minus 1. Now we could have problems which require more than one immediately smaller subproblem. For instance, factorial of n minus 2 is also a subproblem. N minus 3 is also a subproblem, and so on. Right? So any smaller input can be treated as a subproblem of the original thing. Likewise, when we actually do insertion sort, we give it the input x1 to xn and we ask to sort x2 to xn. Right? So this is the subproblem which is directly part of the statement. But in general, one could think of any segment xi to xj to sort as a subproblem of sorting. Right? This would happen, for instance, in something like merge sort or quick sort, especially in merge sort, where you break up the array into halves and then into quarters and so on. So at any given point, you're applying the same algorithm to some segment from ai to aj. So now let's look at a problem that we have seen before, okay, in the context of greedy algorithms. So we looked at this problem called interval scheduling. So interval scheduling said that we had a resource which is available over a period of time, right? And now people will come and make bookings for the resource. So somebody may want to book it during this segment, somebody else may want to book it during this segment, somebody else may want it during this segment, and so on. Now during these overlapping things, you cannot give the resource to two people, right? So you are given a set of requests, each with a starting time and an ending time. So we have a start and an end or a finish time. And now what you want to do is decide which of these requests you can allocate so that the maximum number of bookings are actually granted. Right? So the goal is to maximize the number of bookings, not the length of the bookings, but the number of bookings. So in this particular case, what happens is that when you honor a booking, now if a booking happens to be overlapping with a few other bookings, okay, then if I decide to take this booking, then this goes away, right? So these two bookings which overlap with it can no longer be scheduled because they conflict with this in some time interval. So therefore now we have to solve or find a way of allocating the remaining bookings for some subset of the bookings, right? So each subset of the bookings
is a subproblem in this case. And the strategy that we saw was a greedy one, which said to pick the one which has the earliest finishing time. Right? So among all those bookings which are still available to us to allocate, we pick one in a greedy way by just looking at it among all those that remain the earliest finishing time. Now this, as we said, when we add, will eliminate some bookings which are in conflict. That gives us a sub problem, and we will solve this sub problem. Right? So how many sub problems are there? Now we have n bookings, and every possible subset of this is a sub problem. So we have an exponential number of sub problems. Right? In general, we have any possible subset could be our answer. So we have to look through all these exponential things in principle in order to find the best allocation, the one that gives the maximum number of bookings to be satisfied. Now what our greedy strategy does is effectively it cuts down this exponential space into a linear space, because what it does is it will pick, so we have initially bookings 1 to n, then it will pick among these, let's assume they are actually sorted by order of the earliest finishing time. So you will take the first one and then you will rule out a few from there. Okay, and now you will have some remaining, and then among those you will pick the earliest one. Okay, and then you will rule out a few more and so on. So at most you will allocate all n of them, but at each time once you include one, you will rule out a few. So certainly in a linear scan you would look at only that many subproblems. So you would only look at order n subproblems and find what you claim is an optimal answer. And since you are doing such a drastic reduction from 2 to the n to order n, obviously there is a question as to whether you have overlooked some subproblems accidentally by not examining them at all. So you need a proof, right? So that's why in a greedy strategy, you need to prove that what you are doing actually makes the solution come out to be correct, because you are really not looking at a large number of, you're not considering a large number of subproblems. So suppose we change the interval scheduling problem very slightly. Okay? We associate with each request a weight. Okay? A weight could be, for example, the amount somebody is willing to pay. Okay? So maybe people are trying to book. So we have an auditorium which we rent out for performances and other activities. And people who come to use it are willing to pay to use it. Of course, there is only one auditorium, so two people cannot use it at the same time. Now our earlier goal was to maximize the number of bookings that we gave, but now we have another criterion which is more immediate, which is how much each person is willing to pay. So even if we give it to only one person, if that person is paying a lot more than everybody else, then that would be optimum for us, right? So now our aim is to maximize the total weight, right? So we want to get as much revenue as possible from our allocation, right? Not the number of bookings, but the total weight. So recall the greedy strategy in the earlier case, we wanted the earliest finish time. Right? So if we saw this particular selection of three requests, then the earliest finish time would be this one. Right? So we would first take this, that would rule out this, and then because the third job starts or third request starts after the first one completes, so we will take this, and so we will get 2 bookings. Okay? And this 2 out of 3 is the best we can do, and that was fine in the unweighted case. Right? But now unfortunately what we have is that we have a weight, right? So we have this weight associated with this. So we have to do something a little more clever, because now if we choose the first one and the third one, then the total weight is only 2, right? So job or not job, but let's call it booking 1 plus 3 gives a weight of 2, whereas booking 2 alone gives a weight of 3 because it has a weight 3, right? So ideally in this situation we should recognize that the middle request has enough weight to overcome the penalty of it being the only one that will be scheduled. So though we only get 1 out of 3 requests scheduled, we actually get a maximum benefit from the cost perspective. Right? So therefore what this means in other words is the greedy strategy which we proved for the unweighted case is not valid anymore, unfortunately. So what shall we do? So one strategy is to see, is there another greedy strategy? we can search for another greedy strategy and try to argue that it works. And arguing that it works, as we saw, is rather, it takes a little bit of effort because we have to use an exchange argument or some such thing to prove that it is better than any solution that you could get by any other strategy. So the other approach, which is what we are going to look at in more detail in the next few lectures, is to try and look for an inductive solution which is obviously correct but which can be evaluated efficiently, right? So the goal is to save. So what we are going to save is this effort in proving that by looking only at a few cases we are actually producing an optimal answer. We will in some sense look at every case, but we will look at every case in a clever way, right? And that's what we are going to do. So how do we do this for this problem? Okay, so this time let's do something which is more direct than what we did last time. Instead of looking at the earliest finishing time, just look at the earliest starting time. So let's assume that our tasks are, or our requests are all ordered like this. Right? So we pick them up in this order. So we will begin with the first booking, which you call B1. Okay? Now observe that in the final answer, either B1 is there or B1 is not there. Okay? So we will take two options, right? So yes, B1 and no B1. Now if we eliminate B1, right, then our subproblem just consists of B2 onwards. Right? So we just have a subproblem which says B2 to Bn. So if we exclude B1, then we just use B2 to Bn. Right? So exclude B1 means just throw it out and pretend you only had n-1 jobs to begin with. On the other hand, if you include B1, then you have to be a little bit careful, right? Because now if I include B1 in this particular thing, right? So if we include B1, then we have to rule out something which is in conflict, right? So we eliminate all the conflicting requests as we did in the greedy case, and then we have another subproblem which is not necessarily B2 to Bn, it will be some subset of B2 to Bn, right? But we have now taken both options. We have included B1 and excluded B1, so it's more reasonable to expect that we have either a solution with B1 or without B1. There's no third option. The solution either has B1 or doesn't have B1. We are trying to evaluate both, and then we are trying to choose the best one. Right? So this is an inductive decomposition of the problem into two subcases with B1, without B1. We are not making any predictions about which is better. We evaluate both and take the better one. Okay. So now let's argue that this kind of strategy actually considers all the options. Right? So just like B1, for any Bj, right, the solution either has Bj or does not have Bj. Right? This is very clear. So there are 2 to the n possible solutions, right? I could either have B1, not have B1, have B2, not have B2, right? So I can try every possible subset. That would be a brute force argument. We want to avoid having to try every possible subset. Now, for B1, we have clearly checked both cases explicitly. What about B2? Can we be sure that we are checking all cases of B2? Okay, so let's look at B2. Now, if B2 and B1 are not in conflict, that is B1 and B2 are in disjoint intervals, then whether or not B1 is chosen is independent of whether or not B2 is chosen. This means that whether we choose B1 or B2, the resulting subproblem would still allow us to choose B2, right? So whether we choose B1 or B0 at the B1 or not B1 at the beginning, right, it will be considered in both subproblems. And when we solve that, we will take both choices. On the other hand, if B1 and B2 are not compatible, that is B1 rules out B2 or because they overlap, then when B1 is chosen, B2 cannot be there. Right? So B1 can be there only if B2 can be there only if B1 is not there. So when B1 is chosen, we will not consider B2. But when B1 is not chosen, remember that we get the resulting subproblem of B2 to Bn. Right? So again, B2 will be chosen or given a choice. Right? Therefore, B2 we will consider all options in the presence or absence of B1. Likewise, we can argue that B3 will be considered in the presence or absence of B1 and B2. And what is happening is, as we are going along making more and more commitments, we are ruling out a lot of incompatible combinations which we would otherwise blindly consider if we did 2 to the n. Okay, now we still have to evaluate this efficiently, but at least it is not that difficult to believe that we are actually trying out every possible option. We are not in advance deciding that some local criterion like in a greedy strategy is enough to rule out certain subproblems as being useless. So the computational challenge comes from the fact that the subproblems that we generate may appear again and again. So let's look at a simple case. So supposing we have the picture that is shown below, right? So we have B1 and B2 which are in conflict, okay? But notice that both B1 and B2 are compatible with everything that comes afterwards, right? So if we choose B1, then we have to rule out B2, and so the subproblem we get is B3, B4 up to Bn. On the other hand, if we rule out B1 as we said before, you will try out everything that remains, namely B2 to Bn. Now what happens when you try B2 to Bn? Okay. So now when you come to B2 to Bn, you have to discard B2 or you have to keep B2. So supposing you discard B2, then what happens when you discard B2 from here? You precisely get the remaining part, which is B3 to Bn, right? So you again generate a B3 to Bn problem, which you had already asked once in the context of choosing B1, right? So we now have that you have choose B1, say yes, no. Right? If you choose B1, I get this problem which is B3 to Bn. Then if I choose no, then I get a chance to choose B2. Again, yes, no. Okay? And now if I don't choose B2, then I discard B2, again I get B3 to Bn. Right? So I will be solving this problem once here and once here unless I do something clever. Right? So the whole problem with this approach is that the inductive solution can give rise to the same problem at different stages. And if we just use recursion, as we said before, one of the great benefits of having an inductive definition is that you can just write a recursive solution which just mirrors the inductive definition of the problem. But if you do it naively, every time you come to the function to be done inductively, you will recursively call that same function even if you have done it before. And this can be very expensive, as we shall see. Right? So the goal of dynamic programming is to avoid this wastefulness. Right? So there are two techniques that we will see. There is a technique called memoization, which is a way to build in some cleverness into recursion so that you never call the same function twice recursively. And dynamic programming will then be a way to avoid doing this recursive calls altogether. So dynamic programming is a way to enumerate the subproblems directly and solve them, knowing that the subproblems have some dependencies which you can predict. Okay, so we will look at these two techniques in the next couple of lectures and look at several examples to get familiar with these notions of memoization and dynamic program, which are essentially ways of making inductive definitions and the corresponding recursive implementations efficient to solve. So let's continue our discussion of inductive definitions. So recall that functions like factorial and insertion sort have natural inductive definitions in terms of smaller subproblems. And the attraction of looking at inductive definitions is that we can very easily come up with recursive programs that implement them in a very obvious way. But the challenge is in identifying the subproblems and making sure that they are not overlapping. So in the case of factorial, remember that any smaller input to factorial will be a subproblem. Similarly, for sorting, you can think of any segment of the list to be sorted as a subproblem. And in general, we are looking at recursive solutions or inductive solutions where the solution to the function f we are trying to define is derived by combining solutions to the subproblems of this original problem. And so we compute f on smaller inputs than y. So let's see how this works with a very familiar series that you may know of called the Fibonacci numbers. Okay? So let's define the Fibonacci numbers as follows. The first two Fibonacci numbers are 0 and 1. And then every successive Fibonacci number is obtained by adding these two. Now it is instructive to see, even before we begin, how we would enumerate the Fibonacci numbers. So we know that the first two are 0 and 1. Right? And then you know the next one is the sum of these two, so the next one will be 1 again. Next one will be 2, because it's 1 plus 1. Next one will be 3. Next one will be 5. Next one will be 8. Next one will be 13, and so on. Right? So it's very clear that though these numbers have an inductive definition, right, and there is an obvious recursive function that goes with it, which I'll just mention in a minute, there is a very efficient way of enumerating these numbers directly, almost in linear time. So how does the definition of the function go? Fibonacci of n just says if n is 0, return 0, if n is 1, return 1. So if n is 0 or 1, the value is n itself. Otherwise, you compute value recursively using this criterion, Fibonacci of n minus 1 plus Fibonacci of n minus 2. And finally, whatever value you have computed, you return. So where is the catch? So let's see how this would work on a small input like we just saw, Fibonacci. So we just saw that Fibonacci of 5 is 5, right? We know that we start with 0, 1, 1. So these are the arguments, right? So the values are 0, 1, 1, 2, 3, and then 5, right? So we are trying to compute this fifth Fibonacci number, which we computed very fast. Okay, but let's see how this recursive thing would actually work. So if I call Fibonacci of 5, recursively it would ask me to compute Fibonacci of 4 and 3. Fibonacci of 4 in turn will ask me to compute 3 and 2. Now 3 in turn will ask me to compute 2 and 1. Then 2 in turn will ask me to compute 1 and 0. Now fortunately for 1 and for 0, I have a base case, so I will get those values 1 and 0 respectively. So since I've got 1 and 0, I'll now be able to compute Fibonacci of 2 as a sum of those, and I will get the answer 1. Now when I turn to Fibonacci 1, again it's a base case, so I get the answer 1. So now I have both the answers required for Fibonacci of 3, so I get the answer 2. Now I go back and I compute Fibonacci of 2, but remember I've already computed it, but because I didn't make note of this, in some sense I'm blindly doing recursion. Fibonacci of 2 will again ask me to compute Fibonacci of 1 and 0, which will again produce the base case as 1 and 0. So I will again compute Fibonacci of 2 as 1. And now with both Fibonacci of 3 and 2 available, I will get the answer of Fibonacci 4 as 3. And now I will go back and compute Fibonacci 3 yet again. Right? So I will do this whole tree again. 3 calls 2 and 1, 2 calls 1 and 0. These return the base case. That gives me a value for 2. 1 returns the base case. This gives me a value for 3. And finally, after all this, I get the value Fibonacci of 5. Right? So the problem we can see is that functions like Fibonacci of 3 have been computed twice in full complexity. Other functions like Fibonacci of 2 have been computed 1, 2, 3 times, and so on. Right? And of course, Fibonacci of 1, though it's a base case, has been called several times 1, 2, 3, 4, 5 times. And Fibonacci of 0 has been called 3 times. Right? So this is the big problem with this recursive computation, that we seem to be computing too many things. See, ideally, in order to compute Fibonacci of 5, I know I need 4, 3, 2, 1 and 0. Right? So I need only 6 values totally to be computed, and I'm making a lot more than 6 computations in this. So the crux of the problem is that there are these sub-problems which arise in different contexts within this recursive computation. So Fibonacci of 3 is generated both by the original call to Fibonacci of 4 and the nested recursive call to Fibonacci of, so the original call to Fibonacci of 5, sorry, and the nested recursive call to Fibonacci of 4, right? So we have this entire tree of computation which is duplicated. And because of this kind of wasteful recomputation, overall the computation tree grows exponentially. Right? So you will actually find in general that in order to compute the nth Fibonacci number, you actually do some exponential in n steps. Even though we can see that you can just compute the nth Fibonacci number in linear time. We just saw it, right? You just computed as 0, 1, 2, 3, 4 and so on. So one way to get around this is to make sure that you never re-evaluate a subproblem. So you build up a table, which is sometimes called a memory table. And what does this table do? It just keeps track of every value for which you have computed the function before. Right? So it's just a lookup. In a language like Java, it could be a hash map, or a language like Python, it could be a dictionary. Every time you call f on a value x, you just store x comma fx in this table so that you can look it up and see if you've already computed it before. Right? So it's called memoization. Okay? So this term memoization comes from the word memo, which some of you may have heard. So a memo is a note, okay, which reminds you of something or reminds somebody else of something. So a memoization, or a memo table or a memory table is supposed to remind you that the value you're trying to compute has already been computed. Okay, so how does memoization work? So we have this memo table here, right? So this is our memo table. So in this memo table, Okay, it's just a table where we'll keep different value of k and fib k as we compute them. Right? We assume that we have computed nothing. We don't even know the base case. We are just going to apply the recursive definition, but every time we compute something, okay, we will first look up the table before we compute it recursively. And if we have to compute it recursively, then we will store each newly computed value back in the table. Right? So let's start as before. We wanted to start by computing Fibonacci of 5. So the recursive definition says that we should call Fibonacci of 4 and 3. Now we go to 4, we are just doing this recursion left to right. So 4 will call 3 and 2. 3 will call 2 and 1. 2 will call 1 and 0. At this point, we try to evaluate Fibonacci of 1 for the first time. When we evaluate Fibonacci of 1 for the first time, we hit a base case and it tells us that this value is 1. So we will return this value, but we will also store it in the table, right? So now we have made our first entry in the table. It says Fibonacci of 1 is 1. Then we look at Fibonacci of 0. And again, it's a new value. We get it from the base case, but we have never computed it before. So now we have computed it by computing the base case. And again, we put an entry in the table saying Fibonacci of 0 is 0. So with this, as before, we have got Fibonacci of 2. So up to this point, we have not saved anything, except that we have also now, because we have computed Fibonacci of 2, we have added to this. Every time we get a new value computed, we put it in the table. Now to continue with Fibonacci of 3, I need to go back to Fibonacci of 1. Of course, it is a base case, but what my table thing tells you is that you should look at the table first. Right? So we go down the table. Hopefully it's organized in some efficient way, but in the worst case, let's just naively scan it. We look, have I ever done Fibonacci of 1 before? And it says, aha, I have done Fibonacci of 1 before. So it will look up that value without calling the base case, without looking at the function definition, and just return Fibonacci of 1 is 1. So we have indicated by turning it orange that this call was actually returned from the table. It didn't actually require a computation. So now that I have 1 and 1, Fibonacci of 3 is now 2. So now I have to continue with Fibonacci of 4. So I now have to call Fibonacci of 2 again. So now it will go down and say, have I ever seen Fibonacci of 2? And it will say, aha, I have. And therefore, without doing the recomputation, it will look up this memo table. And again, we mark it as an orange value because it came from the table. It returns the value 1 which we stored in the table. So now having computed this, we've got Fibonacci of 4. So we compute Fibonacci of 4 to be 3 from the recursive definition. And then again we store it in the table. So every new value that we compute, we store in the table. Whether we are going to use it again or not, we don't know. But if we want to use it again, it's good to have it there. Right? So we just blindly put everything that we ever compute back into the table for future use. Now we come back to the top. So Fibonacci of 5, we have got the left branch. We need the right branch. We go to Fibonacci of 3. Earlier we had blindly reproduced this entire tree at the bottom in order to get Fibonacci of 3. But this time we are smarter. We go down the table and we find that 3 has been computed before and the value is 2. So we get this value of 2. And now we have both the answers that we need for Fibonacci of 5. And so we get Fibonacci of 5 is 5. And again we put it in the table, although in this particular case we are not going to use it because the computation is over, but it could be part of a bigger computation, so we just keep doing this. So what you can see in this is that the computation tree, which used to be exponential, is now linear. Now why is it linear? Because every value which is in blue occurs only once. Okay, and every value which is not in blue is a lookup in the table, so it costs nothing. Okay? So therefore, we have now made, so this more or less this memoized Fibonacci is what we do, although we do it in a different order when we actually compute it by hand. So just to see what the memoized Fibonacci looks like. So the green code is what we wrote earlier. Fib of n, if n is 0 or 1, set the value to n, else set the value to fib of n minus 1, fib of n minus 2 and return. So now we will introduce the memo bits, which are the red ones. So we have a table which we will call fib table, whose values are indexed by the position. Right? So fib of 6, if I compute, it will go into fib table 6. So when I get an argument to fib, the first thing I do is I look whether fib table has an entry for that. So if fib table of n exists, return whatever it says. Okay? If it doesn't exist, then we compute it. Now once we have computed it, before we do anything, we put it back in the table, so that next time we will not compute it again. Right? So every new value is put back in the table and then we return it. So when we return a value here, it has been computed for the first time, but it has been stored in the table. So the next time I get the same n, I will come here and I will exit at this point. Okay? So this is our memoized Fibonacci. It just has a very simple check for the table at the beginning, and when you compute the value, it puts it back. So this is a very simple thing that you can do. You can do this for any function. So supposing you had some recursive function or inductive function with 3 arguments, then you would just have a table with 3 indices. So let us call it F table. So computing F. So you have some inductive way of computing the value from the subproblems. So first you look up, have I ever seen this X, Y, Z before? If so, just return it. Otherwise, compute a new value for this given X, Y, and Z in terms of the recursive definition from the inductive structure of the problem. Having computed it, put it back in the table, okay? So that you never have to compute it explicitly again. And then you return. Right? So this is a generic scheme which can be applied to any recursive function that you might write. The only thing you have to do is you have to make sure that you can design a table with the appropriate lookup and look it up efficiently, because if you spend a long time looking up the value in the table, then that's lost. So if you can make it a kind of array lookup, that's ideal. So this is memoization. So the other term that we introduced in the last lecture is dynamic programming. So what dynamic programming does is it tries to eliminate the recursive part of evaluating an inductive definition. So in memoization, what we do is we evaluate the inductive definition recursively exactly as we would normally. The only thing is we keep a table which helps us to avoid having to compute the same thing twice. In dynamic programming, you anticipate what the table should look like and how the values in the table depend on each other. Okay? So supposing we are computing Fibonacci of 5, then by some simple analysis of Fibonacci, we know that if Fibonacci of 5 requires anything at all, it requires things smaller than it. And the smallest thing you can get is Fibonacci of 0. Therefore, from Fibonacci of 5, we immediately know that the subproblems that could be of interest to us are all subproblems between Fibonacci of 0 and Fibonacci of 5. Okay, Fibonacci of 5 is not going to require Fibonacci of 6, 7, 8, nor can we call Fibonacci with a negative number because it's not defined. So there's a very small and finite set of values which we need to consider. Now the next observation is that we can compute the dependencies from the problem structure. This is from the inductive definition. So Fibonacci of 4 is equal to Fibonacci of n is n minus 1 plus n minus 2. So 5 depends on 4 and 3. So I would say that there is, in order to compute 5, I must have first computed 4 and 3. So I will draw an arrow from what it depends on to what it is. So 5 depends on 4, 5 depends on 3. So I put an arrow from 4 to 3 and 4 to 5 and 3 to 5 saying that there is this dependency. In turn, 4 depends on 3 and 2, and 3 depends on 2 and 1, and 2 depends on 1 and 0. And of course 1 and 0 are the base cases and they don't depend on anything. Right? So the dependencies will form a DAG. Why do they form a DAG? Well, it's quite obvious they must form a DAG because if there are cyclic dependencies, you can't compute one before the other. Right? So it's a very natural thing in any kind of dependencies, whether it is dependencies between tasks, as we saw when we did DAGs to begin with. There are many, I have to do something before I do something else. This is precisely that. Right? It's saying that if I cannot compute Fibonacci of 2, I cannot compute Fibonacci of 3 because it has to be done first. Now that I know these dependencies, right, I can now enumerate them in any topological order such that when I reach a value to be computed, everything it depends on is known before. Right? So for example, here a natural order would just be of course 0, 1, 2, 3, 4, 5 because both of these are now elements with no incoming edges. So I can either start my topological order with 0 or with 1. Okay? So let's assume I start with 0. So I know that Fibonacci of 0 depends on nothing. It must be a base case, so I fill it in. Likewise, I know that Fibonacci of 1 depends on nothing, so it's a base case, so I fill that in. Okay, so at this point I've done both of these. Now since I've done both of these edges are gone, so there's nothing pointing into 2. Right? So this is just topological sort, the basic topological set is also gone. So 3 still has a dependency, namely 2, but 2 has no dependencies anymore because both 1 and 0 are available. So I can fill Fibonacci of 2, then fill in Fibonacci of 3, 4 and 5. And this is exactly what we did earlier when we tried to compute Fibonacci by hand. Right? So what we were actually executing when we were writing off the Fibonacci numbers left to right by just looking at the previous two and computing the next one is actually what is called dynamic programming. So dynamic programming for the Fibonacci function just consists of iteratively filling up the table. You start with the value 0 and 1, and then for 2 to n, and of course if I is if n is less than this, we will not go through this iteration at all. For 2 to n, we fill up the ith entry from the I minus 1th entry and the I minus 2th entry, but then as we saw before, these two values occurred earlier, so they were already filled. Okay? So I have converted my memo table filling from a recursive computation, filling on demand as it were, to filling blindly from beginning to end, which is dynamic programming. So to summarize, we have seen two strategies to make recursive computations of inductive functions more efficient. The first is memoization. So what memoization does is whenever it computes the value of the function in a subproblem, it puts it into a table. And before it calls the function recursively to compute a value, it will look up the table to see if this value has already been computed. So the same value is never the same computation, never happens twice. In dynamic programming, on the other hand, we analyze the problem structure to identify the subproblems. And we know that this subproblem structure satisfies a DAG. Okay, the dependencies must form a DAG, because if it's not a DAG, then we'll have cycles and things will not be able to solve anyway. And having done this, what we get from dynamic programming is iterative evaluation. Okay? So this is actually in practice a big saving, because in most programming languages there is a hidden cost to recursion, because every function call actually requires a certain amount of operating system and programming language bureaucracy, some administrative work to to declare some memory on the stack and so on. And this is avoided completely in a dynamic programming solution. Right? So it is a big saving to be able to remove, even though memoization is going to give us an optimum number of recursive calls required for a given problem. It's not going to call anything twice. Okay? It will still involve recursive calls, and recursive calls can be expensive in their own right. For the sake of algorithms, we typically treat function calls as kind of unit cost operations, but in practice it's not the case. So dynamic programming can be a huge saving, because it actually converts an optimized recursive thing into an iterative scheme. So continuing our discussion about efficiently computing recursive functions, let's look at the problem of computing grid paths. So we have a grid, a rectangular grid, where we start walking at the bottom left corner, and the rule is that we can only go up or right. So we want to start at the bottom and we want to reach the top right corner. So we can number the coordinates. So the bottom right corner we call 0, 0. This particular grid has got 5 columns and 10 rows. So the top right corner is 5, 10. Right? And the question that we ask is, how many different ways are there to go from 0, 0 to 5, 10? So what do we mean by different ways? Well, here for instance is one grid path. This blue line takes us up from 0, 0, then right, then up, then right, and so on. So this traces out one particular sequence of edges along this grid, taking us from the bottom left corner to the top right. So we could of course choose a different one, which in this particular one, the red one and the blue one are completely disjoint. They don't use any of the same edges. But in general, I could have paths which overlap with other ones. So this yellow one partly overlaps with the blue in the middle over here, right? And then it overlaps with the red one over here. Right? So we want to know how many such different paths are there from 0, 0 to mn. Now it turns out that this problem is actually a very classical problem in combinatorics, counting. Right? So the way to analyze this is to see that if I want to go from the bottom to the top, then I must, in one dimension I must go from 0 to 5, in the other dimension I must go to 0 to 10. So totally I must make 15 steps, right? There is no choice, I must walk 15 segments. In general, if I am going to some m, n, I must walk m plus n segments. Now if I have these 15 segments and I'm going to 5, 10, that means I have to go right 5 times, right? And I have to go up 10 times. Now in which sequence I do these rights and ups is what determines which path I take. Right? But every path will have exactly 5 right moves and exactly 10 up moves. Right? So there will be 10 up moves and 5 right moves. So now if I take this and I think of this as an overall thing, saying this is my first move, this is my second move, this is my third move, and so on after my 15th move, then if I tell you that you moved right, I moved right at these positions, at some 5 positions, then automatically I must have moved up at the remaining positions, because I have to do exactly 5 and exactly 5 right and 10 up. Okay. So therefore, all I need to do to determine exactly which path I am taking is to fix the position of the 5 right moves among the total 15. Right? So among 15 positions, I choose 5. Okay. This is usually written as 15 choose 5. Right? So this is a very standard combinatorial thing. 15 choose 5, n choose k is n factorial divided by k factorial into n minus k factorial. Right? So 15 factorial divided by 10 factorial times 5 factorial. It happens to be 3003 in this case. So for this particular grid, there are 3003 ways. Now of course, instead of choosing the right positions, I could also have told you the 10 positions where I moved up. Okay, that leaves 5 open positions where I must move in right. Okay, so this would give us 15 choose 10. And so it's not a coincidence that 15 choose 10 and 15 choose 5 are in fact the same expression. Okay, so whether you choose to compute it as 15 choose 5 or 15 choose 10, it doesn't matter. So in general, it's going to be m plus n choose m or m plus n choose n, where I'm going from 0, 0 up to m comma n. Okay? I have to make m right moves and n up moves. So I need to choose m out of m plus n total moves or n out of m plus n. Both of them will give me the same expression, because that's why n choose k is n factorial, k factorial, n minus k. So if you just exchange k and n minus k, you get the same expression. So that's all very well. But what, for example, if this was not a perfect grid? Supposing we have some intersections which are blocked. So in this particular case, if we look at this intersection, which is 2, 4, right? It's 1, 2, and then 1, 2, 3, 4. So we have put a black mark to indicate that for the moment you cannot go through it, right? So any path that goes through 2, 4 should not be counted among the valid paths from 0, 0 to 5, 10. So the blue path that we had drawn before actually goes through this intersection. So this path is no longer a valid path. The red path is okay because it bypasses it, but the yellow path unfortunately also goes through this intersection. So of the 3 paths that we had seen so far, 2 actually don't go through. So the question now is, out of those 3003 paths that we said were there from 0, 0 to 5, 10, how many of them are still valid if we are not allowed to go through this intersection? So it turns out that actually this also has a combinatorial solution. So what you can say is that in order to go from here, and if I want to avoid a blocked intersection, so let me see how many ways are there of going through it and just remove them. Right? So what I will do is I will say that every path that goes through the current blocked intersection is a path from 0, 0 to 2, 4 followed by a path from 2, 4 to 5, 10, because it goes through 2, 4. So we can think of this as a smaller grid from 0, 0 to 2, 4. Right? So if we solve this, this is the general m plus n choose n. Right? So I get 6 choose 2. So I get there are 15 ways to go from 0, 0 to 2, 4. Likewise, if I consider this grid, okay, then this is 3, okay, and this is 6. Because it was 10 and 5, I've done 2 and 4 respectively. So after 2, there's still 3 left horizontally. After 4, there's still 6 left vertically. So this is like going from a new 0, 0 to 3, 6. Right? So there I get 6 plus 3 choose 3, and this turns out to be 84. Now any path which comes to the bottom to 2, 4 followed by any path that goes from there to the top is a valid path passing through 2, 4. So I have to multiply these two numbers. I have to take 15 times 84 and I get 1260. So this is the total number of paths which are going through 2, 4. But I don't want paths going through 2, 4. I'm saying that paths going through 2, 4 are not allowed. So I must count all these paths as invalid. So I take the original 3003, subtract, so I take 3003 and I subtract 1260 and I get 1740. Right? So taking our combinatorial exercise to the next step, I can find out how many paths go from the origin to a given point on the top right, provided one position is blocked. So this imperfection could be more complex. I could have two positions blocked. Right? In this case, the blue, yellow and red paths are all invalid because the red path also happens to get blocked. So now I have a block at 2, 4 and also at 4, 4. Okay? So if I count all the paths going through 2, 4, which I have already done, I can subtract those. Similarly, I can compute all the paths going through 4, 4 and subtract those. But now what happens is that this yellow path, okay, is subtracted twice because it is part of the paths going through 2, 4 and part of the paths going through 4, 4. Right? So I have accidentally removed it twice from my total. So I have to put it back. Right? So you have to now compute those paths which go through both the intersections and add them back. So this in combinatorics is called inclusion and exclusion. You come across it also sometimes when you do Venn diagrams and you do sets. If you want to find out, you say how many sets have one element, how many sets are the intersection, how many sets. So you have students taking 3 subjects, English, history and physics, and then so many take English and history, so many take history and physics and so on. So when you do that kind of counting, you do exactly this inclusion exclusion. Right? So as we get more and more messy grids, this combinatorial question becomes more and more complicated to solve this way. So let's look for a better solution. So as you might guess, since we are looking at these kind of inductive formulations and recursive programs, what we are really looking for is an inductive formulation of the grid problem. So let's ask ourselves the following question. How do I get to a point ij on the grid? So I claim that given our structure, which is that we can go right or we can go up, there are only 2 ways I can come here. I can either come right from the neighbor on my left. So from ij minus 1, I can make one step right and come to ij. Or from I minus 1j, I can go up one step. So if I have any path which starts at 0, 0, right? Any path which somehow comes to ij minus 1, then by taking exactly one step, that path becomes one path to ij. Right? So every path from 0, 0 to ij minus 1 can be extended in a unique way to ij. Likewise, any path which comes from 0, 0 to I minus 1j can be extended in a unique way. Right? So if I count the paths coming to the 2 neighbors, then each of those paths can be extended to reach the current node. So therefore I get an inductive formulation as follows. So let's write paths ij to denote the number of paths from 0, 0 to the current point ij. So what we have just seen from our inductive analysis of the problem is that if we are at ij, then the paths come from the left or from below. So the paths to ij are the sum of the paths to I minus 1j and the paths to ij minus 1. So there are of course some boundary conditions. So if we look at our grid in general, then if we look at the leftmost column, or let's start at the bottom row. So we start with bottom row, right? Then we know that this is of the form 0, 0, then 1, 0 and so on up to 5, 0, right? So anything of the form I0 derives its value only from the left because there is no corresponding move from below. Similarly, if I am in the leftmost column, then this is 0, 0, 0, 1 and so on up to 0, 15. And now there is nothing from the left, so I can only get it from j minus 1, from the row below. Okay? And finally, we have to ask ourselves what happens at the initial condition. So if I am at 0, 0 and I want to go to 0, 0, how many ways are there? Well, this is a trivial path. There is only one way by just staying there. It's important that it's not 0 because remember that if it's 0, then everywhere you're just adding things and nothing will come. You'll get no paths. Okay? So it's important that there is exactly one path from 0, 0 to itself. So how do we deal with holes in this setup? That's easy. We just say that whenever there is a hole at a given point, we just declare paths of ij to be 0. In other words, if there is a hole at some point, okay,
then this thing is going to contribute 0 regardless of what's above or below. So if I have something coming from here and here, I'll just ignore it and say this is 0. And likewise, when I compute the thing above, there will be some value x coming from the left, so this will just be x plus 0. And similarly over here, there will be something coming from below, say y, and this will be 0 plus y. Right? So any hole will just have by declaration, okay, paths ij equal to 0 because nothing can go through it, and this will automatically propagate to its neighbors correctly. The remaining inductive definition is exactly as before, right? So if it's not a hole, it depends on its two neighbors. And then we have the bottom row left column and the origin as base cases. So the difficulty with this calculation is the same as it was with Fibonacci, which is that if I have a particular calculation, so for example, supposing we start our recursive calculation at 5, 10, okay, then this will ask for 4, 10 and 5, 9. Now these in turn will both ask for 4, 9. So 4, 9, if I just evaluate this paths function recursively the way it is written in the inductive definition, it will end up calling paths of 4, 9 at least twice from this perspective, and this wasteful recomputation will occur throughout, and we will get an exponential number of calls to paths. So we have seen before, we have two technologies to deal with this. So one is memoization, where we just make sure that we never call paths ij with the same value of I and j more than once. The other way is to anticipate the subproblems, figure out how they depend on each other, and then solve them directly, iteratively in a suitable order. And this is what we call dynamic programming. So how would we use dynamic programming on the grid? So this is our grid with the two holes at 2, 4 and 4, 4. The first thing is to identify the DAG structure of the dependencies. Right? So we know that every ij depends on its left and bottom neighbor. So this is how we do the DAG, if you remember. If this depends on the two values left and below, we draw an edge from the left to this node and from below to this node. So this is the DAG structure, right? So the yellow edges represent the DAG structure. So the DAG structure goes naturally from the bottom left to the top right. So this is the only 0 in degree node in this DAG. So if we want to do a computation of this the grid paths directly using dynamic programming, the only place we can start is 0, 0. Right? So we start at 0, 0 and we fill the value there, which is 1. And now we observe that we have two possibilities. We can go to the right or we can go up because these two dependencies are now removed. So let's just go row by row. So if we do this value, then automatically this dependency will go. So we'll be able to do this value, then this will go. So we can do this value and so on. So we can compute the entire bottom row. And these are all inherited from the left using our base case. Right? So, and it's very clear. I mean, intuitively it's clear. There's only one way to get to any of these places, which is just to go straight from left to right. Okay, no deviations possible. So there's only one path to every node on the bottom row. Now we can move up one row. We can see that this node in the first row or the second row is now available. It was already available. But if we do that, we can also do the node to its right and the node to its right and so on. Right? So we can fill the entire second row, and at each point we are just adding up. So 2 is 2 plus 1 plus 1 is 2, 1 plus 3 is 4 and so on. Likewise, we can do the next row. So for example, 6 plus 4 is 10 and so on. Likewise, we can do the next row. 20 plus 15 is 35. Now we come to the holes, right? So at the holes, we said that these will be 0 regardless of what comes from below. Even though there's 10 coming from below, this first hole must be 0. With 35 from below, this hole is 0. Right? So we just compute this row exactly as before, except at the holes, we put a 0 regardless of what is coming into it. We don't count it as 5 plus 10, we just put 0. We don't count this hole as 20 plus 35, we put 0. Now when we go to the next row, likewise, this 0 contributes only 0. So above it, because no paths can come through this direction, the number of paths coming here is only 6 coming from the left. Similarly, the number of paths coming here is only 26 coming from the left. Okay. Similarly, the number of paths which are coming to this point, okay, could not come from there. So this 20 is copied there, this 56 is copied here. So we can do this row by row, and if you can just enumerate every row like this by copying, adding up the values to the left and below, and we will find that there are actually 1363 paths with these two obstructions. Okay. And if we move the obstructions around, we can redo this calculation. It will be as efficient. We don't have to worry about this inclusion and exclusion. So this is one way to do the dynamic programming, but remember, any topological sort will work. So we could instead start with 1 and go column by column. So we can go up and
fill that, and then we can fill up the entire first column. The first column will again be only once because there is only one way to do this. Having filled the first column, now we can fill the second column, and then we can fill the third column and the fourth column and so on. And obviously this is only a different way of enumerating the values don't change. So we should eventually end up with the same values at every point. And finally, you can also do it by diagonal. So notice that when I do this one, then these 2 points now are 0 end degree nodes. So I can do both of them. Now I have these 3 points as 0 end degree nodes, so I can do all 3 of these. Then I have these 4 points as 0 end degree nodes, so I can do all of these, and so on. Okay, so this is just to emphasize that the choice of topological sort is entirely up to you. Very often it will be more complicated to program this kind of diagonal thing, so usually one tries to do it by row and column, but any topological ordering of the base values can be used in order to compute them. All you need to know is when you come to a node, a value that you want to compute, all its dependencies must have already been computed. That's what this DAG structure gives you. Right? So the subproblems form a DAG, and you have to navigate your way through the DAG in a most effective way as far as programming it. It's usually by row or column in a table, but it could be by diagonal also. So finally, before we conclude, let's just look at an instructive illustration of the difference between memoization and dynamic programming. Okay, so if we have a bunch of holes which are along the border, then intuitively what it says is that if I start from here and I go anywhere like this, I'm going to get stuck. Okay? So if I start my memoization from there, then everywhere is just going to see a 0. Okay, so all these values are just going to be 0, and my memoization is not going to look further along these. So memoization, I claim, is only going to look along this outer boundary. Only these grid points will actually be computed by memoization. Okay. Whereas if I do dynamic programming, I will start from here and I will blindly fill up. Only when I reach the 0, I will realize that the values are computed inside this grid, don't fill up. Right? So there is this entire shaded region in this grid whose values are not needed because they cannot contribute to any path from the bottom to the top, because every path going through them will get blocked by one of these holes. Right? Whereas dynamic programming is now going to blindly compute values for these points even though they are useless. Memoization will not, because it only computes by need and it will never reach these points. So therefore the memo table will have a linear number of entries, right? It will have, say, 2m plus 2n entries. It will only have the outer boundary of this grid will be covered. So it will have a linear number of entries in terms of the 2 dimensions. Whereas dynamic programming will have m times n entries. It will have every grid point will be computed in the table, even though most of them are useless. So in a sense, in this example, dynamic programming is wastefully computing values which we can, by a little bit of analysis, realize will never be used, because it is just blindly computing every subproblem on its way from the origin to the top. However, as we said before, dynamic programming is iterative. It is going to be just a simple loop. Memoization is going to be recursive. It is going to be optimized to not make the same recursive call twice, but nevertheless it is recursive, and recursion carries a cost in terms of execution in a programming language. So therefore, though this looks like a wasteful dynamic programming strategy in case the holes are distributed in a bad way, actually it doesn't matter. It usually turns out that a dynamic programming implementation will be usually more efficient than a memoized implementation. So the memoized implementation is easy to do because we know that we can go from an inductive definition directly to a recursive program. And we saw last time that there is a generic formula or a recipe to make any recursive program memoized. You just have to insert a couple of steps saying look up the table and feed the table. Right? So therefore getting a memoized implementation is very easy. Getting a dynamic programming implementation requires some analysis of the subproblems and figuring out a good order in which to evaluate the subproblem. So it is more work. But this extra work usually pays off because then you get an iterative computation of all the subproblems rather than a recursive one. So let's now turn to the problem of finding common subwords and subsequences between two sequences. So the first problem we look at is what's called the longest common subword problem. So let's suppose we are given two words. For the moment, let's just assume they are words in English or a language like that. We are given two strings, and we want to find the length of the longest common subword between them, and a subword is just a segment, right? So for instance, if I have secret and secretary, then the longest common subword is just the prefix secret, okay, and it has length 6. Between bisect and trisect, I have this common segment isect. Okay, if I have bisect and secret on the other hand, then the common subword is of length 3, namely SEC. And if I have director and secretary, then there are actually only 2 length subwords, and there are 2 of them. So EC occurs in both of them. Okay? And so does RE. Okay? So we may have more than one candidate for the longest common subword. But our main goal at the moment is to compute not the subword itself but the length. We will see how we can recover the subword quite easily from the length calculation. So the focus at the moment is to get the length of the subword. So let us look at this thing more formally. Okay? So we have 2 words, A0 to AM and B0 to BN. Okay? And now what we want to say is that if I write out A0, A1, then I have a position AI, AI plus 1 and so on, and then AM. So if I can find some segments starting with AI and BJ, okay, such that if I start from here and I read off K letters, if I start from BJ and I read off K letters, so I read AI, AI plus 1 or to K minus 1, I plus K minus 1, and BJ, BJ plus 1 or to BJ plus K minus 1. Then if these are both K length segments which are equal, then I will say that U and V have a common subword of length K. So they must be a matching segment of the word. And now the aim is to find the length of the longest such segment. So the longest common subword of U and W. So here is a brute force algorithm, right? You just try out every position. We look at every AI and BJ, right? So you look at every I and J, I between 0 and M and J between 0 and N. And then I just keep looking, right? I look at the next, if these 2 match, I look at the next letter and go on. I keep going until I find 2 positions which don't match, right? Then I know that the longest subword starting from these 2 positions is only this much. Right? So I match AI, BI, AI plus 1, BI plus 1 as far as possible, and I keep track of the longest such match. I do this for every AI and BJ. Okay? So if M is greater than N, then first of all, the number of choices of AI and BJ is M times N. And in general, I will go to the length of the end of the shorter word matching everything. So I could do order N work before I reach the end of the scan. Okay? If everything matches until the end of the shorter word, then I could do order N work. Okay? So therefore this will be O of M times N into N or O Mn squared. Right? So now our goal is to see whether we can make this more efficient by doing something inductive on this. So the first observation, the inductive observation, is that if I have AI, AI plus 1, if I have BJ, BJ plus 1. Okay? So if I have a subword starting from here of length K, then if I look at the next position and go forward, this must be a subword of length K minus 1. Right? So there is a common subword of length K at ij, if and only if there is a long common subword of length K minus 1 at I plus 1, J plus 1. So in other words, I look at ij. If ij is equal, okay, then there is possible to start a word at common subword at AI and BJ. So if AI is equal to BJ, I look at the longest common subword I could have got from I plus 1, J plus 1 and add 1 to it. On the other hand, if AI is not equal to BJ, then I cannot have a common subword starting here because the very first letter doesn't match. So then I just say the length of the longest common subword starting at that position is 0. So this gives us a handle on the inductive structure. So I look at 2 positions. If they are not equal, I declare that there is no common subword starting there. If they are equal, then I postpone the problem to the next position and add 1 to whatever I get in the next position. And the boundary condition is when one of the words is empty, right? When we have no letters left, so we can't extend one of the words anymore, we can't go forward, then we can say that there cannot be a common subword because there are no letters to use from one of the 2 words. Okay? So for convenience, although our words go from A0 to AM and from B0 to BN,
Okay, we will allow an m plus 1th position and an n plus 1th position. So we'll have positions 0 to m plus 1 in u and 0 to n plus 1 in v. So m plus 1 means I have gone beyond the last position in u, I have exhausted all the letters. Likewise, n plus 1 in v means we have reached the end of the word in v. So what we said is that if we have reached the end of the word in u, then no matter where we are in v, there is no common subword. So the length of the common subword is 0. Likewise, if we have reached the end of the word in v, wherever we are in u, there is no common subword, length is 0. And if we are not in these two cases, we are not at the end of the word, then we check whether ai is equal to bj. If ai is not equal to bj, we declare, as we saw earlier, that the longest common subword has length 0. Otherwise, we inductively compute the value for the next position in both the words and add 1 to it, because we can extend that word by 1 because ai is equal to bj. So we could write a memoized recursive function for that, but we will directly try to compute a dynamic programming solution for this problem. Okay. So we will typically have these sub problems of the form LCW IJ. Right? These are our basic sub problems. So what we saw from the earlier thing is that if I have ai equal to bj, I need to look at ai plus 1, bj plus 1. So LCW ij depends on LCW I plus 1, j plus 1. Right? So we have this kind of sub problem dependency. At every point, a value needs to look to the one which is below. So we have in this, just to be clear, this is our I and this is our j. Right? So it has to look down and right. So therefore, now with our convention that we draw the arrows backwards, that is, if this square depends on this square, then we draw an arrow indicating the dependency in reverse. Right? So I need to compute the bottom of the arrow before I can get to the top of the arrow. That's what the arrow says. I need to compute this before I can compute this. Okay? So now we can start at this corner because this depends on nothing, and then start working. So as we saw at the boundary where I have exhausted one word, where either the first word or the second word is, so we have written the word, by the way, bisect and secret, just to tell us what the values of ai and bj are. So these are the values of ai and these are the values of bj. Right? So these are my two words. So initially at the boundary, every longest common subword is 0 because one of the two words is empty. And now I can do it, say, row by row or column by column. So let's do it by column for a change. Okay. So now at this point we have that A5 is equal to B5. Therefore we get 1 plus LCW of 6, 6. Right? And therefore we get a 1. Everywhere else C and T, E and T, there are no other T. So everywhere else it is just 0 because the value don't match. Now if I go to the previous column now, here the only one that has anything to say is E and E, but there because the next one was 0, I just get 1 plus 0 is 1. If I go to the previous one, in fact the value, no, there's no R in bisect, so therefore all the values, the subword is 0. If I come to the next thing, again now I have one place where C and C match, so I say that the longest common subword starting here is 1 plus whatever happens at T and R, but T and R don't match, so it's 1 plus 0 is 1. But now because this C is now preceded by an E, so at this E I find that it is 1 plus whatever happens to the bottom right, so it's 1 plus 1 is 2. And likewise at S I find that S and S match and it is 1 plus whatever is to bottom right, so it becomes 3. Right? So we identify in this way, we put an entry 3 here. So in this particular table it's a bit mysterious where the answer is. Okay. So what we have to do is find the entry with the largest, find the entry which has the largest value. In this case 2, 0, this is our largest value. Okay, so this tells us that between these two words the longest common subword has length 3. As I said before, we are only computing the longest common subword, so how do we actually find the subword? Well, we can actually in this case very easily read it off. We know that there is a longest common subword here of length 3. That means that it must be succeeded by a word of length 2 and so on. So this particular diagonal tells us what the letters in the word are, and if I just project this diagonal onto both the one column, I'll get the word SEC. Right? So in this example, as we see, once we've computed the length, it's very easy to read off the solution. So here is some code for this particular algorithm, the dynamic programming version. Just to make it less confusing, I have explicitly used the variables R and C instead of I and J. So R is the row, it goes this way, and C goes this way. Right? So what we say is that initially, if I am looking at the last column, okay, these are all zeros, okay, and if I am looking at the bottom row, right, this empty. So remember that the numbering is from 0 to n plus 1 and from 0 to n plus 1. So if I am looking at the bottom row, when the row number is n plus 1, every column is 0. So this puts the zeros. So these two lines just populate things. Now we have to find, remember the goal is to find the maximum position in the entire array in order to give the answer finally. So we'll just keep track of that with a value here. So we'll initially assume that the maximum common word is of length 0. Now what we do is we just go column by column, row by row, right? So we go for each column from n to 0. So we do column by column, and each column we go row by row from bottom to top, m to 0. Okay. We look at the word position R and position C. Is UR equal to BC? If so, I add 1. So this should be W probably, not S. So if I have U of R is equal to B of C, then the longest common word, length of the longest common word RC is 1 plus at R plus 1 C plus 1. Otherwise it is 0 because there is no common word. And if the new value I have computed is bigger than the value I have seen so far, okay, then I will update it to the current value. And finally, at the end, I will just return this length. Okay, so it's a very straightforward, iterative way to process this thing column by column. You could invert these two indices and do it row by row. Okay, so that is an exercise. So we had seen earlier that if we just look blindly at every position and try to scan the word starting at that position, we get something which is of order mn square. Now this solution requires us to fill in the table of size m times n. So obviously every entry in this m times n table, we just have to look at the neighbors to fill it up. So it's a constant time operation. So m times n entries, we fill in m times n times. So we have an order m1 n algorithm. If you use dynamic programming, we have done it. But if you use memoization also, you will get the same answer. Although remember that the recursive calls might cost you in terms of actual implementation time. So we can now look at a slightly more general problem than longest common subword, and one which is more interesting computationally. So what if we don't look for an exact match, but we allow ourselves to drop some letters? Okay. So we have a subsequence, not a subword, which allows us to drop some letters, and now we want to know if after dropping some letters, what is the longest match we can find. So in our earlier examples, some of them are the same. Like in this case, without dropping any letters, I could get 6 and I can't improve it. Same way with this isect, I cannot improve it. But now if I look at bisect and secret, earlier we only had a length 3 match, SEC, SEC. But now I can extend this match to length 4 because here if I add a T, here I can drop 2 letters and get a T. Right? So I can actually get a match which is length 4. Likewise, in these two were director and secretary. Earlier we had RE, RE, and we had EC, EC. Okay, but now by doing this dropping, I can get ECTR, and I can get ECTR, right? And similarly, I can get RETR, and I can get RETR. Okay, so if we allow ourselves to drop letters, we can get longer sequences that match. And this is called the longest common subsequence. So one way of thinking about it in terms of our earlier longest common subword is that I can now, if I have matched a certain segment, I can continue to match to the right. So I can let both indices go forward. So I can go down and right in the grid and look for another place where there is a match. So earlier we had a 3-level match between SEC and then we had a 1-level match between T. So I can combine these to make a 4-level longest common subsequence. But we will do the subsequence calculation in a much more direct way than this. So before we proceed, it's useful to look at why the longest common subsequence problem is interesting. So one of the areas is in bioinformatics. So biologists are interested in identifying how close two species are to each other in the genetic sense. So if we look at our DNA is basically a long string over an alphabet of size 4. Okay. So these are 4 proteins which form our DNA. They are abbreviated as ATGC. So now if we look at two strings of DNA, a natural way to compare how close they are to each other is to ask how well they can be aligned if we just drop a few things here and there. Right? So it could be that one species has a few extra genes, another species has a few extra genes doing something else, and if you drop those genes, then everything else is the same. But these genes may occur at different places in the two species. So it's not that there is a common part and then there is an extra part. It's rather that the new genes are interspersed among the other genes. So we need to know if we can drop a few genes in one and a few genes in another, can we overlap them? So that's the longest common subsequence problem. If you use Unix or Linux or any related operating system, there is a command called diff which allows you to check whether two text files are the same or find a minimal difference between them. So the diff command also does a longest common subsequence. It treats each line as a character and it says what is the minimum number of lines I can drop between these two files before I can match them up, and then it tells you how to insert things back. But basically it's doing a longest common subsequence calculation to tell you how close two text files are to each other. So there are plenty of applications for this longest common subsequence problem. So let's try to understand the inductive structure of this longest common subsequence problem directly, not through the longest common subword. So the first thing to note is that if I'm looking for this longest common subword between two, and supposing I find that A0 is in fact equal to B0. Now I claim that I should combine them in the solution and then look for a solution in the rest. Okay, so I should do something where I say that there is one match A0 equal to B0 and then I must find the rest. Okay, so this requires a little bit of an argument because it could be that this is not the optimum way to do it. Right? So remember, this is a bit like a greedy thing. We are saying that because A0 is equal to B0, match it up and then proceed. So one might argue that this is not the way I want to go. Supposing A0 in fact should be matched to B2. Okay, that would be the best solution. So it is not a good idea to match A0 to B0. But now notice that if A0 is matched to B2, because it's a subsequence, then anything to the right, say A1 is matched to something, it must be further to the right? These lines, I cannot have anything which crosses like this. I cannot have any match with crosses because they must occur in the same sequence. So if A0 is matched to B2, A1 must be matched to something to the right. A2 must be matched to something still further to the right and so on. Right? So all these matches go from the top word to the bottom word without crossing each other. So now if I take this solution and I know that A0 is B0, then I can actually move this arrow here and make it match like this and remove this. What will this do? It will disturb the original solution by no longer saying A0 is matched to B2 but A0 is matched to B0. But in terms of the quality of the solution, right, the number of matches is the same. Earlier A0 was matched somewhere else, now it is matched to B0. So the length of the longest common subsequence does not change. Right? So turning this argument backwards, it says that therefore if A0 is equal to B0, it is very safe to assume that A0, B0 forms part of the solution and proceed with the rest of the problem. So we can look at the sub-problem from A1 and B1. Right? So this is the first case. So the first case says that we can look at, if A0 is equal to B0, we can look at this sub-problem from A1 to B1. Now, if it is not equal, okay, then one is not sure what to do. It's not a sound idea to drop both. Okay, for instance, supposing I have something like straw and a stray. Okay, then just because the S doesn't match the A, it doesn't mean that I should remove both of these, because I should keep the S alive to match with the next S. Right? So both cannot be there because they don't equal each other. And if S matches something on the right, then A cannot match something because if they are both different, right, if they are not equal, then this must match something there and this must match something here, and both cannot happen because they will cross, and this we said is not allowed. So only one of them can match something to the right on the other word. But we don't know which one. So this is what the general principle of these inductive solutions is, that you don't try to choose one or the other. Right? So if I leave B0 and I drop A0,
then I get a solution, I get a subproblem which has A1 to AM and B0 to BN. If on the other hand I keep A0 and I drop B0, then A0 to AM remains, but now it's B1 to BN. Okay? So these are my two possible subproblems, knowing that both A0 and B0 cannot be there, but I should allow one of them to be there. Otherwise, I might have a suboptimal solution. So dropping one of them, it's like in the job scheduling case where you say that if this job is there, something else is not there. Right? If A0 is there, B0 is not there. If B0 is there, A0 is not there. But beyond that, I can't say anything. So therefore, I solve both of these problems in principle and take the maximum, the better of the two. Okay, so this is the inductive structure now. Either the first letter matches, in which case I include it in my sequence and solve the remaining subproblem, or the first letter doesn't match, in which case I generate two subproblems, one by dropping each of the letters in turn, and I take the maximum of the two. So as usual, let LCS I comma j stand for the LCS of the problem starting at AI and Bj. So if AI is equal to Bj, as we said, LCS of Ij is 1 plus LCS of I plus 1 j plus 1. This says we will assume that AI equal to Bj is included in our solution and then proceed with the rest of the input. If it is not, then I have to drop one of them. So either I look at LCS I plus 1 comma j or LCS I j plus 1. I look at both and then I take the maximum of these two. And there is no other thing because the current one doesn't match. So as with the longest common subword problem, we will extend the positions to go beyond the word to indicate the word is over. So we will go from 0 to m plus 1 and 0 to n plus 1. And when we have reached m plus 1 or n plus 1, then the LCS problem will give us 0 because there cannot be a common subsequence since one of the words is going to be empty. So the subproblem dependency in LCS is a little more complicated than in LCW. In LCW, we only had this dependency. That is, we said that Ij depended on I plus 1 j plus 1. But now we have also a dependency on I plus 1 j and Ij plus 1, right? So we have a dependency coming from the right and from below as well. So we have a three-way dependency. As we saw, all these values are going to be 0 here, right? So this is the first non-trivial value that we can compute because all its three neighbors are known. Nowhere else are all. So if you look at here, for example, the bottom neighbor is not known. If I look here, the right neighbor is not known, right? So at LCS m comma n, 5 comma 5 in this case, the value is available to compute because everything around it, the three dependent squares around it are all populated. So I can do that and then I can again do row by row. Once I've got this, I can do this because I'll have all three values. Once I do this, I can go left. I can do this and so on, right? Or you can do diagonally. So let's do it column by column, right? So we start with the base case where the LCS at the boundary is 0 because you cannot have a longest common subsequence with an empty word. Then we fill up the first column and here we get a 1 because when the two match we have 1 plus LCS of I plus 1 j plus 1. Right? Now we have some differences. So when it doesn't match, like when C, so if I look at C and E, they don't match, then what I'm supposed to do is I'm supposed to take the maximum of these two. So since I take the maximum of these two, I get 1. Now since I take the maximum of these two, I get a 1. Maximum of these two, I get a 1 and so on. So the longest common subword problem, it said if the current letter doesn't match, then I get a 0. Here it's not there because I'm allowed to drop this letter and go ahead, right? So therefore this 1 propagates along this column. Similarly, the 1 propagates along the previous column because nothing is an R. Now I get some additions. Okay, when I reach C and C, it is 1 plus I plus 1 j plus 1, so I get a 2. Likewise, when I go to the next column, when I reach E and E, it is 1 plus I plus 1 j plus 1, so I get a 3. And finally, when I reach this S and S, okay, I get this 4, and now this 4 propagates because here I take the max of these two, so I get this 4. Max of these two, I get 4. So in this particular case, actually LCS of 0, 0 is my answer. Remember in LCW, I had to look around in the whole grid to find out where the maximum was. In LCS, you don't have to do that. The value you get at 0, 0 is actually the answer you're looking for. Okay? And now, as before, you can trace back the path. Why was each value filled? Was it filled because it is 1 plus I plus 1 j plus 1? Or was it filled because it was max of the other two neighbors? If so, which was the max?
right? So it's very clear that this 4 came because it was a max, because s is not equal to b, so it came from below, and this 4 also came from below. Now s is equal to s, so this came from here, and so on. So you can trace out this value, and everywhere where you have this diagonal, okay, it was there because the values matched. So there are, the value is 4, and there are exactly 4 diagonal steps. This one, this one, this one, and the one on the bottom right. Okay? These are the 4 matches which constitute the longest common subsequence, and you can read it off by the thing, and it forms the sequence SCCT. Okay? So as we saw before, provided you can compute the answer numerically, you can go back and retrace that computation and figure out the witness, as it's called. Now, which word actually, which subsequence actually gives rise to this answer. So the code for LCS is a little bit simpler than for LCW, because we don't have to keep track of this maximum value and where it occurs, because we only need to find the value at 0, 0. So as before, we use R and C to be a little clearer, that rows goes this way and columns go this way. So columns go from 0 to n minus 1, n plus 1, and rows go from 0 to n plus 1. So we initialize the boundary to be 0, and then we do column by column, row by row from bottom to top. If the two are equal, then you add 1 plus the value of the bottom right. If the two are not equal, I take the maximum of these two values and copy it. And finally, when those values are filled out, I return the value at 0, 0. So this is similar to LCW. Right? We basically fill out an n size table. Each entry in the table is easy to compute. It takes only a constant amount of time. You have to look at the 3 neighbors. And therefore, overall, using dynamic programming, we have demonstrated an order mn algorithm. You can also use memoization at the cost of recursion. So having looked at the longest common subword and subsequence problem, we now look at a closely related problem called edit distance. So the aim is to measure how similar two pieces of text are, the so-called document similarity problem. So let's look at the following 2 sentences. The first sentence says, the students were able to appreciate the concept optimal substructure property and its use in designing algorithms. The second sentence says, the lecture taught the students to appreciate how the concept of optimal substructures can be used in designing algorithms. So the third sentence here indicates how one might obtain one of these two from the other. If you have used certain document preparation systems which allow you to track changes, it will typically indicate the changes between one version of a document and another version like this. So here the green indicates letters which have been, so if we call this version 1 and this version 2, then in going from version 1 to version 2, what we have done is we have introduced the letters in green. So we have inserted these characters. We have deleted the letters marked in red with a line through them. Okay, and in this yellow we have replaced, so we have replaced a T by a B and an S by an E. Okay, so we have 28 characters. You can count that there are 28 characters which have been inserted, including spaces and all that. 18 characters have been deleted. Okay, and 2 characters have been substituted. Okay, so now this can be a basis of measuring how close to documents are to each other. Right? So the edit distance is the minimum number of edit operations required to transform one document to another. So we have to define what we mean by an edit operation. So let's just start with very basic operations. Either you can insert a character, or you can delete a character, or you can replace one character by another one in one step. So replacing, of course, could be thought of as deleting and inserting. So that would be a 2-step operation. I delete the character and then I insert the character I want. But I'm going to allow changing one letter A by B or S by T as a single operation. Okay. So in our example, we claimed that 28 characters were inserted, 18 were deleted, and 2 were substituted. So the total number of changes we made is 48. If the edit distance is supposed to be the minimum number of changes, it can't be more than 48, because we've already shown that it is possible to do it in 48. Perhaps it's possible to do it in a more clever way in less than 48. So the edit distance is at most 48 for the 2 sentences that we showed earlier. So this distance is also called the Levenshtein distance, because it was first proposed by then Soviet, now Russian scientist called Vladimir Levenshtein. And this, like the longest common subsequence problem, is extremely useful in practice.
So the first thing is to suggest spelling corrections. Now if somebody types something that is wrong, okay, then a spelling corrector will have to suggest the correct word from the dictionary to replace it. So which word should the spelling corrector choose? So one criterion for choosing is to identify among all the words in the dictionary that are possible, which one is closest to the one that has been typed. Right? So this can be measured in terms of this edit distance, and then the menu will pop up saying, "Did you mean to type this?" This also happens when you type queries in search engines, right? So if you type something to Google, Google will sometimes change your query to a word which is meaningful because it recognizes that you have mistyped a name or a concept. We also said that the longest common subsequence problem that we saw earlier is useful in genetics and in bioinformatics. And in the same way, edit distance also, if we want to compare the genetic information in two different species, then it's natural to to compare them in terms of the content of the DNA, and DNA are just long strings, right? So we want to find out how easy or difficult it is to transform one piece of DNA into another, and depending on that, we can tell whether two species are close to each other or not. So if you go back to the longest common subsequence problem, right? So one way of thinking of longest common subsequence is, supposing I just delete all the parts which are not part of the LCS, right? So I had things like bisect and secret, okay? So now in this, if I deleted the B and the I from here and the R and the E from here, then I'm left with exactly the longest common subsequence, okay? The other way of thinking about it is that I start with one word and I'm transforming it to this word. So I first delete the B and I, and then I insert here the R in, right? So I don't operate on both words and delete from both. I operate only on the first word. So I delete the words I don't do, delete the letters I don't want because they're not in the second word, and I insert the letters that I do want, which are there in the second, not the first. This way I transform the first word to the second word, and this is equivalent to deleting from both and coming to a common subsequence, right? So this tells us that LCS is somehow equivalent to computing the edit distance if I only allow delete and insert, right? So the interesting thing about edit distance is that it also allows a substitution of one character or another. So it might give us a slightly different metric from longest common subsequence. So going back to longest common subsequence, right? It said that if two letters match at the beginning of a word, then it's useful to assume that the common subsequence includes that. So I have this one which says that AI is equal to BJ, so I include this in my subsequence and then I solve the rest of the problem. Otherwise, I take the max of the two subproblems that I get by dropping AI or BJ. Now in the edit distance problem, we have a similar criterion. Okay? If AI is equal to BJ, then I have nothing to do. Right? So the edit distance of words starting at I and j is the same as the edit distance starting at I plus 1, j plus 1. Recall that we are now doing the opposite of longest common subsequence. We are now trying to minimize the number of changes, not maximize the number of matches. So if we see that something is already matched, then no change is needed. So we just move ahead to the next position. Now, if they don't match, now three things are possible, right? So I have AI plus 1 and so on, and I have BJ plus 1 and so on. So the first thing I can do is I can directly make this into BJ. In which case, I have now made the first letters exactly equal, and so I just need to look at I plus 1, j plus 1. Okay? The other thing which I can do is to remove this AI altogether, right? I just remove this AI. So now this discrepancy is gone, but I am still left with the rest of the problem. So now I have to now see if I plus 1 onwards matches j onwards. And finally, the last thing which I could have done is to introduce that this bj at the beginning. Okay? So now this means that these two things now match up. So now I have to look at ai onwards and bj plus 1 onwards. Right? And whichever of these three requires the minimum work overall is the one I want. So I want to take 1 plus the solution for I plus 1 j plus 1, or 1 plus solution for I plus 1 j, or 1 plus solution for I j plus 1, and take the minimum of these three. Right? So this gives us the final inductive structure that we want. So ED, the edit distance for the word starting at I and j, if ai is equal to bj, it is ed of I plus 1 j plus 1. If it is not equal, then it is 1 plus the minimum of the edit distance of these three different subproblems. Okay, and as usual, we extend this to m plus 1, n plus 1, but the interpretation is now different. If one of the words is empty, then the number of changes I need to make is to transform everything else or insert everything from that word here. So if I am looking at bj plus 1 to bn, and on this side I have nothing, then what is the edit distance? Well, I have to basically insert this many letters. How many letters are there? N minus j plus 1. Okay, so the edit distance when u is empty and v is at position j is n minus j plus 1. Likewise, when v is empty and u is not, it's m minus I plus 1. Okay, because I have to insert all those letters. So this is a slight difference. It's not 0, but it's the cost of using up the letters which are there, which are missing in this word. So the inductive substructure in edit distance is exactly the same as in LCS. Okay. Every position depends on I plus 1 j plus 1 and the I plus 1 j and ij plus 1. Okay. So we have the same three neighbor dependency that we had as we did before. And as usual, we can start at the bottom right corner and work backwards row by row or column by column. Okay. So in this case, remember that the boundary condition is not 0, but it is n minus j plus 1. So as I go up, the number increases. Okay. So this is my boundary. And now I can just apply my recursive thing, which says that, okay, t matches. So the edit distance at t is 0 because I have nothing to do and there's nothing to do beyond that. Everywhere else, because they don't match, the edit distance is just going to be the minimum of the remaining 3. Right? So it's the minimum of the remaining 3 plus 1. So in this case, if I look at this, for example, the minimum of 0, 1 and 2 is 0, plus 1 is 1. Okay? The minimum of 4, 2 and 3 is 2, plus 1 is 3, and so on. Okay? So it's the minimum of those plus 1 to make the current change. So I keep doing this, and as I go left, okay, eventually I'll find that the minimum edit distance between bisect and secret is actually 4. I need to make 4 changes. Okay, just using the inductive definition that we had done earlier. And as before, now the question is, how do I recover the solution from this? So I follow the path. Right? So why did I get a 4 there? Because it is the minimum of its 3 neighbors. B is not equal to S. What is the minimum of these 3? It's 3. So I went down. Similarly, why is this 3 here? Because it's the minimum of these, so I went down. So every time I go down, okay, it amounts to saying that I go from ij to I plus 1j. Right? And if you remember in our case, I plus 1j and ij corresponds to deleting. Similarly, at this place I go right. Right? This means I go from ij to ij plus 1. And this corresponds to inserting. So what I can read off from here is that when I'm going, I delete this b, I delete this I, then I come here, I insert this r, and I insert this e. And these are exactly the 4 changes that I need to make in order to transform bisect into secret. So the pseudocode for edit distance is very similar to the longest common subsequence. The only major change, one is in the initialization. The values of the boundary are not 0, but whatever is required to complete the editing. Then as usual, I start at the bottom right and I do columns from right to left, rows from bottom to top. If the current value, if the two values that I'm looking at, u of r and v of c are the same, then I just postpone the edit distance to the next thing. I have nothing to do here. Otherwise, I take the minimum of the subproblems and I add 1 for the current change. And finally, I return the value at 0, 0. The complexity is order m times n. It's exactly the same as the previous one because I have to fill up this table of size m times n and it takes a constant time to compute. Now in all these 3 problems, there's another issue which we have not addressed, so let's deal with it now. So the notion of space complexity. So we have this table that we have to compute, which we have agreed is m times n. But notice that the way we computed it, for example, was to compute this column, then this column, then this column, and so on. Right? So at any given point when I'm computing the second column, for example, I only need the first column. Now when I reach the third column, okay, this column is now not needed anymore because the third column depends only on the second column from the right. So if I fill column by column, I only need the next column, the column on my right, and the current column. Okay, or if I'm doing it row by row, the next row and the current row. So in other words, by just keeping two columns or two rows, I can completely compute this thing back to 0, 0. So therefore, there's actually no need to do m times n size table as storage. I still have to compute m times n. So the time complexity remains m times n. Okay, so time is m times n. What we're saying is the space can be reduced if let's say that n is the smaller of the two. The space can be reduced to order n, okay, by just keeping two columns. Okay. And now you might ask, how do I recover the solution? Because in the solution I trace back the path and the whole thing. Well, you can actually keep track incrementally as you are going. You can build up the solution associated with each entry incrementally. So even that can be done in order n space. So you don't need this table at all even to compute back the witness for the given numerical solution, right? So in all these problems where we have a very limited neighborhood dependency in our dynamic programming, you can actually often make do with much less space than it seems to require in terms of the actual table as given to you. So for our last example of dynamic programming for this week, we look at the problem of efficiently multiplying a sequence of matrices. So as you probably know, to multiply two matrices A and B, you need compatible dimensions, right? So if we have A and B, then we need that the number of columns in A must match the number of rows in B. So we have m times n matrix A and an n times p matrix B, and the final matrix is going to be of times m times p. It will have the same number of rows as A, the same number of columns as B. And the way you compute the product AB, so if I want the ijth entry in AB, then I will take the ith row in A, okay, and I'll somehow multiply it with the jth column in B. So I will take the first entry here, the first entry there. So I'll take AI1 and B1j, multiply them, AI2, B2j, multiply them, finally AIN, B and J, multiply, add them all up. So this takes order n steps, right? Because I'm computing order n pairwise products and then adding them up. So therefore I have to compute finally m times p entries. Each entry requires a linear order n amount of work. So the total cost of multiplying two matrices in terms of basic arithmetic operations is of the order of m times n times p. So this is the basic fact that we need for the problem. So now the concern is not computing the product of two matrices, but computing the product of three or more. So supposing I want to multiply three matrices A, B and C. At a time I can multiply any two. So either I have to multiply it as A times B, get a intermediate matrix AB and then multiply it by C. Or I can do B times C and then multiply it by A from B. So matrix multiplication is not commutative. We don't have this in general. Okay. So it is important that the order is the same, but within that, in which sequence I do this simplification doesn't matter. So it's associative. I can bracket it by as A times B followed by C or A times B followed by C. Either way, I have to do two matrix multiplications. Okay. And what associativity means is that the answer will not change. The final product will remain the same. But what is interesting for us now is that the complexity of computing the answer can change depending on which order I do it. Whether I do it as A times B followed by C, or first I do B times C and then I pre-multiply by A. So let's look at a very trivial example. Right? So I have three matrices of this kind. So A is a matrix which looks like this. Right? It has one row and 100 columns. B is a matrix which looks like this. It has 100 rows and one column. And C is again a matrix which looks like this. So this is my A, this is my B, and this is my C. Okay. So now supposing I do B times C first. If I do B times C, what happens is this 100, okay, will now blow up and I will get a big matrix which is 100 by 100. because I'll have 100 rows here and 100 columns there, right? And so the final thing is going to be number of rows in B and number of columns in C. So the B times C matrix is actually 100 by 100. And how many steps does it take? It takes M into N into P, which is 100 into 1 into 100, which is 10,000 steps. Now I have A, which is 1 by 100, and B, which is 100 by 100. So I'm going to produce something which is again 1 by 100, but I'm going to take 1 into 100 into 100, right? Because M into N into P is another 10,000. So together, this particular sequence requires 20,000 steps. If I did it the other way, on the other hand, if I computed this product first, then I will collapse it to a simple 1 by 1 matrix, because number of rows here is 1, number of columns is there. Right? So AB is a 1 by 1 matrix and it takes only 100 steps to compute. And now again I have a 1 by 1 times a 100 by 1 matrix. So again it takes only 100. So this takes only 200 steps. So you can see that there can be a dramatic difference in the complexity depending on whether you bracket it as AB followed by C or A followed by BC. So in general we'll have a sequence of n such matrices, right? So M1, M2 up to Mn. And their dimensions will be R1, C1, R2, C2 up to Rn, Cn, number of rows, number of columns. The dimensions will be given to us so that they can be multiplied. Remember that all we need, assuming the entries of course can be combined by sensible multiplication, addition operations, what we need to be able to multiply two matrices, the dimensions would match. So we are guaranteed that the column of each matrix, size number of columns is equal to the number of rows of the next matrix. So that product is well defined. Okay? And our goal is to find an optimum way to compute this product. What is the sequence of basic operations of multiplying two matrices together that I need to perform to get the minimum overall cost? And this is equivalent to finding an optimum way of bracketing. So remember when I did A times B times C, the choice was whether to put the bracket like this, okay, or to put the bracket like this. Now in general, if I give you now A times B times C times D, then you can do many things, right? You can do A, B, C, D and then multiply. Or you can do C, D, then B, C, D, then A, B, C, D. Or you can do A, B, then A, B, C, then A, B, C, D. Okay, so there are many different ways in which you can partially compute pairs of products of pairs and build up the whole thing. So we want to find the optimum way to do this. So let's try and identify the inductive structure in this problem. So our goal is to compute this long product M1 to Mn. But remember that at every stage we can only multiply two matrices at a time. So at the final stage we would have multiplied two such matrices. Now we can regroup by bracketing, but we cannot reorder. So when we did the final stage, we would have had two groups, right? So we would have done some product from the left to the midpoint and some product from the midpoint to the end, right? So for some k, we would have computed M1 to Mk and Mk plus 1 to Mn. In the first part, after doing all this, we'll have as many rows as M1 and as many columns as Mk, so it will be R1 times Ck. Second one will be Rk plus 1 to Cn, right? And we know that Ck is going to be equal to Rk plus 1, so that these two can be multiplied together, right? So the final cost is going to be M into N into P, which is R1 into Ck into Cn. So we know how much the last step takes. Assuming that it was broken at Mk, the last multiplication costs us this much. Now to get the total cost of doing it with this particular choice of k, we have to get the cost of computing M1 to Mk and Mk plus 1 to Mn. Right? So we have this final situation, and now we have these two subproblems. Right? So we have these two subproblems. So the total cost is going to be the cost of the first subproblem, however much it takes to compute M1 to Mk, however much it takes to compute Mk plus 1 to Mn, plus the cost of the last step, which is to multiply these two subproblems after they produce one matrix each, to multiply those two matrices together. But we have said that this k could be anywhere between 1 and n. So which k should we choose? So the spirit of these kind of problems that we have been seeing, these inductive things, is that we don't try to make a choice. Okay? We say we have no idea in advance which k is good. So we just try out all possible k's and take the best one. In this case, the minimum one. In other words, the cost of multiplying m1 to mn in terms of total number of operations should be the minimum value of k between 1 and n. It has to be strictly less than n because the second part will be mk plus 1. Okay, so between 1 and n of multiplying the matrices 1 to k, multiplying the matrix k plus 1 to n, and adding the cost of the last multiplication. Okay. So now in turn, if I look at this for example and I break it up, it will break up at some intermediate point mj. Right? So I'll have some mj plus 1 to mk. Right? So I would get arbitrary segments from 1 to n as my subproblems. So a natural thing is to define the inductive structure on an arbitrary segment from mi to mj, where of course I is less than j. Okay? So we want the minimum value for any k in the middle, k between I and j, of going from mi to mk and then from mk plus 1 to mj, and the cost of the last multiplication, which is r1 into ck into cj. Okay. So as before, we will just use the index. So instead of writing cost of m1 cross m2 or whatever, we will write ij. Cost of ij is the cost of multiplying mi to mj, that whole sequence. So let's look at the final inductive form of the equation that we need to compute. So the base case is when we are looking at a sequence of length 1. Right? So if we are computing, for example, m1, m2, m3, m4, then one possibility is that I break it up as m1 times m2, m3, m4. Now if I am doing this breakup, then the cost of doing m1 is nothing, because if I am computing from 1 to 1, I am doing no multiplication. So the cost of ii is 0. And then otherwise, I use the recursive formulation we had before. We take the minimum value for k ranging from I but not strictly less than j of the cost to I to k, cost k plus 1 to j, and ri times ck times cj. Okay. And of course, we will only compute this when I is less than or equal to j. We will never want to compute it when the index j is smaller than I. Now it's instructive to check what happens when I do something like cost I plus 1. Okay. So what this will say is that I want to take mi plus 1. Now my only possible value for k, so k should be between I and strictly less than I plus 1. So that means the only possible value for k is I. So this will break up this thing as mi to mi and mi plus 1 to mi plus 1. Right? And then inductively those will give me cost 0, and then I will only get the cost of multiplying this pair, which will exactly come out of this term. Right? So there is no problem with this base case. We only need the base case when the two indices are exactly equal. So now, as before, we will have this matrix to fill up. Because we have, this is not used because we require, so I is going this way. So we have the first index going this way and the second index going that way. So we basically never need to look at values where the ending point is before the starting point. So we only need to look above the diagonal. Right? And now if we are trying to compute the position ij, then we will need cost ik. That is, in this row we will need values between for smaller values than j, and we will need values of the form jk, kj rather, right, in this column. So we will need the values below and to the left with respect to the diagonal. Right? So one way of doing this is to fill up this way, so that wherever we fill up, we have the values below already, and we also have the values to the left. Okay? So we will fill up this matrix from bottom to top. You can also fill it up by diagonal, but it's very painful to program it. So it's better to do it in either row by row. So you could also start like this, right? You could also do it this way, so that wherever you start, you have the values below and to the left. Okay? So you start from the diagonal and work right or up. So either you start at the top left and work down the diagonal, and each column you do bottom to top, or you start in the bottom right and work up the diagonal, and each row you do left to right. Okay? So either of these will work. So here is a pseudo code for that. So we first initialize a diagonal to be 0. Okay? And now we do what we said before, is that we start all the columns. Okay, so this should actually be from column
So column 1 we don't have to do because that is the diagonal element. So we started column 2 onwards, right? So 2 to n. Then for every row starting from the diagonal up to the top row, we now need to compute this minimum. So we initially assume that the value to be filled there is infinity. Now infinity could just be the product of all the dimensions plus 1, because you know that that's not going to, the cost is not going to exceed that. So you can choose a large value. And what you do is now you check for each value of k, you find that inductive thing. You look at r to k, k plus 1 to c, and then r times ck times cc. Okay, so you look up this particular value, which is the inductive thing, and then if it is smaller than the value you have seen so far, so this is basically computing that min over k. By setting it to infinity and then looking and updating every time. So this is just a direct implementation of the recursive, of the inductive thing, and it's just enumerating the subproblems in a way which respects the dependency as we have seen before. So one interesting thing to note is that we are filling up an order n square table. Now when we looked at longest common subsequence or edit distance, we said that the complexity of the problem time wise was exactly the complexity of the size of the table. We had an m times n table, it takes m times n time to fill it up. Because in those two problems, we were filling up each entry looking at exactly 3 neighbors. So we had a constant lookup. Now here what happens is that when I'm above the diagonal at some distance, in order to fill this entry, I need to scan this row and this column. Right? So the amount of time it takes to fill one entry in my matrix could be linear. In the extreme case, when I'm very far from the diagonal, I could be spending order n time to fill that entry. Right? So each intermediate value of the matrix could require looking at n intermediate, each value, each position could require looking at n intermediate values. So though the table is of size n square, the actual complexity of filling the table is of size n cube. Okay, so that's why this is an interesting problem, because it says that you cannot directly conclude the complexity of a dynamic programming algorithm from the size of the table that you are trying to update, because it also depends on the amount of effort you have to take to update each entry in the table. So in the last lecture of this course, we will look at the celebrated question about P and NP, which is often mentioned as one of the last and most important open problems in computer science. So we have seen that a checking algorithm is something which allows us to verify whether or not a given problem's solution is valid. So a checking algorithm doesn't necessarily solve the problem itself, but what it can do is take an input to the problem, a potential solution to that problem, and validate whether or not that solution is indeed one. Right? So without having solved the problem itself, it can just check whether a given solution is a valid solution or not. So the class NP is the class of problems for which such checking algorithms exist, with the additional constraint that the check runs in polynomial time in the size of the input. Right? So the checking should be efficient. So in all the problems we have seen in the last lecture, this is in fact true. Factorization is an NP because given two factors, we can multiply them efficiently to get the answer that we want and check. Satisfiability, again, because we just have to take the assignment of true false to the formula variables and verify whether the formula evaluates to true after that. Again, traveling salesman is the bounded version. We can take a set of a given path, check it is a simple cycle, add up the weights and verify that the bound is satisfied. Likewise, vertex cover and independent set, right? So these are all in NP because the solution can be validated efficiently with respect to the input size. One thing to note is that in problems like traveling salesman, vertex cover and independent set, we took an optimization problem and converted it into a bounded checking problem. But we also said that the bound could then be exercised using binary search in order to find the actual answer. So this binary search adds a logarithmic factor. So overall, in some sense, there is no loss of generality because you take a polynomial times step and then you multiply it by a logarithmic thing, so everything is still the same. So there is no difference really between the pure checking problems like satisfiability and the modified checking problems which involve introducing a bound like traveling salesman or vertex cover.
So why is this class called NP? So NP comes from the word non-deterministic polynomial time. Right? So this is a historical reference. So it refers to the fact that these correspond to problems where you can non-deterministically guess a solution. Right? You can magically produce a solution, and then in polynomial time, you can verify whether the solution is correct or not. So the actual origin of this term comes from computability theory, from the theory of non-deterministic Turing machines. So if you have studied that, then you will know why it is called NP. But if you have not studied that, it's not so important as to realize what it implies for algorithms. So NP comes from non-deterministic polynomial time, which in turn comes from Turing machines. So the two classes that people talk about are P and NP. So we have just seen what NP is. So what is P? So P is just a class of problems which we have been trying to explore in this course. These are problems for which you have a worst case algorithm which runs in polynomial time. Right? So recall that we said right at the beginning that we are looking at problems of the form n squared, n cubed and all that. We are probably looking at even less in terms of practical things, such things like n log n, but we certainly don't want 2 to the n and n factorial. Right? So P is the class of all problems, a regular polynomial time complexity in terms of worst case. Now, by our definition, everything in P is also an NP because we don't need to get a solution to check it. Because it's in P, we can actually generate the solution ourselves. Right? So, a checking algorithm asks somebody to give us an input and a proposed solution and then validate it. A problem in P, we can actually generate the solution, so we can validate it again. And therefore, every problem in P is actually an NP. So the question that people want to know is whether P is equal to NP. So it's a converse to. Is it possible that whenever I have an efficient checking algorithm, I also have an efficient algorithm to generate a solution? So intuitively, does not seem to be the case. As we observed, the teacher who is checking the factorization homework need not even know how to factorize. The teacher only needs to know how to multiply. Right? So it seems intuitively much simpler to check a solution than to actually generate one. So let's see whether this intuition can be made formal. Right? So why do people believe that P is not equal to NP? Well, one of the reasons is just from experience, or it's empirical. So we have seen many natural problems, factorization, satisfiability, traveling salesman, vertex cover, independent set. These are all in NP. We have seen that vertex cover and independent set can be reduced to each other. Today we will see that some other NP problems can also be reduced to each other. Okay? So in fact, you can find that all these problems actually are interreducible. This means that they effectively have the same level of hardness, because when things are reduced between one and another, either you can transport efficient solutions or you can claim inefficiency. But effectively, they're all of the same type. If you can solve one, you can solve the other in roughly the same amount of time. So all it takes is to solve any one of these, and all of these problems will then have an efficient solution. But people have been trying these problems from different angles for many years now, and nobody has found one. Therefore, there is good experimental evidence that there is no good solution for these. So let's look at these interreducibilities a little more closely. So we start with Boolean satisfiability. Recall that in Boolean satisfiability, we have clauses. Clauses are composed by disjunction of literals. So we take X or not Y or Z or blah, blah, blah. Right? So we have these ors strung together to form a clause, and then we put these clauses together with an AND. So in general, we argued that it is hard to think of how to find a satisfying assignment, but if we get an assignment of values for all the variables, we can quickly check whether it makes it true or not. So a restricted form of satisfiability is called 3-SAT. Right? In 3-SAT, we have only clauses like X or not Y or Z. Okay? Or we could have two also, X or Y and so on. So we could have even trivial things like Z, but remember, if I have a clause which says Z, the only way to make it, this forces me to make Z true because there's no option. If I have X or Y, I can make X true or Y true. So a clause like this doesn't contribute much to my problem because it forces a valuation for a particular variable, and then I can reduce the problem to one which has 2 or 3. So 3-SAT has typically 2 variables or 3 variables, but not more than 3. It doesn't have 4 or 5 variables. So the first claim is that 3-SAT is as general as SAT. So we will show this just by a simple example. So supposing I have a given clause which has 5 variables like this. Okay. So what I want to do is I want to have only 3 variables. So what I will do is slice off this part. So I will keep the first 2 and I will slice off this part. So I will introduce a new variable a and I will say it is v or not w or a and I will put a not a with the rest. Okay. So now what does this tell me? So this tells me that supposing in this case that these are both false. Okay. Then in order to make this true, I must make a true. But if a is true, then this is false on the other side. So that means that if this clause is true, one of these is true. So in other words, it's saying if both v and not w are false, then one of the other 3 variables must be true, which is exactly what the original clause is saying, that one of these 5 must be true. Okay. On the other hand, if v or not w is true, then I can afford to set a false. If a is false, not a will become true, then I have no obligation on the remaining variables. Right? So the claim is that by this expansion, okay, by removing this one, by splitting away the first 2 variables and adding this intermediate thing linking the 2 clauses, I produce 2 clauses which have the same satisfiability as the original clause. Now again I have, unfortunately, too many variables here. So what I will do is I will now again keep 2 and split the rest off. Right? So I will keep not a x and I will introduce new variable b and then I will take not b and take the remaining 2. Okay. At this point, fortunately, I have now reduced everything to 3 variables. I can stop. If I had 4 variables still, again I will do the same thing. I will do c and not c and so on. Okay. So in this way, I can take any clause which has more than 3 literals and systematically decompose it by adding new literals into a sequence of 3 literal clauses. So I can convert any clause which is not in 3 sat into a sequence of 3 sat clauses. And how big is the sequence? Well, it's going to be proportional to the number of literals in the clause. So the blow up in my formula is going to be linear in the original formula. That's important because we said that when we do reductions, right, we want the reduction part to be efficient, to say that we are not spending so much time with the reduction, otherwise we can't transfer efficiency claims across. So what this tells us is that if SAT is hard as we believe, then so is 3 SAT. Okay, because I have reduced SAT to 3 SAT. So far we have seen reductions which are not very perhaps surprising. We have seen independent set, okay, and vertex cover. But these are similar problems. Similarly, we have seen SAT and 3 SAT. Okay, these are similar problems. Now what we're going to do is we're going to bridge the gap between these 2 different problems. We're going to look at 3 SAT and say that 3 SAT actually can reduce to independent set. Okay, which is a little bit more surprising because they seem to come from very different domains. So here is a typical 3 SAT formula. So we have 1, 2, 3, 4 clauses and each of them has at most 3 literals. So this one has 2 literals and the other one has 3. So since we have 3 SAT, then we have a structure which is bounded by 3. So we will represent every clause by this triangle. And in the triangle, we'll put a label which indicates the literal. So not x is replaced by not x in this thing, y, and so this not x or y or z, not z is this triangle. Okay. Similarly, this is not x or not y or z. Okay. So in this way, every clause contributes a triangle to my graph. So what does this triangle signify? This triangle signifies that if my independent set picks one of these things, say y, then it cannot pick the other 2. Right? So what this is saying is it's going to make exactly one of these things. It's going to identify for me which of these literals is true in order to make this formula actually work out to be true. Right? So it's kind of giving me a witness from each clause. So in order for this to be a valid witness, if y is true here, then I cannot pick not y to be the witness for the next clause because y and not y contradicts each other. Right? So in addition to the triangle, I have these green edges saying that a variable and its complement will be connected by a green edge. Okay, so there should be some more green edges, perhaps connecting this y to that not y and this. Okay, so there should be, yeah. So this y to that not y. So every variable is connected to its complement to indicate that if one is there, the other cannot be there. So what the independent set is saying is it's trying to pick out a solution. It's trying to pick out a solution by looking at each clause, right, and saying that maybe I pick y here. If I pick y here, then I'm going to rule out these things. Okay, and maybe now I can pick y there. Then I have to pick something here. So maybe I pick x here. If I pick x here, I ruled out that not x. I have to rule out this not x. And now I'm in trouble because I don't have anything there. Okay, so maybe I could not have picked that x. So therefore, I go back and say that maybe I should pick this not x. This not x will rule out this x, will rule out this x, and will force me to keep this z. Okay. And now if I have an independent set of size 4, then I'm done. So I can say that the solution now I want is that x goes to false, y goes to true, and z goes to true, right? So the existence of an independent set on this particular thing of size 4, which picks out one per clause. So notice that within a clause I can only pick one. So if I have 4 clauses, okay, and if I insist on the size of the independent set being the number of clauses, then I will definitely have got one witness per literal. And those witnesses have to be mutually consistent because I connect z and not z, x and not x everywhere by edges which rule out the same variable from being set true in one clause and false in another clause. Okay, so this independent set now picks out those literals which make my formula true. So if there is an independent set of size 4, then every clause can be made true in this set of 4 clauses, and therefore I have a solution to 3-SAT. And if there is no independent set of size 4, there is no solution. Right? So 3-SAT reduces to independent set, which is a bit more surprising than our reduction, as we said, from SAT to 3-SAT, which are both similar looking problems, or from independent set to vertex cover and backwards, which are very directly structurally related problems in the same type of graph. Right? So this is the surprising thing. It says Boolean satisfiability and vertex issues, independent vertices and graphs are connected. So we have shown that 3-SAT reduces 3-SAT. 3-SAT reduces independent set. Independent set and vertex cover are mutually reducible. Therefore, for instance, because I can now compose these reductions, SAT now reduces to vertex cover. Okay? And you can find in the literature such reductions for various other problems like traveling cylinder, integer linear programming, and so on. Now, in all these, it's important to remember that we are looking in this context of reductions where the pre-processing and post-processing step are polynomial time, because we want to say that there is no time lost in the reduction. Therefore, all the complexity is in the solution. If I have a simple solution for B, I have a simple solution for A when I reduce A to B. If I have a complex solution for A, then I cannot say that the solution reduction is what makes it complex. It is because the reduction is simple. It must be only the fact that the two problems are similar, that they are actually having the same complexity. So given this, when all these problems are interreducible, it means that all of them are equally hard. Now the famous theorem by Cook and Levin says that every problem in NP can be reduced to SAT. Okay, now this is a rather amazing theorem because it says that if I take everything in NP, anything there I can reduce to SAT. Okay, so there is some reduction by taking an instance of that problem. I can convert it to an instance of SAT, solve the instance of SAT and go backwards. Okay, so we are definitely not going to try and prove this theorem here. It is enough to know that this proof is by encoding a suitably general model of computation. So the original proofs of Cook use Turing machines. You can take Boolean circuits or register machines, anything which is universal, anything which can compute every problem in NP, and then argue that the computation of that problem. So if something is in NP, there is an NP computation. There is a checking problem, a checking algorithm. So you can encode the behavior of that checking algorithm for that problem in SAT. And therefore, it turns out that SAT is equivalent, or everything reduces to SAT. Okay? So this gives us a notion of completeness. Okay? So we say that SAT is complete because it belongs to NP and every problem in NP reduces to it. Okay? This is the definition of NP completeness. A problem is NP complete if, first of all, it has a checking algorithm. It belongs to NP, an efficient checking algorithm. And in addition, every problem in NP reduces to it via polynomial time reduction. Okay, so SAT by definition by the Cook-Levin theorem is NP complete because it belongs to NP, we know, and the Cook-Levin theorem establishes that every problem in NP reduces to it. But now we have seen that SAT itself reduces to 3-SAT. So every problem can be reduced to SAT, and then in a further polynomial step reduced to 3 SAT. So every problem now reduces to 3 SAT. But 3 SAT is also NP. So 3 SAT is also NP complete. Okay? So this is a generic technology now. So you have some problem which is NP complete. And then I reduce it to my problem here, and that makes B also NP complete. Okay, because provided B is an NP. If it is not an NP, then it is something weaker called NP hard. Okay, it is at least as hard as every problem in NP, but may not be in NP itself. Okay, so NP hard says that it is every problem reduces to it, but you are not sure whether or not it belongs to NP. You don't have a checking algorithm for it. Okay, so there are a few problems like this for which the checking algorithm is not easy to describe, but you can certainly show a reduction. But otherwise, if you can do both, you can find a checking algorithm, and every problem you have found some problem which in NP, which NP complete problem which reduces to it, then it is also NP complete. So this brings us back to this question of whether or not P is equal to NP. Right? So many useful problems which are extremely important for day-to-day life, like scheduling, bin packing. So bin packing is basically now if I want to put various objects into a container in an optimum way, okay, or traveling salesman tours, okay, if you want to find optimal tools. All these are very important real-life problems which people would like to solve efficiently. The theory of NP completeness tells us that all of these problems are actually interreducible and therefore equivalent to each other. If I can solve one, I can solve them all. Now we have this experimental evidence that since these are important problems, a large number of smart people have been looking at these problems from even before the time that computer science was invented. Right? People have been looking at scheduling problems and bin packing problems for very hundreds of years. Okay? Therefore, these problems, if they have not yet yielded an efficient solution, then it looks likely that there is no efficient solution. Therefore, from an empirical point of view, okay, purely from experimental evidence, it seems to strongly suggest that NP is different from P. But this is not a proof, unfortunately. Mathematically, one has to argue that NP is different from P by giving a proof saying that there is a reason why some NP complete problem can never be solved using a polynomial time algorithm. Okay, this is what is called a lower bound. Right? So you need to establish a lower bound for some NP complete problem. Okay, and this is very hard. This is proved very challenging. NP completeness was first identified by Cook and Levin in the early 1970s. So it is now more than 40 years since the theory of NP completeness itself was invented. And a lot of people have looked at this problem and nobody has yet found a direct way of doing this. Right? So a formal proof is elusive and it's worth $1 million because there is a prize given by the Clay Math Institute. So this is one of the celebrated open problems in mathematics for which the Clay Institute has awarded a large prize. So if somebody does prove that this is indeed not the case, then there is a large prize at stake. Okay? So with this, it seems an appropriate place to end this course. So I thank you all for listening. So in the last week of this course, we'll look at some advanced topics. So let's begin with linear programming. So the kinds of problems we have looked at so far are largely optimization type of tasks. So we are looking for shortest paths in a graph, or we are trying to identify the minimum cost spanning tree, or we are looking for the longest common subsequence. So we are trying to optimize some quantity, the length of the path, or the cost of the tree, or the length of the subsequence. And then this optimization takes place subject to a constraint. So when we're looking for paths, the constraints are given by the graph itself. Right? So the path must follow the given edges in the graph. So as the graph changes, the path that we identify will also change. Similarly, we are looking for spanning trees with respect to a given graph. So in each graph, we have to first identify the different spanning trees and look for the smallest cost one among them. Similarly, with two subsequences, the actual letters in the sequence determine what is common between them. So we can look at a more general formulation of such constrained optimization problems in the framework of what is called linear programming. So in linear programming, we are given some variables, some quantities that we want to calculate. And then there are some linear functions that constrain these quantities. So a linear function, remember, of a variable x is something of the form ax plus b, right? So it has no x square, x cube term, right? It's all linear. So we have ax plus b. So in general, then if we have multiple variables x, y, z, then we could have a constraint of the form ax plus by plus something is less than equal to some constant, or ax plus by plus something is greater than equal to some constant. And then these are the constraints on the values that the variables can take. And now our aim is to optimize some quantity. We want to minimize or maximize some cost or some weight or something like that. And that quantity is expressed in terms of the variable by yet another linear function. So we have some function which I will again write as ax plus by, but it's a different set of coefficients, of course, for each of the constraints and for the objective function. Okay, so we have a different linear function which tells us what it is we are trying to optimize. So the best way to understand linear programming to begin with is to look at an example. So suppose we are running a sweet shop called Grandiose Sweets, and we sell two types of sweets, burfis and halwa. Now we know that each box of burfis earns a profit of 100 rupees and each box of halwa earns a profit of 600 rupees. So obviously it makes sense to make more halwa than burfis. Now we also know that on a given day we cannot sell more than 200 burfi boxes, we cannot sell more than 300 halwa boxes, and together the staff can only produce 400 boxes. Okay, so now if you make 400 boxes, we can only sell 300 of halwa or 200 of burfi, so we need to make both. So the question is, given these constraints, what combination of burfis and halwa should we make? So let's start by identifying the variables that we are trying to manipulate. So we're talking about the daily production of these sweets. So we will use two variables b and h to denote the number of boxes of burfis and halwa that we produce in a day. Now given this, we know that our profit is 100 rupees per box of burfis and 600 rupees per box of halwa. So it is totally 100b plus 600h. We also have some information about how much we can sell. So we know that we can't sell more than 200 boxes of burfi a day. So b must be less than or equal to 200. And we can't sell more than 300 boxes of halwa a day. So h must be less than or equal to 300. And finally, we are told that together our staff are only capable of producing 400 boxes altogether, whether burfi or halwa or any combination. And implicitly, of course, we can only make a non-zero quantity of burfis. So we can't make minus 7 boxes of burfis. So we have these implicit constraints. We say that both b and h must be greater than 0. Right? So now we can put these all together into a set of inequalities and an objective function and call it a linear program. So the our objective is to maximize the profit. Right? So this is the profit. Right? So this is what we are trying to maximize, the quantity 100b plus 608. And we cannot choose, obviously, if b and h can vary, then we can make them as large as we want, but there are these constraints. So b and h must lie between 0 and 200 and 0 and 300 respectively, and together they can be no more than 500 or 400. Right? So these are the constraints we wrote in the previous page. Now we are just writing them down as a system of equations or inequalities. So we can visualize this quite easily in this case because there are two quantities, basically b and h, that we want to compute, and we are given a set of facts about them. So we know that b lies between 0 and 200, right? So the range for b is anything in this region. At the same time, we also know that h lies between 0 and 300. So this constrains the space that we can look at to this rectangle. And finally, we have the other constraint that together b plus h must be less than 400. Okay? So now that's on this side of this line. So we now have to be within this trapezium. Okay? So overall, this gives us what we can call a feasible region. Any point in this region represents a combination of b value and h value which meets all the constraints. Now we have to introduce our profit function. Right? So our objective is 100b plus 600h. Okay? And depending on what values of b and h we choose, this will be equal to some c. So we can examine what this looks like for different values of c. So for example, if we set our profit to be 60,000, then any quantity along this line, right, any value of b and h which is inside the orange feasible region, will give us 60,000, right? All these points give us 100B plus 60H equal to 60,000. Now if I move this line across this region, the value changes. If I move it further up, I can go from 60,000 to 120,000, 1,20,000. If I move it still further, I can get 1,50,000. When the line actually leaves the region at that corner vertex where the trapezium bends down, we find that we can get 1,90,000. Right? And it turns out that this is actually going to be the optimum value. Now this optimum value happens at some corner of this trapezium, and this is generally the case. One can argue that the optimal value will always occur at a vertex, because as we saw here, the function we are trying to optimize is a line, right? And as we sweep across the feasible region, the value will either keep decreasing or increasing, and so therefore where it leaves the region, it will be some vertex. Now it could be that supposing this optimum line had actually been parallel to this, then both this vertex and this vertex would both have been optimal perhaps, and every point along this line. So it's not saying that there are not optimal values away from vertices, but definitely there will be some vertex which has an optimal value. So if our goal is only to find an optimum solution, it is enough to look at the vertices. So in fact, this is how the very famous simplex algorithm works. So what it does is it constructs this feasible region which is bounded by our constraints, and then it picks a vertex. Okay, so we will not discuss it in detail, but you have to generalize this notion of a corner. In 2 dimensions, it's quite easy to imagine what a vertex is. But if we have multiple constraints and we have to optimize more than 2 dimensions, then you need to define vertex properly. But intuitively, a vertex is a corner of this feasible region. So we start at any of these vertices, evaluate the objective function. Then we look at the neighboring vertices. If any adjacent any neighbor has a better value, we move to that neighbor. If none of our neighbors are better than us in terms of the objective, then we stop and announce that this vertex is the optimum. Right? So we will not go into a proof in this lecture that this is, if it is actually correct, but it's not hard to argue this. But there are of course a lot of details which need to be worked out to implement simplex correctly. So one of the problems with simplex is theoretically it can be exponential. But actually in practice it turns out to be a very effective algorithm to solve linear programs. Now there are theoretically efficient algorithms. So there is a polynomial time algorithm for linear programming. Okay, so there are these so-called interior point methods, and there is a method due to Narendra Karmarkar which many people may have heard of. These are more complicated to describe and program. Simplex is probably easier to program, but what we need to know as far as we are concerned is that once you set up a set of constraints and an objective function using linear constraints, you can solve it efficiently. So of course, we also have to ask when a solution exists. So in our case, we had a solution where we had a feasible region which looked like a trapezium like this. Right? So the first point is that the feasible region will always be convex. Convex means that if you take any 2 points inside the region and you connect them by a line, the entire line stays in the region. So for instance, if I have a shape which looks like this, then this is not convex because I can pick 2 points inside and then connect it by a line, and this line in this portion leaves the region. Okay, so the feasible space will always be convex, but it could be empty. Supposing we had an extra constraint in our earlier thing which says that everything must be below this line. Now in addition to the orange, if I add this blue constraint, then there is no point that satisfies everything. So if the constraints are unsatisfiable, the feasible region will become empty and there will be no solutions. The other possibility is that we don't constrain it enough. Right? So we could just say that, supposing we only say that, say for example, h must be less than 300. Then this has an unbounded region. So as I draw my blue line as we had done before and I keep moving it up, it says the profit keeps increasing. Right? There is no upper bound. Right? So there are these pathological cases where either the feasible region is empty or it is unbounded, where you will not find a solution. But if it is bounded, then what the theory of linear programming tells us is that the objective function will lie, its maximum or minimum will lie on a vertex along the boundary of that bounded region, and so it's sufficient to examine those, and that's what simplex does. So just to get a little bit more practice at this, let's extend the example. So now, in addition to our barfi and halwa, which had the same details as before, 100 rupee profit for barfis, 600 for halwa, we've added almond rasmalai, which gives us a much higher profit of 1300. And almond rasmalai actually people are willing to buy in an unlimited quantity. So the earlier demand for burfis and halwa is the same, 200 and 300, but almond rasmalai can be sold in unlimited amounts. Unfortunately, we haven't got any new staff, so we are still restricted to producing a total of 400 boxes. And now we have an extra constraint, which is in terms of what we can do with the milk that we get, right? So with the milk that we get, we can either make 600 boxes of halwa in a day or 200 of rasmalai or any combination of this. So effectively, a box of rasmalai requires 3 times as much milk as a box of halwa. So now again, given these constraints, we want to find out what is the most optimum production schedule that we should impose on our sweet shop. So if we look at the equation now, the objective function now has an extra quantity, which is the profit we get from rasmalai. So we have an extra variable, we have B and H, which are as before burfi and halwa, and R for rasmalai. So we get 100 rupees per box of burfi, 600 rupees per box of halwa, and 1300 box per box of rasmalai. The constraints on burfi and halwa demand are the same, and there is no constraint for rasmalai, so we don't add anything there. The total production now includes the rasmalai, so all three together must be below 400. And this expresses the milk constraint. Right? So he says at one extreme, I can make 600 boxes of halwa. At the other extreme, I can make 200 boxes of rasmalai because 200 times 3 will be 600. But I can make any combination and that will require the same amount of milk or less. So H plus 3R must be less than or equal to 600. So this is the milk constraint. And finally, of course, all three of these quantities must be bigger than or equal to 0. So in this case, if we draw this picture, it now becomes a three-dimensional geometric object because we have three axes, B, H, and now R coming out in the vertical direction. And the constraints now, instead of lines, they become these planes. So they kind of become now, instead of a polygon, we have what is called a polytope. Okay, we have a three-dimensional object. And again, we will find that you get the optimum at some corner. Okay, and the optimum happens to be in this case that you make 0 burfis, you make a full amount 300 of halwa, and then you make the rest into rasmalai. Okay, and you get a profit of 3,10,000. Okay. So, so we might ask, is this really the case? Okay. So is this really our best thing? So remember that if I do this, I get 300 into 600, right? So I get 1,80,000 from here, and you get 1,30,000 from here, and that's how we get our 3,10,000. So is it? How do I know that this answer is actually the best? Okay, so here is an interesting observation that we can make. So these are some of the constraints that we had before. Right? We have just removed the one which says that the three values B, H, and R are greater than 0 because that's not useful. Now in this, supposing I take the three constraints labeled A, B, and C. Now in general, if I take a constraint and I multiply it, so if I say 2H is less than or equal to 600, right? So we know from simple algebra that this is the same as H is less than or equal to 300. So in the same way, I can multiply each constraint by a constant. I can also combine them, right? I can take some combination of A plus some combination of B plus some combination of C. It tells us nothing new. It just combines it in a different format. So supposing I take 100 times this, and I take 100 times B again, and I take 400 times C and I add them, right? So I will get 100H plus 100H plus 400H, that is 600H. Okay. Then I will get 100B, and finally I will get 1200 plus 100 is 1300R, right? So combining A, B, and C with this combination, where I multiply A by 100, B by 100, C by 400, I produce a new inequality. But this new inequality tells us something interesting, because in fact what we have on the left hand side is our profit, right? So the profit is exactly 100B plus 600 plus 1300R. We are trying to maximize this. And what our constraints tell us is that in the feasible region, this value can be no more than 3,10,000. In other words, right, this is actually the optimum profit, because from our constraints we can derive the fact that we can't get anything more than this. Hence, this must be an optimum value. So in this particular example, it seems that we can prove to ourselves that we have achieved an optimum by just doing something clever with the constraints. So it turns out that fortunately this is not a coincidence. It turns out you can always construct such a combination, right? So if I have now constraints C1, C2, so these are my constraint equations, I can always find some combination. Okay, so I can take some lambda 1 C1, lambda 2 C2, I can add these up, and then I can get from that some upper bound, and that upper bound will actually tell me whether or not the solution I found is right. Okay, so this is called the dual of the LP. Okay, and again we are not going to look into the theory of this, but this is useful to know that we can take the formulation that we start with for LP, right? And then we can ask another question, which is what is the minimum value that we can get by combining the constraints with some linear multipliers. So we get new variables which are exactly these multipliers. What are the values of lambda 1 to lambda k which minimize the combination lambda 1 C1 plus lambda 2 C2 plus lambda k ck, right? So this is my new question. I want to minimize this. Okay, and then this becomes another LP problem, and I solve that, and it turns out that the dual and the original have a solution if and only if that solution is the optimum for both, right? So this gives us one way of justifying that a given linear programming problem has been solved correctly. Let's look at another example of modeling a problem using linear programming, again to do with production. So recall that a linear program is an optimization problem where you have some variables which describe the quantities you want to compute, and you now have linear constraints on these variables as well as a linear function describing what it is that you want to optimize, maximize or minimize. That's called the objective function. And one way to solve a linear program is to think of it geometrically and use the simplex algorithm. And the simplex algorithm exploits the fact that the optimum value of a linear program is always at the vertex of the feasible region. So it starts at some vertex and it keeps going from one vertex to a neighbor until it finds a vertex whose value is optimum with respect to its neighbors, and the claim is that that vertex actually represents a solution. We also said that we can justify that this is the optimum value by constructing the dual, which asks how to combine the constraints together to minimize the combination, and a solution which solves both the original and the dual is actually an optimum value. So the next example we are going to look at is a carpet manufacturing company. So we have a company which makes hand-woven carpets, and we currently employ 30 employees. Each employee produces 20 carpets a month and is paid 20,000 rupees a salary. So if we just look at the cost per carpet, then we are paying 1,000 rupees to manufacture each carpet. Now it turns out that our monthly demand is seasonal. So after looking at some past data, we have made an estimate of the amount of carpets that we can expect to sell in each month of the year. So we have a range of demand from 440 to 920. So remember that if I have 30 employees and 20 carpets each, I can make 600 carpets in a given month. Okay, this is what I can do with my current staff. Now sometimes the demand is as low as 440. So if I make 600 carpets, now if I have 30 employees and each one is going to produce 20 carpets a month, I'm going to get that done, right? So I'm paying a person to make carpets, not to sit idle. So every employee will produce 20 carpets a month. Therefore, I will always produce 600 carpets, but I'll have 160 perhaps which I can't sell that month. But there are some months where I would have a demand for 320, and now it's a question of whether I have enough carpets to sell or not. So I know the demand from January to December, and say these are stored as D1 for January, D2 for February, and so on to D12 for December. So I have these 12 quantities which are known in advance. These are how many carpets I can expect to sell in each of these months. So now I have to come up with a strategy to cope with this varying demand in order to make sure that I lose the least amount of money because of this demand fluctuation. So one possibility is that whenever I have extra demand, okay, I pay overtime. So if I pay overtime, I get workers to work longer hours and make more carpets. But there are two costs to this. The working wage per hour for overtime is typically higher than the regular wage. So let's assume it's 80% extra. So if you remember, originally we paid 1,000 rupees per carpet as our labor cost. So if I make it in overtime, it's going to cost me instead rupees 1,800 per carpet, because it's going to take the same amount of time and the person is going to be paid 80% more. So 80% of 1,000 is 800. So it's going to cost 1,800 per carpet is the overtime rate. And the other thing is that you cannot, of course, expect somebody to work 24 hours a day. So there is a limit saying that a worker cannot make more than 30%, cannot spend more than 30% overtime. So if they make 20 per month normally, then at most they can go plus 6. Right? A single worker can make at most now, including overtime, 26 per month. The other option for me is to add or subtract employees. I might want to add new workers in case I have a higher demand projected that month, or I might need to terminate some employees in case my demand drops below 600. But this also comes with a cost, okay, because I have to do some paperwork and also I have to give some compensation and so on. So let's assume that there are some certain costs. 3,200 is the cost associated with hiring a worker, and 4,000 rupees is the cost associated with firing a worker. And finally, I can store carpets when I have made excess and sell them later when I have a demand, but storage also costs something. So let's assume that storing a carpet costs rupees 80 per month, because I have to keep it carefully, avoid damage from moisture and all this. Right? So these are the various options. I can pay overtime, but up to a limit, and it costs more for a carpet made by a person who's being paid overtime. I can either add or subtract from my workforce, but this also comes with a cost each time I do it. And finally, I have a surplus storage cost in case I want to keep my production handed over from one month to the next. So we want to make a linear program out of this. So we need some variables. Right? So we are dealing with these 12 months, January, February to December. So it's natural to think of everything as happening within the scope of 1 month. So for month I, where I ranges from 1 to 12, let's assume that we have WI workers. Initially we have 30 workers. Right? Then from these 30 we will either hire or fire some to get the workers in January. Then we will hire or fire some to get in February and so on. So each month potentially we have more or less workers, but we start with 30. Now these 30 workers will make some number of carpets. So let's assume that the total number of carpets made in a month is Xi. And OI, which is included in Xi in terms of the total, but OI is specifically the number of carpets which are made in overtime, because for these there is an extra cost. Okay? This is over and above the salary we already pay the worker. And finally, we said that we have this hiring and firing costs. So let HI be the number of workers hired at the beginning of a month, and FI be the number of workers fired at the beginning of a month. And let SI stand for the number of surplus carpets that I have in stock at the end of month I. So I initially assume that I have an empty warehouse. So S0 is 0, but S1 will say at the end of January how many carpets am I storing. S2 will say at the end of February how many carpets am I storing, and so on. Right? So there are 1, 2, 3, 4, 5, 6 quantities. Each of these quantities is there for 12 months. So I have 72 variables. Plus I have these default initial variables for W0 and S0. So I have 74 variables. Okay? So this is a lot of things that I have to estimate. But it turns out that actually in a linear program this is not a large number, and it can be solved quite efficiently by any of these standard things, including simplex. So let's now think of the constraints. So the first constraint is the usual one, which is that every quantity that we are talking about is strictly greater than or equal to 0. The second constraint talks about how the number of carpets made break up into the regular production plus the overtime. So if I make I carpets in a month, then each worker, remember WI is the number of workers in my establishment in month I, will make 20. Right? So 20 times WI is what workers in month I produce in the normal time. And in addition to that, OI is just the number of carpets made. So OI is not the number of hours overtime. So OI is the number of carpets. Right? So each month I make 20 times the number of workers plus OI. Now if I had I minus 1, WI minus 1 workers last month, and I hired a few and I fired a few, then the total number I have now is the old number plus the number I've hired plus minus number I've fired. Okay, so this is a constraint on how each of the wi's is connected to the previous wi. Similarly, the stock is connected to how much I had before I started this month, how much I made this month, and how much I sold. So remember that D1 to D12 was the demand. So this is a fixed quantity. These are not variables, these are known values. So in this month I would have sold DI, but I produced XI. So XI minus DI is the excess that I produced this month, or the deficit, as the case may be. I started with a surplus of SI minus 1. So if I add this month's surplus or deficit, I get the total surplus at the end of the month. Okay? And remember, I can't have negative carpet. So SI, all these things must always be bigger than equal to 0. And finally, as we said before, a worker who produces 20 carpets in a regular month, if I add now the fact that he can do 30% overtime, okay, this is 20 plus 6. Right? So the number of carpets made in overtime can be at most 6 per worker. Right? So OI should be less than or equal to 6 times WI. Right? So these are our constraints now. So now, given these constraints, what we want to do is minimize the total amount of cost that we are going to put out. So first, this is the regular salary cost. Okay, so the regular salary cost is 20,000 per worker, and we have W1 workers in month 1, W2 in month 2, and W12 in month 12. So we add up the total number of workers. Each of them is paid 20,000 rupees. So this is our total salary bill for the year. Then, depending on how many people we hire in each month, for each hire we pay 3,000. So this is our hiring bill. Similarly, for each person that we dismiss, we have to pay 4,000 for that. So this is our firing bill. Then the number of carpets that we have to keep in storage in each month incurs an 80 rupees per carpet cost. So I have to multiply the total storage by 80. And finally, when I pay overtime, I am paying over and above the salary. So each carpet made in overtime, remember, costs 1,800 rupees as opposed to 1,000 rupees, which is already accounted for in the salary. So this is my overtime cost. So now, so this says that we can take this fairly complicated looking question about production with demand and hiring and firing and productivity and all that, and set it up with some 72 plus 274 variables and a complex cost function, and feed it to simplex and get an answer. So we run simplex and we find a solution. So are we done? So it turns out that we might get an answer which is not something that we can actually use. For instance, we might get an answer which says H3 is equal to 10.6. Okay, so this tells us that we must hire a fractional number of people in a month. Now obviously we cannot do this. At the same time, we have not in any of our constraints expressed that the values must be integers. So what can we do about this? Well, we can take this 10.6 and we can look for the nearest integer 10 or 11 and re-evaluate what happens to the cost if we make it to an integer. So this is called integer rounding. Now, if the values are big, they're like 10, 11, if they are 2-digit values, say, then rounding is a relatively small displacement and the quality of the optimum will not change much based on this. But if the numbers are small, if I'm rounding between, say, I'm going to take it from 0.5 to 1 or 0, or from 1.5 to 2 or 1, then the effect of that rounding is can be quite drastic. Right? So this is a general problem with linear programming, which is linear programming cannot guarantee you that you have integer solutions when you want an integer solution. You can use rounding to achieve an integer solution, but you have to be careful that the rounding actually gives you an optimum. Now, why not just insist that you want an integer solution? So can you not set up the same problem and solve it, but require the solutions to be integers? Unfortunately, this turns out to be quite a hard problem. Right? So we have claimed rather that when we set up general linear programming problems, we can solve them efficiently. So simplex is not an efficient solution, but an effective solution. But there are interior point methods and other polynomial time algorithms for linear programming. But if you change the rules of the game and say, I don't want an arbitrary solution that meets the constraints, but I want one where all the values that I get are integers, then we have the so-called integer linear programming problem. And integer linear programming, unfortunately, is not solvable efficiently, or at least not known to be solvable efficiently. So the best we can hope to do for integer linear programming is to actually turn it into an arbitrary linear program and somehow interpret the answers as integers by doing appropriate rounding. So for our next example of linear programming, we will look at a problem involving graphs and networks to do with network bandwidth. So suppose we have a small communication network involving three users. So the users are capital A, capital B, and capital C. And each of them is connected through some switches which we call A, B, and C. And so we have a network which, this is an internet network, which connects these three users, and our requirement is to ensure that each pair of users, A to B, B to C, and A to C, gets at least 2 megabits per second of connectivity from between that pair of users. Right? So we want at least 2 Mbps connectivity along these three routes. Now notice that from A to B there are two ways I can send packets. Right? I can send them directly via A and B, or I can send them indirectly via small c. Right? So it turns out that it doesn't really matter from the point of view of the users whether this 2 Mbps bandwidth comes from the shorter A red route or the longer green route. Okay? So our aim is to combine the capacity of the red and the green for each pair. Okay? So similarly there will be, for example, there will be a direct route from B to C, and there will be an indirect route that goes like this. Okay? So for each pair there is a direct route and an indirect route. So long as a combination of the capacities of the direct and the indirect routes adds up to at least 2 Mbps, our customers are satisfied. So now the constraint that we have is that these links have a capacity. So if I look at, for example, the link between B and C, it can only transmit 13 megabits per second total across all the different connections that it is a part of. Now on the other side, we earn some money from these customers, which is not uniform. So for the A-B link, we get 300 rupees per megabit Mbps per month. Okay. For B to C, we get only 200, but for A to C, we get 400. So now we have to allocate a minimum of 2 megabits, but the customers are willing to take as much as we can give them, subject to that minimum. And we get a certain amount of revenue depending on how we utilize the capacity. So our goal is to allocate bandwidth to maximize the revenue, given that the customers are willing to take anything above 2 Mbps. So as we have been seeing, our aim is to set this up as a linear program. So in this case, what are the variables that we are going to use? So recall that we said that every connection has two routes, right? So we have A to B coming via the short route, and we have A to B coming via the long route. So what we'll use is the variable x from A to B to denote the quantity that is flowing on the red route, and similarly y from A to B to denote the quantity that is flowing on the green route. Right? So we have two variables associated with the A to B service that we're going to provide. How much goes directly XAB, how much goes indirectly YAB. Similarly, between B and C, we'll have XBC which goes through the short route and YBC which goes via the long route. And same way for XAC and YAC. Right? So we have these 6 variables describing the different ways of connecting pairs of customers. Now these variables are constrained by the capacities of our links. Okay? So supposing we look at this particular link, the link from small b to capital B. Now it has a capacity of 10. Now what routes does it lie on? So it certainly lies on the short route A to B. So it lies on the XAB route. So if any quantity which is assigned to XAB will eat into this 10. Similarly, it lies on the YAB route. Right? Because that also has to ultimately reach capital B through small b. So this will also eat into that. It also lies on the B to C route, right? So XBC. And finally it lies on the B to C route going the other way, which is YBC. So all these 4 routes put together will add up to whatever capacity is flowing through this link, right? And this link has capacity 10, so XAB plus YAB plus XBC plus YBC has to be at most 10. So likewise, if I look at, for instance, this link, in the same way I have all these different things which are coming here. Right? So I have 4 quantities. I have the direct link from A to B, the indirect link from A to B, the direct link from A to C, the indirect link from A to C, and they all must add up to at most 12. and the third same holds for this. Okay, so these three constraints that we have seen here, okay, account for the capacities of the tail end links. So we have accounted for this capacity, and this capacity. Okay, so these three capacities are connected to our flows by these three equations. So this still leaves us to account for these three constraints. So now if you look at this link, okay, then this is part of three connections. It is the A to B direct connection. Okay, it is on the B to C indirect connection. And finally, it is on the A to C indirect connection. Right? So that says it's a direct connection A to B plus the indirect connection B to C plus the indirect connection A to C all together cannot be more than 6. Okay? In the same way, we have a similar equation for this link. Right? So it lies on the indirect connection from A to B. It lies on the indirect connection from, it lies on the indirect connection from A to B, it lies on the direct connection from B to C, and it lies on the indirect connection from A to C. Right? So these three things cannot exceed 30. And the third same thing holds for 11. Right? So for 11 we have that it lies on the direct connection from A to C and on these two indirect connections, right? A to B indirect connection and B to C indirect connection. So in this way now we have covered the 6 constraints. So we had 3 constraints corresponding to the tail end links and we had 3 constraints corresponding to the links of the triangle. So we have 6 total constraints. Okay? Finally, we have this minimum requirement that between A and B we must apply at least 2, between B and C we must apply at least 2, and between A and C we must apply at least 2, and these are the sums of the indirect. We don't distinguish between them. And of course, every capacity must be non-negative. Right? So this gives us all our constraints. And what is our objective function? The objective function is the revenue that we realize. Okay? So the A to B connection is XAB plus YAB. This is the total volume. That gives us 300. Similarly, XBC plus YBC gives us 200. And XAC plus YAC gives us 400. So if we multiply 300 into XAB plus YAB, 200 into XBC plus YBC, and 400 into XAC plus YAC and add it up, this is our total revenue and we want to maximize this revenue. So for these particular numbers, these are the answers that we get. Okay, that we have nothing flowing directly from A to B. We have 7 going from A to B indirectly and so on. So if you look, for example, at this link. Okay, so this link lies on the direct route from A to B, so that is 0. It lies on the indirect route from A to B, that is 7. It lies on the direct route from B to C, that is 1.5. Okay, and it lies on the indirect route from B to C, that's another 1.5. And if you see that, this is 10. Okay? So therefore, this link has a total capacity of 10, and all 10 units are being utilized given the combination that it gives. Right? So in this way, you can try for each link and find out that everything except this link of 11 is actually saturated by this flow. It also turns out here that you can see that some of the quantities that we get are fractional. But since we are dealing with internet bandwidth, there is no reason, it's not like hiring or firing a person or making half a carpet. Okay, we can easily split our bandwidth in some fractional quantities, so that's not a problem here. There is, however, another problem, okay, which is the way we have actually set up the linear program. So the way we have set up the linear program is to take each possible way of routing the traffic. So we have A to B, we have a link. We have A to B like this, we have another path. And for each path, we have a variable. We have XAB, YAB, and so on. Right? So every path is represented by the quantity flowing through that path. So the problem with this is that the number of paths flowing through a graph is going to be exponential. So this is not a good modeling strategy. So what we are doing is we are taking this network bandwidth allocation model and we are implementing it, or we are describing it using linear programming. But if we set up a linear program which has a large number of variables, then the problem is in some sense blowing up in complexity in the translation. So we don't want this, we want efficient translations. Okay, and this is not one. It so happens that for a small problem like this with only 3 customers, it works fine, but as it grows larger and larger, this translation will not scale up. But we will look at another way of looking at these network flows, as they are called, and see that in general network flows can be easily represented in terms of linear programs. But it's important to note that in general, when we do a translation into a linear program, we would like the number of variables we get to be small, say polynomial in the input problem. So in the input problem, if we have a certain size, the linear program should not blow up. In the bandwidth allocation problem, we use one variable per path in order to encode a network flow problem as a linear program. And we argued that that's not an efficient way to do it. So let's look at a more direct way to represent network flows in terms of linear programs. So suppose we have an oil network, which is shown as given in this directed graph. So we have a source vertex S, right? And we have a target or a sink vertex T. And our aim is to ship as much oil as we can from S to T given the pipes that we are given. So of course one property of a flow is that it must flow. So I cannot keep any quantity at any intermediate node. So anything that enters B must leave B. Anything that enters D must leave D, right? So if we try to do this, then for instance, this green quantity represents one possible flow. I send 2 units from S to A, 1 from S to B, 4 from S to C, and you can check that these are in fact within the capacity, because I could have sent 3, 3 and 4, and I've sent 2, 1 and 4, and I keep going, and therefore now at this particular thing I have a total of 7 units which flows out of S and 7 units which comes into T. So I'm able to flow 7 units from S to T given this network. Right? So we can just verify this locally that this is the flow by checking, for instance, at D the total quantity flowing in is 2 plus 1, 3. Nothing is stored because the total quantity flowing out is again 2 plus 1, 3. Right? So if we can do local checks like this, we can satisfy ourselves that this is a valid flow. The total amount is 7, but the question is this the maximum? How do we know whether we've achieved the maximum or not? So the problem, just to phrase it formally, is that we are given a special type of graph. Okay, so it's a directed graph, and it has 2 special nodes, a source and a sink. The source has no incoming edges and the sink has no outgoing edges. Okay, each edge has a capacity, which is a weight associated with it, and our aim is to come up with a flow. A flow is again a quantity that we will assign each edge, and now the flow must satisfy some basic conditions. The flow must always be less than the capacity. Then we have no storage. So at every internal node, the total amount flowing into the node must be equal to the total amount flowing out. Okay, so this is called conservation of flow. We cannot lose anything or generate anything at an intermediate node. Everything that comes in must go out. And finally, what we want to do is we want to optimize the total volume of flow, and the total volume of flow is the amount of flow which is coming out of here, which is also of course the amount of flow which is going there, because no flow can be lost. Okay, so we can look at either end, but let's just define it to be the total volume of the outgoing flow from the source node. Okay. So now we have this formulation in mind, so we can now set up a linear program for it. Right? What we do is we associate, as we said, one variable for each edge. So for instance, for the edge for SA we have FSA, and then for the edge BD, for example, we have FBD, and then for CE we have FCE, and so on. Right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I believe, edges. Oh, yeah, 11 edges, and therefore we have 11 variables in this linear program. Okay. Now, what can we do with these variables? Well, first is we can say that each variable is constrained by the capacity of the corresponding edge. Okay, so FBA. So BA is now this edge. It has a capacity of 10. So whatever flow I finally arrive at from B to A must be less than 10. Then the other thing that we can say is that we must have a conservation of flow at each internal node. Right? So for instance, if I look at this node D, then the incoming flow is AD plus BD, and the outgoing flow is DC plus DE plus DT. Right? And these two quantities must be equal. FAD plus FBD must be equal to FDC plus FDE plus FDT. And finally, so these are the constraints. Right? The constraints say that every edge can only carry a flow within its capacity, and every internal node there is conservation of flow. And finally, our objective is to maximize what happens on these three edges, FSA plus FSB plus FSC. This is our objective function. So, of course, as before, we will just invoke a linear programming solver such as simplex on this and get an answer. But what we will do now is to understand what this actually means. Remember how simplex works. So simplex starts at a vertex in our feasible region and keeps going from one vertex to the next. So as long as it's increasing the flow, okay, it's actually taking an existing flow and adding something to it. And this can actually be interpreted directly in terms of a flow finding algorithm. So there's an algorithm called the Ford-Fulkerson algorithm, which actually tries to directly solve a network flow problem by gradually building up an optimum flow. So the algorithm assumes you start with an zero flow, and then you choose some path on which there is spare capacity. And then on this path, you augment the flow as much as possible so that that flow path becomes saturated. So now, if you look at the algorithm network on the right, it's very clear that there is a flow possible of two. You can send 1 unit of flow that way, and you can send 1 unit of flow this way. But the Ford-Fulkerson algorithm says take any path which exists and start flowing things to there. So you could, for instance, begin with this path, the one that goes from S to D, and then from D down to E, and then to T. So this flows 1 unit, but now at this point, this edge is now saturated, and this edge is now saturated, and of course this edge is in the wrong direction. So I cannot make use of these two capacities to generate the second unit of flow. So it looks like the Ford-Fulkerson algorithm reaches a bottleneck if you choose the wrong path to start with. So the solution is to say that even if we have taken a bad path, okay, one of the things we can do is reverse the decision we made earlier. So we want to say that if we are flowing one through this, then we can reduce this flow. Okay, so we can divert this flow back another way. So that's a bit complicated to describe, but one way to solve it is to actually set up an extra edge allowing us to flow things back. Okay? So this is what we call the residual graph. So in the residual graph, what we will do is we will actually take the flow that we just constructed, and then we will change the capacities. So the forward edge S to D, which had capacity 1 and flow 1, now has residual capacity 0. Right? So if we have a regular edge, then we replace its weight by the actual amount that is still available. So that is the capacity minus the current flow. And in addition, we add these new edges, these backward edges, okay, which correspond to the flows that we have committed but which we may want to change later on. So we have sent a flow 1 from S to D, but now we can reduce that flow by sending some flow back from D to S. So that's what this is supposed to mean. Right? So formally, this is how you construct the residual graph. You take the original graph, then any flow that you have set up in an existing edge, you reduce the capacity of that edge by that flow. And corresponding to that flow, you set up a reverse edge, which allows us later to undo this. So going back to this example, right? So what we would do is we would first start with this wrong flow, and then we will say but then we build this residual graph, and now we will observe that in this residual graph there is a path which goes like this. Right? So we are not talking about the original graph, we are only talking about the residual graph at each stage. So we will build this. Now this will result in a new flow. So this will end up producing a 0 here, a new edge back here, similarly a 0 here, a new edge back here. Okay, and this one will now become cancelled out because now this path is this flow, so this is restored to 1 and this edge will disappear. Okay? And now in this new graph, we will find that there are no edges left because I have 0 capacity going from S to D, I have 0 capacity going from S to E, so I can't leave any flow from S. So this is my final flow. Okay? So this is the Ford-Fulkerson algorithm. Let us look at it again in a slightly similar structure but with a slightly different set of numbers. So this is a graph which has not ones but some 20s and 30s. So here intuitively the claim is that all 30 units can flow. But the 30 units cannot flow, unlike the earlier case, along the edges of the diamond, because if I take 20 units up, then I must split it as 10 plus 10. Right? So I must recognize that 10 must go down and 10 must go there. Similarly, if I put 10 here, then this 10 and the incoming 10 combine to form this 20. So this is how I get a flow of 30 in this graph. But if I start the fourth Fulkerson algorithm, it will try to saturate a path. So supposing it identifies the path S to D to E to T. Then if it identifies this path, then it has put a 20 flow through this edge. Okay. So we start by this flow and we build the residual graph. The residual graph says that this 10 is 30 minus 20. Right? The residual capacity from D to E is now 10 because I had a capacity of 30 and I put 20 through. And the blue edge is now the residual edge, which allows me to reduce this 20 back. Similarly, from S to D, I had earlier a capacity of 20. I've put 20 through it, so its reduced capacity is now 0. But I have a backward edge which allows me to undo this later if I want. And the same with E to T. E to T has reduced to 0, but I have a backward edge. Now I look for another path in this graph. So for instance, I find that this path is there. Right? I have a path from S to E to D to T. And in S to E to D to T, my constraint is 10. Right? Because I have only 10 flowing out of S to begin with. So I take that 10 and then I build a residual graph. Okay? So when I take that 10, these quantities here, okay, which are associated with this edge, gets restored back by 10. Because the total flow from D to E was 20 in the first round, minus 10 in the second round is 10. Therefore, the residue is 30 minus 10, okay, equal to 20. Right? And everywhere else now I've got 0 because I've saturated. Now if I look at S, there is no outgoing flow possible in this residual graph. So then I say that there are no more feasible paths and I stop. And the residual edges, or if I've been keeping track of the flows, will tell me that I've achieved a flow of 30 in this graph. So again, if we want to ask a question as to why a given flow is optimal, we can ask for some quantity which is a certificate of optimality. So if we go back to our original oil shipping thing, we claimed that we could set up a flow of 7. Okay, so by hand we constructed a flow of 7. Now let's look at these three edges, the edge A to D, the edge B to D, and the edge S to C. If we disconnect this graph by cutting these edges, rather if we cut these edges, we disconnect this graph. Okay? So these three edges form what is called a cut between S and T. Now in this cut, the total capacity is 4 plus 1 plus 2 is 7. Now if there's any flow at all, however it flows, it must cross from this side to this side, right? From the left to the right. So it can only flow from the left to the right through the edges with that part of the cut. But the cut can only support a flow of 7. So therefore, our optimum flow can definitely not exceed 7 in this example, which we have already achieved. Right? So we know that we can do a flow of 7, but no more than 7 is possible because this cut will prevent anything more than 7 from flowing from the left to the right. So actually in this case, this shows us that 7 is optimal. So in general, you can look at various such cuts. So a cut is any set of edges which disconnects S from T, and you can calculate the minimum cut across all of these. Right? And it is pretty clear that the maximum flow cannot exceed the minimum cut because it has to cross this cut. Right? So you have to go from one side to the other, it can only take that much capacity, so the flow cannot exceed that. So what is surprising is actually that it will always, in this example of that we did, it was equal, but it is always going to be equal. Okay? So the max flow min cut theorem says that the max flow is actually always equal to the minimum cut. So here is one way to understand this. So if we look at our LP solution, right, when we achieve the maximum flow, okay, then S is going to be disconnected from T. There is no further path. If I look at edge weight 0 and I remove those edges, then there is no further path. Right? So S is disconnected from T, so there is a cut. There are some edges which disconnect S from T. Now let's look at any edge in the residual graph at that point, which goes from the left hand side to the right hand side. Okay? So left is everything. So everywhere inside this I do have paths with non-zero weights. Okay? And everywhere inside this I do have paths to T with non-zero weights. So now, but I cannot get from the blue side to the green side. So that means that in the forward direction, all the edges must have saturated the capacity, right? So every edge from L to R is actually at full capacity. What about an edge in my residual graph from F to R to L? The claim is that if there was some capacity here, then there would be a reverse edge which goes this way, right? Which would be at non-zero capacity. So there would be a path from S to T, but there are no paths. So this must be at 0. So all the reverse edges must be at 0, all the forward edges must be at full capacity. So this gives a not very precise, but a reason why the max flow will actually saturate this cut, but this could be any cut, right? So therefore the minimum cut in particular will be saturated, and therefore the max flow cannot exceed the minimum cut anyway, right? So the max flow must achieve the minimum cut value. So one thing that one has to be careful about in the Ford-Fulkerson algorithm is the choice of how to increase the path. So remember that in our pathological examples, we instead of going around the diamond, we go through the center. So supposing we keep doing that, then what will happen is that here after one iteration, we'll go through the center and then we'll reduce this to 99, this to 0, and this to 99, and we'll set up a reverse edge of size 1. Then in the next iteration, we'll go in the reverse direction and we'll again reduce this to 99, this to 99, and then we'll set up this, reset this edge back to 1 this way. So this way we can keep zigzagging. So I'll go from 99 to 98 and then down I'll go from 99 to 98. So it will take me 200 iterations in order to find this path that this flow has 200. On the other hand, it's pretty clear that I could have done it in 2 iterations if I had been cleverer. Okay, because I could have just said, oh, initially there is a path of 200 there and that saturates those 2 edges, and there's another path of 200, there's a path of 100 there and a path of 100 here. So in 2 iterations I can achieve 200. So it depends quite crucially on how I pick the path to augment. How do I take the feasible paths which still exist in the residual graph and choose which one to add to. So in general we cannot say anything good, and Ford-Fulkerson is going to take time which is proportional to the capacity of the edges, which is not a great idea, because although the edges may be large, you might be able to directly say, oh, this edge can take 100, the next edge can take 100. So in one shot, I can say the whole path can take 100. But if I have to do one at a time, then it becomes an extra parameter, not the actual size of the graph. But how do we do this feasible path business at all? Right? So every time we set up a residual graph, we have to find a path from S to T, okay, and then augment it. So this we would have seen right at the beginning of this course. We will either do it through breadth first search or depth first search. Finding a path from one node to another node is typically the exploration of the graph. If we use breadth first search, then what do we know? We find the shortest path in terms of number of edges. So one can prove that in this Ford-Fulkerson algorithm, if you use breadth first search at every iteration to decide which path to augment, then you will be augmenting always the shortest path in terms of edges. So for instance, in this example here, if you had a choice between augmenting that path, the path which goes above like this, and the path which goes like this, then breadth first search will say that the red path has got 2 edges and the orange path has got 3 edges. So the red path is shorter, so you must augment that first. Okay? So if we use breadth first search in the Ford-Fulkerson algorithm, it turns out that you will always get something which is proportional to the product of the vertices and the edges. So it will be polynomial in the size of the network independent of the capacities. We have seen that we can use linear programming as a technology to solve a number of problems. And formally this involves what we call a reduction. So rather than reducing to linear programs, let's look at how we can actually reduce to network flows, which we saw already could be reduced to linear programs. So here is a problem which seems to have nothing to do with flow. So we have some course allocation to be done in a school. We have a collection of teachers and we have a collection of courses. And each teacher has indicated a preference of which courses he or she is willing to teach. So here we have 4 teachers, Abbas, Chitra, Madan and Sunita. And we have 4 courses, math, history, biology and economics. So Abbas for instance is willing to teach history and biology. So that's these 2 edges. So this indicates that Abbas is okay with teaching these courses. Similarly, for instance, if you look at Madan is happy to teach history or economics. Okay. So each teacher has indicated a collection of courses that he or she is willing to teach. Now what we have to do is allocate these courses to the teachers. Obviously each course is going to be taught by exactly one teacher. Okay? but also we would like that each teacher teaches only one course, and that course should be something that the teacher is willing to teach. So we would not like an allocation, for example, which asks Abbas to teach math because he has indicated that he is not comfortable teaching math. Right? So we want to find such an allocation that each course is taught by a single instructor. Each instructor teaches only one course, and that is a course which he or she is willing to teach. So this is what is called a matching problem. Okay. In particular, it's called bipartite matching. So what is a bipartite graph? A bipartite graph is in which one in which the vertices come in two groups, which we call V0 and V1, and all the edges go from V0 to V1. So there are no edges inside V0. There are no edges inside V1. Okay. So this is the example here. So this, for example, the teachers are V0 and the courses are V1. Now there are no edges between courses, there are no edges between teachers, all the edges are from a teacher to a course. Okay. Now what we have asked is to find an allocation. What will an allocation do? An allocation will pick an edge and say, for instance, that Abbas will teach history. Now once Abbas has been assigned history, then this means that this edge cannot be taken anymore, because Abbas cannot be assigned anything else. It also means that this edge cannot be taken, nobody else can be assigned this edge cannot be taken. Okay? So we want to find edges such that no two of them share an endpoint. In this example, if two of them share an endpoint on the left, it means that the same teacher is being asked to teach two courses. If the two edges share an endpoint on the right, it means that the same course is being taught by two different teachers, neither of which we want. So we want a matching. We want a matching which is a subset of edges so that no two of them share an endpoint. And in particular, if we have an equal number of nodes on each side in a bipartite graph, then we can expect or hope that everything on the left is matched to something on the right. Okay? If we don't have an equal number, of course something has to be left out, because each edge will match up two people. So supposing we have 5 teachers and 4 courses, then one teacher will not teach a course. Or if we have 4 teachers and 5 courses, then some course will not be taught unless a teacher takes 2 courses. But if you have 4 teachers and 4 courses, you could ask whether there is a way of matching them up so that every teacher teaches a course and every course is taught by a teacher. This is what is called a perfect matching. So what has this got to do with network flows? So here is how we can answer this question using network flows. We add a spurious source node feeding into the teachers, and we add a spurious target node, a sink node coming out of the courses. So implicitly all our edges are now going from left to right. Right? So we have the direction. So we are trying to flow something from left to right. Now what we want is to assign capacity 1 to everything. So every edge in this has capacity 1. Right? So supposing we find a maximum flow. So a maximum flow will select some subset of these teachers. Right? Hopefully all of them. Because it is a flow, that flow will go into a teacher and out of a teacher, so it will select one of these edges, say this one. Okay? And therefore, now it will flow from this out here. Now because the output can only take 1, I can only flow 1 from history to the sink, it cannot allow another thing to come in from here. So if I had a flow 1 here and a flow 1 here, then 2 would have to flow out of the history, but I've got it. So by putting a flow capacity of 1 on all the edges, I ensure that exactly one teacher and one course can be selected in the matching. And now if we maximize this flow, it maximizes the number of teachers who are connected to the courses, and therefore it maximizes the matching. Right? So we have managed to take a problem involving something very different involving graphs and model it using network flows. So this is a general example of what we call a reduction. So we want to solve a given problem, problem A, but we don't know how to solve it. But we do know how to solve another problem B. Right? So in our case, this is matching, and this is flow. So what we do is we transform our problem from matching to flow. So we take our matching problem and then we add a source, we add a sink, we add capacities, convert it into a flow problem. Right? So having converted into a flow problem, we solve it. So this is the diagram shown below. Right? We have an algorithm for B. So now we have a matching input. We convert it into a flow input. This is the flow solution that comes out. Okay? And now we look at the flow solution. Wherever we see a 1, that is our matching. Wherever we see a 0, that's not in our matching. So from that we get a matching solution. Right? So we can invert the solution from the inner problem to get a solution to the outer problem. So this is a reduction. Okay? So we say that A reduces to B. To solve A, I can convert it to B and solve B instead. Okay? And therefore, if I have an efficient solution for B, and if this conversion process is efficient, that is the process of setting up the problem for B and interpreting the answer are both efficient, then that's the efficiency of the algorithm for B composed with the efficiency of the pre-processing and the post-processing step will give us an efficient algorithm for A. Right? So without directly attacking A, I have indirectly found an efficient algorithm for A by exploiting the existence of an algorithm for B. So as we said before, our example that we did in this lecture says that bipartite matching in this way reduces to max flow. Now what we saw last time was that max flow itself reduces to linear programming. But the key is that the pre-processing and the post-processing must be efficient. When we went from max flow to linear programming, what we did was we introduced one variable FE for each edge E. Okay? So therefore, that is an efficient translation because it produces a linear program whose size is comparable to the input graph for max flow. Earlier we had seen an example of network bandwidth where we produce a linear program which required one variable per path in the network. That would not be an efficient reduction because that would require an exponential amount of work to construct the linear program and to reinterpret it. Okay? So therefore, we have to be careful in order to, if we are only interested in solving the problem, is one thing to convert it to another problem, but if we want to exploit the efficiency aspect, then the translation to and from the inner problem must also be efficient. So we will see that another interpretation of reduction is also useful for us. So what we have seen that is that if A reduces to B, okay, then if B is efficient, then this implies that A is also efficient because I can use the solution for B as solution for A. But supposing I have that this is not efficient or not known to be efficient, if I have some reason to suspect that there is no efficient way to do A, then if I can show that A can be reduced to B, then this also means that B cannot be efficient, because if it could be done efficiently, we know that we can do A efficiently, but we have reason to believe that A cannot be done efficiently. Right? So reduction can be used depending on the way in which we exploit it, either to transfer a positive result from B to A or a negative result from A to B. That is, A is not known to be efficient, B also is not known to be efficient. So in this last couple of lectures, what we have seen are two what I would call big hammers. Okay, so we have linear programming and network flows. We actually express network flows in terms of linear programs, but network flows independently are a very powerful modeling formalism. So many algorithmic problems can actually be reduced to one of these two. Either you can set up variables and set up a linear program, or you can take a graph theoretic problem and model it using flows. And the nice thing about this is that linear programming and network flows are both very standard problems for which people have invested a lot of time to write general purpose tools which solve these problems. So you can set up an arbitrary linear program, an arbitrary network flow, give it to the tool will give you an answer. So you have efficient off-the-shelf implementations. So in many practical situations, rather than try and solve an algorithmic problem directly, it does often make sense to think of whether it can be modeled as a linear program or a network flow, and then use an off-the-shelf package to solve it. But of course, you have to be able to express the problem in terms of one of these things. So in order to understand whether you can do so or not, you need to spend some time analyzing what can and cannot be expressed as linear programs. In linear programs, the crucial thing is that the constraints must be linear functions. Sometimes you have constraints which refer to the product of two variables. This is not a linear function. Similarly, in network flows, you have to make sure that you can actually model it as a source to target flow. Okay? It cannot be something going around and around in a network. So within these constraints, however, both of these are extremely useful generic problems for which efficient solutions do exist and which can be exploited in a large number of situations to solve the given problem at hand. So most of this course has been about identifying efficient solutions to problems. But it's also important to realize that there are some situations where no known efficient solution exists. And we have to be able to recognize this so that we don't fruitlessly try to look for solutions where the problem is known to be hard to solve. So let's look at some issues involving intractability. So in many of the problems that we have seen, we are trying to search through a number of possibilities to arrive at some kind of optimum combination. The actual search space is exponential. If you are looking for shortest paths, there are an exponential number of paths. If you are looking for a minimum cost spanning tree, there are an exponential number of such spanning trees to search through. If you are looking for the maximum flow, we have many different ways of adding and subtracting flow along edges. So if we look at all possible flows, all possible paths, all possible spanning trees, and then choose the optimum, this would be a brute force solution which would take exponential time. When we have a polynomial time algorithm, we are actually cutting through this exponential and in some very drastic way reducing our search space from an exponential one to a polynomial one. So it is tempting to believe that if one just thinks long enough and hard enough, that any such problem we will always find such an efficient shortcut, okay, where we can cut through the exponential space of possibilities and quickly narrow down the space to a polynomial number of realistic ones from which the efficient solution, the actual solution we want, will emerge. Now, unfortunately, this ideal world is not actually the way the world is, right? So there are many problems for which efficient algorithms don't exist or are not known to exist. And unfortunately, also many of these problems are extremely important practical problems. So to get into this discussion, let's talk about the difference between generating a solution and checking a solution. So supposing a school maths teacher assigns the following homework. Okay? Take a large number which is known to be the product of two prime numbers and find these two prime numbers. Okay? From the student's point of view, obviously, the problem is to generate the solution. So given the large number n, the student is expected to find two prime numbers p and q such that p times q is equal to n. Now the student submits, or the students submit their solutions to the teacher for evaluation. So the teacher is in a much better perspective, right? The teacher doesn't have to keep generating p and q. The teacher doesn't even need to know the answer, right? So the teacher can just take the answer given by the student, multiply p times q, and determine whether p times q is equal to n or not. So even without knowing the answer, or even if the answer is wrong, the teacher may not know the right answer, the teacher can decide whether or not the student has given the correct answer. So what the teacher is doing is checking the solution. What the student was trying to do was generate a solution. So this gives us a notion of a checking algorithm, right? So if I have a problem, I can say that I have a checking algorithm if for every instance, okay, I can take a solution to that instance and quickly verify whether or not that solution is actually a valid one, right? So a checking algorithm takes an input for the problem, a solution which is maybe not just the solution but solution plus some extra information, right? And then it determines whether or not this is a valid solution. If so, it says that the solution is correct and outputs yes. Otherwise, it says no. So in our example before, the factorization example, the input instance is the number n to be factorized. The solution that we get as a candidate to solve the problem is the pair of primes p and q that the student has calculated. And the checking algorithm involves verifying that p times q is actually n. So in this context, let's look at a very canonical problem which has a checking algorithm called Boolean satisfiability. So we have some Boolean variables x, y and z. So Boolean variables can take values true or false. And we have the standard operations on Boolean variables. Negation takes a value of true and turns it into false and vice versa. So we write that with this exclamation mark using some programming language terminology. So not x is written as exclamation mark x. Then we have x or y, which is true provided at least one of them is true. So if either x is true or y is true or both are true, x or y is true, we write that with this vertical bar or pair of vertical bars. And we use ampersand to denote and. X and y is true only if both are true. So x must be true and y must be true. If either one of is false, x and y is false. So this is the standard Boolean operations that we know about Boolean variables. Now we set up Boolean formulas in a very special form. we first construct what we call our clauses. So a clause is a big disjunction. It's X or y, not Y or Z or something. So what is inside the disjunction are either variables or their negations. So these are called literals, right? So a literal is either a variable or a negated variable. So clause is read as this clause is X or not Y or Z dot 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 or W. So this is a clause. And then finally, a formula will be a combination of such clauses connected by ands. So C will be some X or Y or something. D will be some Z or not Y or something, and so on. So each clause will have the structure of a big disjunction of literals, and then they are combined by an ampersand. So they are all ANDed together. So I need to make clause C true, and I need to make clause D true, and I need to make clause E true, and so on. So our goal is to find out whether this given formula can be made true by assigning suitable values to X, Y, and Z. Okay, all the variables in the formula. So this is called a valuation. So a valuation is a function that says X is true, Y is false, Z is true, and so on. So it fixes the value of each Boolean variable. Now having fixed that, I can evaluate, right? So for example, if I take X to be true, Y to be true, and Z to be false, okay, then here for instance, in this clause, X is true, so that's enough to make the whole clause true, Y is also true. In this clause for instance, X is true, so this part is true, X is true. Here it says Y is true, Z is false, so both of these are actually true. And now here it says X is false, okay, not X, but X is true, so not X is false. Y is true by our valuation, not Y is false. But fortunately Z is false, so not Z is true, right? So in each of these clauses, at least one of the literals becomes true under this valuation, so this entire formula is actually satisfied. Now, if I add this extra clause here to the same formula, now it turns out there is no way to find any way of assigning true, false to X, Y, Z to make it true. You can check that this particular valuation doesn't work because if I look at this, it says that X is true, so this doesn't work. And it says that Z is false, so this doesn't work. So Z is false, so Z is not true. Not X is true, so not X is false. So this is false or false. So this clause actually evaluates to false. So this particular valuation which made the first formula true doesn't make the second formula true. And in particular, no valuation will actually make it true, and that can actually be checked if you look at these three clauses. Okay, this can be said as that Y implies X. What this says is that if Y is true, then X must be true, and this says that if Z is true, then Y must be true, and this says that if X is true, then Z must be true. So this more or less says that X, Y, and Z must all be the same. But then if X, Y, and Z is all the same, then either one of the first or the last clause is going to be false. Actually, there is no satisfying assignment. So our goal is to find out whether there is a satisfying assignment or not. Right? So to generate a solution, of course, the brute force approach is to try assigning each of X, Y, and Z true and false in turn. And then once we have assigned X, Y, Z to be true, false, we can evaluate it and check if the formula is true. And we try this for every possible such assignment. Okay, there are n variables. Each of them has two possibilities. Clearly, there are 2 to the n. Okay, so an exponential number of possible assignments. Now, the amazing thing is that in general, no better algorithm is known for this problem. Okay, at the moment, as things stand, we do not know an efficient way to take a formula in this form and find out whether it has a satisfying assignment. However, it's easy to check that it has an algorithm which can check a solution, right? So if I give you a formula and I claim that a given valuation is actually a satisfying assignment, all I have to do is plug in that assignment like we did for the earlier case. I can say, oh, you say Vx is true, let me put true everywhere I see X. You say Vy is false, let me put false everywhere I see Y. And then evaluate the formula, find out whether the ands and the ors add up to a true answer or not. So it's easy to see that this has a checking algorithm, but it doesn't have a generating algorithm. At least we don't know of one. So in this case at least, and in other cases also, sometimes the presentation of the problem is important. So we said that a clause was a disjunction of literals and then a formula was a conjunction of clauses. What if we reverse this? What if we say a clause is a conjunction of literals? So in the clause I connect everything with and then I connect the clauses with or. This means that I must make C true or D true or E true. Earlier I had to make C true and D true and E true. Now if I look inside a clause, how do I make a conjunction like this true? Well, it's easy, right? I must make each of these true. Unless I make everything true, this whole AND will fail. So if I take a clause, then the settings of the variables inside the clause force me. It says x must be true, y must be, not y must be true, so y must be false, z must be true, and so on. So I don't have much choice. Now inside a clause, I might see not y, and then somewhere else I may see y. Right? So therefore, this such a thing will say, oh, I'm being asked to set y true and y false, so this clause cannot be true. Then I move to the next. So I look at each clause, I check whether the unique valuation it insists on is plausible or feasible. If it is, I'm done, because I only need to satisfy one clause. Otherwise, I move to the next one. Right? So in a linear scan from left to right, I can basically solve this problem if it is given to me in this form. Okay? Whereas in the earlier form, there is no efficient algorithm. So clearly the presentation of the problem is important. So let's look at a completely different problem. So we have this well-known traveling salesman problem. So a salesman is supposed to visit a network of cities, and between each pair of cities, we have a distance. Right? So we can think of it as a complete graph. Every city is connected to every other city, and on each edge between two cities, there is a weight indicating the distance or the cost or the time or some quantity which the salesman has to use up in order to travel from the one city to the next city. So the salesman's goal is to visit every city on this map. Right? So the salesman wants to find the shortest tour that visits each city exactly once. So in a graph theoretic sense, what it means is that you have a simple cycle. Simple cycle means that no nodes repeat. I don't visit the same vertex twice along this thing, which starts and ends at the same state. That's why it's a cycle. So we start and end at the same city, same vertex, visit every vertex in between, and of minimum cost. So once again, there is no simple way to write a generative algorithm which will actually analyze this and find a good solution. Right? So now our question is there a checking solution? Is there a checking algorithm? So recall that what a checking algorithm does is it takes as input, it takes an input instance and it takes a solution and then it says yes or no. Okay, this solution works, this solution doesn't work. So now we have a graph and somebody gives us a cycle. Okay? We can verify that it's a cycle. So that part is easy. We can even compute the cost of the cycle. That's also easy. But how do we know that among all the different cycles, this is the least cost? Right? So it's not very clear that there is a checking algorithm because in the end, though we can verify part of the solution, that it is a cycle that visits all the cities and we know its cost, we have no way without solving the problem. Remember, the goal of a checking algorithm is not to solve the problem. It's to ask whether this given solution is correct for this given instance. So we may not know how to solve the problem. Like the teacher who's assigning the factorization homework. The teacher does not need to know how to factorize, does not even need to know the factors. The teacher only needs to know how to multiply two potential factors and check whether the answer is the same as the big number given. Similarly here, we just need to check whether the given nodes form a cycle, but unless we know how to solve the problem, the checking algorithm cannot figure out whether it's the least cost cycle or not. So how do we get around this? So the solution in such optimization problems to convert them into checking algorithms is to transform the problem by giving a bound. Okay, so you give an upper bound or a lower bound depending on how. So in this case, we'll not just ask if there is a tour, if there is a traveling salesman tour of lowest cost, we'll say is there a tour with cost at most k. Right? So we have just given a bound on the cost. We are not asking for an optimum tour. We are just only asking for a tour which does not cost more than k. Now we are given a solution, we can check it because we can check it's a cycle and then we can add up all the edges which form part of the tour and find out whether it adds up to k or less. Right? So how does this help us? Okay, because our goal was to find the shortest tour. What we have said now is that if I give you an upper bound in the size of the tour, I can use a checking algorithm for yes or no. But now we can try a different case, right? So we have the minimum value of k is clearly 0, okay? And the maximum value is some upper bound. What is a good upper bound? Well, we know that a tour is going to take edges from the graph. If I take all the edges in the graph and add up all the costs, the total tour cannot be more than that. Okay? So I have a range of values possible for the cost of the tour from 0 to say the sum of all the edge weights in the graph. You might even find a better bound than that, because obviously you can't use all the edge weights. You can only use n of them to complete a cycle of size n. Okay, but this is a very conservative bound. Now what we do is, we do in this range, we do binary search. So we first check, is there a tour of whose cost is midway? If there is, then I will now check below, is there a tour of cost half of that? So by doing a binary search, we narrow down the thing, and finally we'll find that this is the level where we have a tour, and above that we have tours, and below that we don't have tours. So this is the minimum cost tour. Okay, so by using a binary search and an upper bound, we can take an optimization problem where we are looking for an optimal answer and transform it into a sequence of checking problems, which after a logarithmic search through the space of the bounds will give me the actual solution I want. So here is yet another problem. So this is called the independent set problem. So we say that two vertices are independent if they are not connected by an edge. So for example, here if you look at say 1 and 7, then they are independent because there is no connection. Similarly 6 and 5 are independent. Okay. So we say that two vertices are independent if there is an edge. Now if I take this set, if I take 1 and 7, this is independent. But if I add 5 to it, for instance, now 5 and 7 are connected by an edge, so these are not independent. So an independent set is one in which every pair is independent. Okay, so 1 and 7 is an independent set, but 1, 5, 7 is not an independent set because 5, 7 is an edge. So here, for instance, you can check that 3, 4, 5 forms an independent set. Okay, because there is no edge between 3 and 4, there is no edge between 4 and 5, there is no edge between 3 and 5. So for example, if you are trying to, if you say you interpret these nodes as people and you note edges as knowing each other. So supposing you want to set up some kind of a committee where you want to be sure that all the committee members have independent opinions and are not influenced by the facts that they know each other before that. Okay, then you can pick up an independent set. So an independent set will produce people who mutually do not know each other. So therefore, when they meet for the first time, hopefully they have neutral opinions about each other, about the problem that they have. Okay, so this might be one example of why you want to pick up an independent set. So the algorithmic problem is to find the largest independent set, right? So here we have found an independent set of size 3. Can I do better? Can I find one of size 4? Maybe, maybe not. Right? So this is my algorithmic problem. Given a graph, what is the largest independent set that I can find in it? Now, as we saw before, this is a problem where we have to get an answer. So if somebody tells me 3, 4, 5 is a maximum independent set, I can verify easily that 3, 4, 5 is an independent set, but I cannot necessarily verify that there is no larger set. Okay, this is like the traveling salesman problem where I can verify that the tour given to me is a simple cycle, but I may not be able to verify that the cost of this tour is the best among all such tours. So once again, if we want to set up a checking version of the problem, we will set a bound. We will say, is there an independent set of size k? Okay, so we are trying to find the largest one. Okay, so we will say at least size k. So if I say at least size 3 and this produces this, I will verify it as size 3. If I have said at least size 4 and this is my witness, this is my solution, I will say no. Right? So independent set, again, like traveling salesman and Boolean satisfiability, we don't know of a good generative solution. Okay? But by using this bounded version where we provide a number for the quantity we are trying to estimate, we can produce a checking version. So a related problem to this is called vertex cover. We say that a node U covers every edge that is incident on it. So for example, if I take this node, then it covers these 4 edges because all these edges start at 2. Okay? So now a vertex cover is something that covers all the edges. So for instance, if I take 2, I cover those edges. Now this edge is not there, so maybe I take 3 to cover it. So I take 3 and this covers these edges. Now I still have some missing edges, so maybe I pick up 7. Okay, so 7 covers these 3 edges. Okay. So now I have found a collection of 1, 2, 3 vertices which cover all the edges in this graph. Okay. So now what we want to do is find the smallest vertex cover in a given graph. Right? And again, because we don't know how to do smallest in general, okay, we will say that we will take any vertex cover which is at most size k. Okay, because we're looking for the smallest one. So it is like the traveling salesman, we're looking for the shortest tour. So we'll say, is there a tour of less than or equal to certain cost? So is there a vertex cover less than or equal to certain size? So these two problems look connected, and in fact they are. Okay. So here, for example, we have a vertex cover of size 4, which is indicated in green. So the connection is that U is an independent set of size k, if and only if its complement is a vertex cover of size n minus k. Right? So in our case, U 3, 4, 5 was a vertex independent set of size 3, then its complement must be a vertex cover of size n minus k. So if I could solve the vertex cover problem for a certain size, I can solve the independent set problem for n minus k. So I can convert one to the other. Okay? And the proof of this is very easy. Okay? So supposing I know that U is an independent set. U is an independent set, then no edge is within U. Right? So if I take any edge, UV, okay, then if one end is inside U, the other end must be outside U. Right? Or both endpoints are outside U. So therefore, if I take any edge, at least one of its endpoints lies in V minus U. So V minus U covers all the edges. So therefore, V minus U is a vertex cover. And of course, given that this has k vertices, the other one must have n minus k vertices. Conversely, supposing I assume that V minus U is a vertex cover, then every edge starts from there. Okay? If every edge starts from there, one of its endpoints is there. So I cannot have an edge which is entirely within the complement. Because if I have an edge which is like this, then this is an edge which is not covered by the vertex cover. Right? So there cannot be any edges within U, therefore U is an independent set. And once again, the sizes are guaranteed because they are complementary sets of vertices. Right? So this says that independent set reduces to vertex cover with the complementary size. This is the bounded vertex version. And vertex cover reduces to independent set. Right? So they reduce to each other. So when we introduce reducibility in the context of linear programming and network flows, we said that one aim is to transfer efficient solutions from B to A. So when I reduce A to B, if B is efficient, then A is efficient. But in this context, what we are trying to say is that if this is not known to be efficient, then this also is not known to be efficient. Right? So since independently, we believe that independent set is not efficient, then because it reduces the vertex cover is also likely to be not efficient, and vice versa. Right? So it turns out that many pairs of checkable problems are such interreducible problems, either directly or we might find a cycle of things. A reduces to B, B reduces to C, and C reduces back to A. Right? So in that sense, all of them are equally easy or equally hard. And since we tend to believe that nobody has solved any of them yet, that they must all be hard, okay, this gives rise to the belief that there is a large group of problems which are actually practical in terms of their usefulness, but not known to be efficiently solvable in terms of our notions of algorithmic efficiency. So we will look at this a little more detail in our last lecture.